for you, and it's just waiting for you, and all the hardware, computer technology around you is generally waiting for you. And we can use this for useful things. We could play video games. We could have it help navigate for our cars. Someday we might even have self-driving cars. And it's really, in a sense, in my mind, silly if you spend your whole life not really understanding this technology. And I think it's important that we learn to tell these computers what to do rather than just let them increasingly control our lives. And so, as we'll see, computers aren't very smart on their own. We humans are the ones that imbue them with knowledge, but we need to learn to speak their language. It is much easier for us to learn to speak their language than it is for them to learn to speak our language. Although, with these cell phones, we're starting to see little bits where they can begin to understand, but you would be amazed at the 40 or 50 years that it has taken us to understand how to build programs to begin to understand. So I'm bringing you into something where you are going to learn the ways of programming and the ways of the computer, because it's easier to teach you how to program than it is to teach this how to work in your world. Even though ultimately the goal is to get this to do work for you. So part of what I'm trying to do is move you from a user perspective where you just look at the computer as something that someone else has constructed and you are the user of, to the point where you construct new things. Now the first kinds of things that you're going to construct are actually things to solve your own problems. And it's very popular now to work on data. Python is an excellent programming language for data mining and data analysis, and that's a lot of what we're going to do in this course. Although really it's a gateway to all kinds of things like, artificial intelligence or gaming, or navigation, or mobile applications, or entertainment, all kinds of things. But first we have to learn to program. We have to move from using the computer as a tool to using the tools within the computer that allow us to change how the computer sees the world. So there's a couple of reasons that you might want to be a programmer. Some of you are looking to improve your career, to be paid to work on programming. I've been a paid programmer most of my life, and I like it. It's a good job. You don't have to stand in the mud. You don't have to lift things. You have to use your brain. And I'll just say that it has been nice for my career to not be exposed to the elements, but to be able to work often wherever I want. But that's actually our secondary goal. Our first goal is to get you to write programs that solve problems that you have to solve. Maybe you have a job as an accountant or a lawyer or something else, and maybe you run across some data. Maybe there's some system that logs your time and it's not quite giving the report that you want to give. And so you say, could I just grab the log data myself and write a program to do some analysis to say, oh, what's the average this versus that, or the average of some other thing, right? And so that's the basic idea, that you'll initially use computers to serve your own ends. That makes it a lot easier to write programs because you don't have to worry about, a million users using your software. If it works for you, then we're happy. And so it takes a little more training to write software for other people or for thousands and thousands of other people. And so part of what I want to do is I want to change your perspective. You look at this from the outside and you see it from the outside and you click on things. I want to turn this around, and I want you to be the person inside this looking out at the world. And as a programmer, we are making things inside these computers for the world. And so we want to pull you into being part of this. We want you inside this, or thinking inside this. And what you learn is that if you're inside this computer and you are taking your instructions to build programs to be used by the human, oops, I'm gonna drop that, the human outside the computer, you have things that you need to take advantage of. There's things like the central processing unit, the memory of this system, the network connection of this system, the disk drive or permanent storage on this system. And as a programmer, you are kind of mediating between all those internal resources that this has that are not very smart but highly powerful, and mediating with what that user wants, right? And so we take the end user, and we programmers, we serve the end user, but the computer serves us. So together, between us and all the computer's resources, we can serve the needs of the end user. And we do this by writing code or programming, okay? And what is that? Well, programming is a sequence of instructions where we are giving instructions to the resources inside the computer in a way to accomplish the goals of the end user. And remember, sometimes we are our own end user. It's not just you know, you're not always doing a startup, you're not always writing a mobile gaming system. Sometimes you're writing something for yourself, but that's okay. So sometimes you're writing something to solve a problem. You're like crafting, you're doing something that you could do by hand or manually, and you're making some clever little 25 or 100 line program, and you're putting that in. Other times, like when I work on the open source learning management system, Sakai, it is my creativity. I've got an idea and I want to share it with 1 million users. And so I write my code for an external audience. And so code is that sequence of instructions that the computer itself doesn't know how to hand a roster out, but I can write code that will hand a roster out by looking at the data that's inside this computer, inside this application. And so if you think about programs, we have programs for computers and programs for humans. And a number of years ago, now I'm starting, sooner or later this will be me showing my age, this is an example of the Macarena. And the Macarena is a song that effectively is a sequence of instructions. You put your left hand out, you put your right hand out, you put it on the shoulder, you wiggle, 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 and you spin around and you do things. And this is a program for people. And so I want you to take a quick look at this and see if you can find anything wrong with this particular program. So look really closely. So I'll show you. It's got some typographical errors in it, and we as humans are really good at reading or hearing typographical errors and correcting them automatically and instantly. And but computers are not. Computers are extremely literal. If it saw this ham instead of hand, it would think, what's a ham? And why am I going to hit someone in the back of the head with a ham? And why would I take my left hand and hit somebody? That's, these are all bad things. But the computer is going to take us very literally. And so we have to be really precise. And the computer just doesn't know the difference between what we mean and what we say. So we have to be very precise. And this is one of the great frustrations that people have when they first start using computers. And so we have to get this right. We have to get these little bits of text exactly the way they are. Computers will blow up with syntax errors, and they seem to make quite a fuss when you make the tiniest of errors, but you'll get used to that. I mean, that's not because you're bad or you're less than awesome. It just means the computers can't compensate when you make small mistakes. And so you got to get used to the fact that the computer is sort of intellectually not as strong as you, and so it gets confused really easy. Even though when it gets confused, it says seemingly mean things to you. So you'll get used to that. Okay, so the first thing I want to do is I want to throw up some text, and I want you to, while this text is up, I want you to count the number of each word in this text and tell me what the most common word is in this text. Okay? So here we go. Okay, so I kind of made that hard on you on purpose by moving it around and distracting you and confusing you. But even if it's not moving at all, it's a little bit, tricky to do. You probably stare at it a couple of times. Your brain is going back and forth and back and forth. And so text analysis is one of the great things that computers are very, very good at. And some of the things that they can translate text, and that's because they've looked at a lot of information. So looking at text is actually something computers are really good at. And so if we take a look at the kind of programs that we're going to write to do this kind of thing, this is something that humans are not naturally good at, but computers are super good at. Now, I'm not going to have you look at this code. This code you will understand in a few weeks, but basically this is a set of instructions to open a file, read that file, read all the words in the file, create a histogram of all the words in the file, and then search through that histogram to find the most common word and tell us what the most common word is in the file. And in this clown file, the word "the" is the most common. It happens 7 times. And here's another large file called words.txt, and the word "to" is the most common thing. And our goal is to get to the point where you can write this on your own. So you can say, you know what, I got a problem to solve. That is, what's the most common word in this file? I know how to start, and then I know how to finish. I know how to do the stuff in the middle. And we have to learn this kind of weird language. But when we do, we can count millions of words as easily as you count 20 words. So that's the fun of all of this, is to teach you this language so that you can solve that problem so that you don't have to solve it. Because you could solve it, but it's not something that you're naturally good at, and it's hard work. So up next, we're going to talk a little bit about the hardware architecture that you're going to be experiencing as you write programs. Why do I tell you about hardware architecture? You're not probably not going to build any hardware, although it's fun stuff to do. And if you're going to become a computer scientist, which most of you won't want to be, it's a great thing to study. And those who build our hardware are amazingly talented individuals, and it's a really rewarding job. The reason I like talking to you about hardware is because I want to be able to use words at some point and say, oh, secondary storage, or central processing unit, or random access memory, or peripherals. input devices. And I want to be able to say those words, and I want you to be able to understand them. And so I'll start with a little piece of hardware called the Raspberry Pi. And the Raspberry Pi is a cute little single board computer. As we go forward, these things are smaller and smaller and smaller. And the interesting thing is that the architecture of these stays the same, but the number of components drops. So I'm going to start and give you a block diagram of sort of a generic computer and tell you the major parts of it. Now, I'm going to show you some really old hardware, some really new hardware, and then some hardware that is of medium age. And the medium age hardware is probably the easiest one to see. The architecture is the same, okay? And so the basic block diagram is that the brains, if there are brains in computers, which there really aren't. The software is the closest thing computers have to brains. But in hardware, the closest brain a computer has is this, called a microprocessing unit or a central processor unit. And this is designed, 3 billion times a second to ask the question, what do you want me to do next? And these little pins on the back are our instructions, like 32 or 64 of these pins. 3 billion times a second, we send an instruction into these things. Now, we can't sit there and talk to it. We can't. And so the instructions we store in what's called the main memory. And this memory is really fast. And the memory sort of feeds this. And so every time the CPU needs a new instruction, it asks the memory where that instruction is. And so the memory feeds the instruction to the CPU does it, says give me another instruction, CPU does it, gives me another instruction, and that is the basic essence of programming. This asks what's next, and this is where your program is stored, or a program you purchased or came with your hardware, where that's all stored. And those are your places. And so you end up inside, your programs end up inside this memory. So then there's so in software you tend to program the CPU. And if you had bought a desktop computer a number of years back, it would have this thing called the motherboard. And the motherboard is called this because it kind of connects all the components together. And so if you buy memory by itself, it does nothing, but it has a place to plug into the motherboard. And if you buy a microprocessor, it has a place to plug into the motherboard. And if you buy a hard drive, this is a really old hard drive, it has a place to plug in on the motherboard. And so the motherboard sort of connects everything together. The hard drive is secondary storage. Now, the way how secondary storage is different than the main memory, which there it is. I got unpile this stuff. So this main memory is really fast, but as soon as you turn the power off of this memory, it sort of vanishes. And so to store files like word processing files or text files or whatever, you got to store it on something that lasts a little bit longer. And so that's the purpose of the secondary storage. It's permanent. When the power's off, it stores it. Now this one here is in such bad shape that isn't probably storing anything, but it's got these little heads and it spins around and goes in and out. And we'll have a video later that shows you one of these things that's not quite in as bad a shape. If you look, this has 4 different platters that are all spinning around. And so this is just using magnetic material and electronics that sort of magnetize and demagnetize this stuff. And if you look at a disk, they're often rated, physical disks are rated in revolutions per minute, and that's how many times this thing spins around. And if you got an old desktop and you hear it spin up, this is the thing that's spinning. And it's the place that your operating system lives, your files live, your applications live, while they're stored and while the computer's turned off. And then they're loaded into this while they're running, and then this CPU takes the data from the main memory, and your program runs at 3 billion operations per second. So, let's talk a little bit about something that this is probably from the 1960s or 70s. This actually has, if you're an electrical person, it has capacitors. Those little silver things are capacitors. These little colored things are resistors, and that's more capacitors, and then there's wires. Wires move everything. And so when you say like this has millions of transistors, oh wait, that isn't a capacitor, that's a transistor. That's a transistor. When you say that this here has etched, and if you look closely at this, go look at a picture of a microprocessor online, you will see that it has millions of these. And so the difference between 1960 and today is this circuitry of capacitors, resistors, and transistors has been microized and put onto this. It's using a photographic process, and they're tinier and tinier and putting more and more on. And if you think going from millions of these to one of these is crazy, the thing that's happening now, and the reason we have whole computers inside our pocket, is that everything, all of this whole thing, CPU, memory, everything, all of it connected, and the storage is being made smaller and smaller. And so this little single board computer called the Raspberry Pi has one thing in it, and it has the main memory, and it has the CPU, it has connections for things like peripherals like keyboards and stuff. Now it doesn't yet have secondary storage on it. The secondary storage gets plugged in right here via USB. And then if you take it one step farther to my phone, it's got the secondary storage built right in. And so, you know, this picture goes from the size of cabinets in the old days all the way down to really tiny. But at the end of the day, inside it is a highly sophisticated piece of circuitry that asks for instructions one at a time, and main memory that holds the instructions and feeds them. Okay? Central processor does the thinking. Take a look here. Central processor does the thinking. It runs the program. It's asking what's next. It's not really smart, but it's really fast. And so we compensate for the lack of intelligence of this thing by us writing really good software that runs really fast. And so voice recognition on things like phones is possible because computers have so much storage and they run so fast, and the algorithms that do voice recognition are finally starting to work. Input devices like keyboards and mice and pens and whatever, they come in. Output devices are like the screens that we see. The main memory is the fast part of the computer that stores all the programs, and the secondary memory is the permanent storage. Increasingly, secondary memory, do I have any USB sticks in here? I don't. Well, increasingly secondary memory is flash RAM or static RAM with no moving parts. And so you, in a few years, you'll not even be able to see secondary memory with moving parts. But that's okay. It's still secondary memory. It's still memory that lasts. And so you, and where your place is in here, is you live in the main memory. This is you. You are here. And so, in a sense, when the CPU asks the question, what next, it is your job to answer that. And you answer that by writing Python code. And so your Python code, you'll write a file in Python code, blah, 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 blah. And then that Python code sort of gets loaded into main memory. There's a magic translation process that happens. And then your code is actually answering this question 3 billion times a second. 3 billion times a second, you're sitting there. But this is you. You're really out here. But you then write a file, and the file's loaded in, and then the file runs, and that's how things are at. And that's your place in the world. Now, what's actually running is not Python code. There is, as I said, a translation process. You write a Python file, and then Python itself translates this into the actual language known by the microprocessor, which is a series of zeros and ones called machine language. Someday I would love to teach you a class on machine language. But for now, we're going to teach you Python, and we're going to use Python as a crutch. We don't have to talk machine language, but you could, if you really wanted to, you could know how to write machine language. But I assure you, Python is far easier to learn than machine language. So Python acts as a translator, translates what you're doing into machine language, and then the machine language is what's sent back and forth. But still, even though it's translated to machine language, it's you. It is you answering those questions, and that's what a program is you pre-storing your response to the what next question over and over again. So here's a couple of videos that you can look at on YouTube about a CPU. These CPUs, and it looks very much like this CPU that I've got with me, these CPUs have extremely high heat. When you put this thing, or your computer, on your lap and it starts to heat up, that means it's thinking really, really hard. And so this is a small little old video from a long time ago that shows what happens when you take out the cooling capability of microprocessors and just how hot they can be. And the other video that I have is a hard disk, something like this hard disk that I have, except that it works and they turn the power on. Some of them last for a few seconds, some of them last for a few minutes. It's never I must be allergic to this hard drive. Or maybe it's because there's dust in this hard drive and I keep spinning it and I sneeze. But basically, some of them last for a few seconds, some of them last for a few minutes. It's not a good idea to open them up, but I'm glad somebody opened it up and then did what they did and then recorded it so we can all enjoy what it is that they're capable of doing. Okay? So that's a quick introduction to hardware, mostly so that I can use those words going forward. Now what we're going to talk about next is communicating in the language Python. That is, writing code and putting it into. Welcome to my video that shows how to get started and install Python on Microsoft Windows. Okay, so it's not too hard. We're going to both install Python 3 and we're going to install text editor. And so I'm just going to go into Google and I'm going to say install Python 3. And my top link is downloading Python. And there is my link for downloading Python 3.5.2. This version of my class uses Python 3. I have an earlier class that you may have seen that uses Python 2, but in this class we're going to do this. Now it might take you a while to download this. I've actually already downloaded it. Now the other thing we need is a programmer text editor. And you can really use any programmer text editor. We've used Notepad+ in the past. We've used JEdit in the past. I like Atom, Atom.io, Tom.io, mostly because it works the same on Windows and Mac and Linux. But you can really use any text editor that you like. Just don't use Word or text edit that comes with the operating system. You need a programming editor that doesn't mess with weird characters or weird lines or strange formats. You must have a real programmer editor. So I've already downloaded this as well. And so I won't waste the time waiting to download it, but let's go ahead and do the installation. So these things ended up in my downloads file. So I'll go to downloads and I'll start installing Python 3.5.2. Now it's going to ask me some things. Add Python 3.5 to the path. Yeah, that's a good idea. Install the launcher for all users. I'm going to add that. Maybe you will, maybe you won't do that. It's going to tell me where it's going to install it. Install now. Of course, it's going to ask me for permission to do these things. And now it's running through the installation. Okay, so there we go. You could maybe click on this online tutorial and documentation, but we're just going to close this. And I'm going to start and run the Windows command line. Now, you may have all kinds of fancy ways to run Python, but I like running the command line, COMMAND. I like running the command line because it's after a while it's important to know what folder things are being run in. And so here's this command line, and I should be able to type Python here. And so now I'm in Python 3.2, and this is the chevron prompt here is the Python interpreter, where it's asking for Python commands, and I can say print hello world. Of course, this is what we tend to print all the time. I can make a mistake. I can say blah, 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 right? And it'll complain to me. Now to get out of this, I can either type Control-Z or quit. In this case, I'm going to type Control-Z, and I'm back to the prompt. A couple of things. I can do a dir to see what folders and files I have, and that is like my desktop. And then the cd command tells me where I'm at in the folder. That means I'm in the users directory, Dr. Chuck. Okay? So I have now installed Python. I ran the Python interpreter to verify it. I said print hello world. Okay, and so now what I'm going to do is I'm going to actually install Atom. I already had this downloaded, so let's go ahead and install Atom on my computer. Okay, so Atom is now installed and it's kind of telling us what to do. I'm going to actually just close all these windows, close this window, close everything, and I'm going to create a file. I'm going to say print, in this case, let's see if I can make this bigger. I can make it bigger. So I'm going to type print hello from a file. Okay, and I'm going to save this. I'm going to say file, save as. And what I'm going to do is I'm going to go to my desktop and I'm going to make a folder on the desktop. I'm going to call this folder PY4E. So I now have a folder on the desktop. Move this here. I'll move this here. Oops. And I'm going to go into PY4E and then I'm going to name this file first.py. And you'll notice that when I save this, it syntax highlighted it. That's one of the nice things about a programmer editor. Okay, and so it says, oh, it's got a suffix of .py, so therefore it knows that it's supposed to look pretty with Python and make this one color, make this another color. The other thing that you'll notice is that I now have a folder called PY4E. And if I'm in this command line, let me just start that up again. I'll show you how to start the command line again. Command. Now, if I do a dir, I see the folders that I'm in, and one of the folders that you can see here is the desktop folder. So I'm going to say cd desktop, and then I'm going to type the dir command to see what folders are in the desktop. These folders are the same as these folders. These things are kind of virtual folders. PY for E is PY for E. Now I can type CD, which stands for change directory, PY for E. And I can do a dir, and now you see first.py. And that's the same as if I'm diving into this folder. Here's this file, first.py. Windows hides the suffix, which is somewhat annoying and frustrating, but that suffix is there, that file is there. And so for me, one of the things you got to figure out in Windows is how to make sure that you are in the same folder, users, Dr. Chuck, desktop, Pi4E, and that's the name of this file, and here as well. And now I'm going to run this program. I'm going to type Python first.py. And you see that it ran the Python code. Okay? Another way you can do this is you can type first.py. And that's because this file association has happened in Windows. This doesn't work in Macintosh. This only works in Windows. That all files with .py are expected to be Python, and it knows the Python interpreter where to run. Okay? And so I've got Python 3.0 installed, and that gets me started. And so I hope that this little introduction about getting things started and writing your first Python program has been helpful to you. distributed version of Python 3, but there's so many things inside Mac that depend on Python 2. I would expect that it will always be named Python 3, which is what we're going to call it in a second. So here I am with the python.org downloads, and I'm going to download Python 3. Click here. Obviously got it sitting here. Download is ready. Do that. And so I'm going to install this. There is the installer. So continue. Of course I agree. I read all that really fast. And now I'm going to install it. Okay. So now that means if I run a terminal, so of course it's start run terminal. So Python 2 is still there. But Python 3 is also now involved there, so we should have Python 3 installed. So we installed Python 3.6, and so there we go. And that's all it takes to install Python 3 on the Macintosh. So let's write our first little Python program. I'm going to, I like Atom, and so I've got this Atom editor. It's atom.io. Right here, atom.io, download and install the Atom editor. I like it because Atom works the same on both Windows, Mac, and Linux, and it has syntax highlighting, and so I really like things like that. So I'm going to make myself a simple Python program. Hello world, like we always do. Now you'll notice that it's not syntax highlighting yet, but I'm going to do a file, save, oopsie daisy. File, save as, and I'm going to go into my desktop and I'm going to make a folder called py4e. I'm just going to call this hello.py. Oh crud. Got to rename it. I ended up with 2 dots. Hello.py. There we are. And so now I'm here and I'm in my home folder. I can go in my desktop and I can go into that new folder I made, Python for Everybody, and I can see the files. Now there are ways to run this, and I really want you to learn the terminal so that you really know what you're doing. And so here we are in the folder that has the Python, and then all we do to run it is we say Python 3 hello.py, and there we go. And of course this is Python 3 because I'm using parentheses there. So instead of double quotes. But Python 2 is still there, and of course if you just run Python hello.py, it'll be a syntax error, or not. Must be they added something. Yeah, because Python is still version 2, but apparently they allowed print in the latest version of Python 2. So away we go. Okay, so again, thanks for watching. I hope this was helpful to you to get Python 3 installed on your Macintosh. Hello and welcome back to Python as a Language. You'll notice that I'm wearing a hat. Part of the story of the hat is that where I work here at the University of Michigan School of Information, my office is in this building called North Quad, and we call it quadwarts sometimes because it's sort of got a square. It sort of imitates an Oxford quad, and so it seemed to me to evoke notions of Harry Potter. And when we first moved into the building, I joked in one of my classes that we should have a sorting ceremony for all the students as they come into North Quad for the first time, and so that was cool. And I thought that I would belong in Gryffindor, like everyone wants to be in Gryffindor, right? They're the good guys. And my students told me that I couldn't be in Gryffindor, that I had to be in Slytherin. So you'll see me drinking tea throughout the course out of this teacup. It's my Slytherin teacup. I picked that up from Harry Potter World. I went down to Florida and visited Harry Potter World. And the reason that I am was sorted by my students into Slytherin is also because I teach Python. And Python is like a snake. And so if you think about the people from Slytherin, they are capable of talking to snakes. And the class that we were doing the sorting was a Python class, and so it sort of made perfect sense that you would have to be in Slytherin if you were the Python teacher. And of course, your name is Charles Severance, and then that sounds kind of like Severus Snape, and so I just accepted that I'm in Slytherin, okay? So you all can be in Gryffindor, but I can't. I'm in Slytherin. So I'm the bad guy, or the good guy, depends on how you look at it, right? And so what I'm going to do now is I'm going to, bring you into Slytherin as well, because I'm going to teach you the Python language. Python is the language that we Pythonistas talk. It was invented about over 20 years ago by a fellow named Guido van Rossum, and away we go. Now, even though I'm using this whole snake Slytherin thing, it turns out that Python was not at all named for Harry Potter, because Python was invented, almost 2 decades before Harry Potter was created, and it wasn't for the snake. It was actually Monty Python's Flying Circus was the inspiration for Python, the name Python, and because Guido van Rossum really wanted to create a programming language that, while it was powerful underneath it in its very nature, was a very powerful language, he wanted it to be a language that was fun, and he wanted it to be a language that was approachable. And so that's why Python recently has become so absolutely popular. And it's easy to learn, but it's also powerful, and that's sort of the magic of Python, is the ease of learning it, the brevity of the programs, the shortness of the programs, and the power. And so we are going to become Pythonistas. Now, as you learn to be a software developer using the Python programming language, you are going to encounter syntax errors. And I remember when I used to get syntax errors, and I remember my first programming class, and I would type on cards. And I would upload those cards to the computer, and the computer would say, "You're not worthy." And I'm like, wait a sec, those are pretty good cards. How could you be so critical of me? I'd say syntax error. And I really got sort of a really bad attitude that somehow this computer didn't like me, and that I would make cards, it would complain, and I would make changes to the cards, and it would still complain, and I'd make changes, and it would still complain. I'm like, how can I win in this situation? And you're going to feel the same thing. You're going to absolutely feel the same thing. You're going to be struggling. You're going to be like, how come this computer hates me? Let me assure you right now, the computer doesn't hate you. The computer actually loves you. It just is not very good at showing how it loves you, or telling you how or why it loves you. And so syntax errors are not so much Python telling you that you're bad, or that you're an inadequate programmer, or you should find something else to do. It's really Python's admission that it doesn't understand what you're trying to say. And so you got to get used to that. And it's frustrating, but you got to get used to the fact that syntax errors are your friend. Python is saying, hey, I got to line 7, and I was doing fine up to line 7, but boy, in line 7, there's some little thing. I don't know what the word else means in this context, or you didn't indent it, and so I'm kind of confused. What did you mean? Please, please, please help me. And so it's so much easier for you to learn Python than it is for Python to figure out what you mean when you're writing code. So we have a number of different ways to sort of encode our instructions when we talk to Python. One is we just run Python interactively on our computer. Hopefully by now you've got it installed, and you just type Python at a command prompt. So either a Windows command prompt, or a Linux command prompt, or a Macintosh command prompt. And I got some examples of how to sort of get this all started, get Python installed, and away you go. Now you'll notice when you run the Python interpreter, the 3 chevron prompt, Python is asking you what next, right? This is you, it's saying, I want to talk to you, I want you to tell me some Python to do. If you know the Python language, you know what to say right here. Now if you know Python, you can type these languages. You can say, oh, x equals 1, which really means go find a little piece of memory, label it x, and stick 1 in it. Print X is like, go find that thing where you labeled it X and bring me back that number and tell me what I stored in there. Now, why you want to do this, that's a different question. These are very simple things. It's going to take you a while to get the big picture of why we're doing this. So just trust me that you want to learn these statements, and then later we will successfully turn those into a program. So x equals x plus 1, the third line there. X equals x plus 1 is not as it seems in math. It basically says, hey, go grab the old value of x, add 1 to it, and stick it back in x. That's what that means. So an equal sign really has kind of an arrow to it. And then we say, hey, go look up that x thing that we just did and print that out, and then we're going to say quit. So that's us talking to Python. Now, you can type just about any crazy stuff you want in here, and Python will be unhappy and talk to you. So what we're going to do next is we're going to start talking about the actual language of Python and what it is that we have to say to make Python happy when we're talking to it. So now we're going to start learning the actual Python language. So what do we say? You can think of this as almost like writing a story. We're going to start with a basic vocabulary. We're going to talk a little bit about lines or sentences, and then we're going to start talking about how to put those sentences together to make a coherent paragraph, as it were. And you just have to accept the fact that when I start teaching you this stuff, it's not going to make sense for about 6 or 7 more chapters. And so just sort of bear with me, except, I remember when I first learned, it went from me confused, holy mackerel, this is awesome. And so I expect many of you will go through that same thing. So just learn the first parts, accept the fact that it doesn't necessarily make sense in a big picture, and just bear with us, okay? So we'll start with vocabulary, we'll start to make sentences, and then we'll have little short stories and paragraphs, okay? And so this is a short story about how to count the words in Python. It's got a couple of paragraphs, and we are going to look at all of this stuff eventually. So we start with a set of reserved words. And what are reserved words? Well, they're words that Python expects when you use these words that they're going to mean exactly what Python expects to mean. And what it really means is you're not allowed to use them for any other purpose than the purpose that Python wants. It's sort of part of the contract. It's like when you have a dog and you go, what did you think of that television program? And the dog has no idea what you're saying. And then you say, do you want to wait until Saturday to go to the veterinarian? And the dog still doesn't know what you say. And then you go like, how would you like to take a walk? And then the dog goes, walk. I know what that means, and then hits the door, right? And so the way the dog sees you is blah, 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 walk, blah, 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 food, blah, 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 treat, blah, 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 walk. That's kind of how Python looks at these reserved words. When you say class, it goes class. Oh, I know what that means. Now, if I say zap, it's like, oh, zap something that you get to decide, or it's maybe a variable name. So reserved words are simply words that when you use these words in Python, and there's only a few of them, like and or del, or if maybe, pass maybe, in. A lot of these, you won't end up using them. It's just these are reserved for Python and part of the Python vocabulary. This is Python vocabulary. Now, when we move from words to sentences, you see that Python is a series of lines. A Python program is a series of statements. They have an order because the computer wants to know what next, what next, what next. So what next is start at the beginning. So I already talked about an assignment statement that basically says x equals 2. This is not a mathematical statement. This is a directive to say, take this variable 2, this value 2, this constant 2, and stick it in a location in your memory, and remember that I asked you to name it x. X is a variable, something you made up. You chose that. And so, but it's Python's job to remember it. So this says, go to whatever that x is, there's a 2 in there. Now pull that x back out, add 2 to it, which makes it 4, and stick it back in x. And so that makes this a 4. So x is a 4. And print x says, go look up that thing that was an x and print it out. And so these are like Each line has something to it. I'm using a reserved word. Well, actually, that's a function, but it's a reserved word too. And so there's reserved words and all these things, and you combine these. There are operators. Plus is an operator. Equals is an operator. These things do things, and we'll learn all this stuff in time. So the basic building blocks of lines of Python. Now, as we take these lines of Python and build them up, we end up making paragraphs, programming in paragraphs. And so one of the things that it's important is I showed you how to do interactive Python. So you just type Python and you type a statement and a statement and a statement. Those get really tiring after about 3 or 4 lines of Python because you start making mistakes and you have to start over. So the better thing to do is to, as your program gets a little larger, to write a script. Put your Python instructions in a file and then tell Python to read from the file and then run the script as it's entered in that file. We tend to name these files with .py, and I've got a series of videos that you can watch to figure out how this all works. Like I said, you can type interactively to Python, and it's a great way to experiment with Python, check to see if a statement does what you think it does, but script is the way. After we are past 1 or 2 lines of code, we write it in files and then run it separately. So there are a couple of basic patterns, and it's really important to understand each of these patterns. And like I said, we'll teach you these patterns separately, and then we'll combine them together. And when you combine them together is when you say, oh, that's what a program is. So you have to suspend disbelief. We have a couple of different patterns. One is a sequence of steps. Do this, then do this, then do this. Conditional is like skipping something. Repeated does it over and over and over again. Computers are really good at repeating stuff, much better than people. People get tired going over and over doing the same thing. And then we have store and repeated steps as well. And so if we take a look at this, and we take a look at a Python program, this is a piece of code. This is a little script. If you type this into the code, take this code, Python code, into a file and ran it, it starts at the beginning, and then it goes to the next line, and the next line, and the next line. And Python executes the scripts as you write them. So it says stick a variable to find a place called in your memory called x, stick 2 into that. Okay, then go to the next one, print that out. So the program is producing output. Now go read x and add 2 to it and stick it back in x. So x is 4. Then print that. This side over here, this is called a flowchart. I'm not going to draw flowcharts. I'm only going to draw them a few times in ways that I think will help you. But you can think of it as Python, when it finishes something, it goes on to the next one, unless you tell it otherwise. Finishes this, goes on to the next one. Finishes this, goes on to the next one. Finishes this, and now the program is all done. And so that's sequential steps. You just type them in, Python runs it. They're important, but sort of uninteresting, because you can only get so far. And you can't really make them intelligent because it's always going to do the next one. So the next thing we do is what are called conditional steps. And this is where it starts to get intelligent. I mean, where you are able to encode your brain into the computer. Like, oh, wait a sec, let's only do this step if something is true. And the syntax that we tend to use here is the reserved word if. Okay? And so the if is like a fork in the road. You can go one way or you can go another way, and you're asking a question. So inside the if statement, right here, there is a question saying, is x less than 10? That resolves to a true or false. If it's less than 10, that's true. If it's greater than 10, it's false. And so then what we do is, if it's less than 10, we have this indented block of code. There's also this colon that tells us we're in the beginning of an indented block of code. And so what it basically says is, if this is true, run that code. If it's false, skip that code. So it can either run it or skip it, depending on this question that's being asked. Now, if you look at this code, it's pretty obvious what's going on. It comes down, x is 5. If x is less than 10, that's true. So it runs this code and prints out smaller. And then it comes back here, it de-indents the next basic sequential. This ends up being kind of a block. If x is greater than 20, if x is greater than 20, oh, come back. If x is greater than 20, this turns out to be false because x is 5, and so it skips this. So the bigger never comes out, and then it continues on and prints fini. Oops, that's a typographic error, make that a lowercase print, and then prints fini. So it comes in, runs this, skips this, and then finishes. Okay? So here is the last one we'll talk about, the repeated steps. We'll get back to store and retrieve later, but for now we're just going to talk about 3 of the 4. This is another program, and the key is that we're going to use this same choice where we're going to go in, but then we're going to run for a while, and then we'll have an exit condition where we get out. So this is a repeated over and over and over and over again, and this is the essence of how we make computers do things that are seemingly difficult, well, that are more naturally difficult for people, okay? And so how do we encode this notion that we want to do something for not forever, but for a while? How do we encode that notion? And so we do it in this way. So we have our statement, sequentially go to this while. While is a keyword, and it's asking another question that's a true-false question. Is n greater than 0? I read this as long as n remains greater than 0, keep doing this indented block. You have a colon at the end, and then you have 2 lines of code that's indented. So that tells us what the loop is, and then this is now de-indented. And so it comes in, and if this is true, if this is true, it runs these 2 lines. Prints out n is 5, and then it says n equals n minus 1, which makes n be 4, and it goes back up, and it goes up and it asks this question again. Is n greater than 0? If it is, continue on, and prints 4, and then subtracts it, and it does that, 4, 3, 2, and prints out 1, then it comes up, and now after this, n is now 0, and n is no longer greater than 0, so it takes sort of the exit ramp and goes down here. So it takes the exit ramp and goes to here and runs the next line. Now, we're going to cover all this again. So I'm just trying to give you the big picture. Next couple of chapters, we're going to hit all these things again, and we're going to hit them in much more detail with a lot better information. This is now sort of like combining these. And again, I don't want you to really like know this stuff. You will know this in a couple of weeks. You will see this program again. But this shows you how we combine those patterns of repeated, sequential, and conditional together. And so this is a bit of sequential code. Comes in here, runs this, which happens to ask for a file name. Then it opens the file. It creates a data structure called a dictionary. This is all sequential. Now the for is another form of loops. So this is going to loop for a while. And then this is within a loop. We can even have 2 indents, and that's another loop. So these are like repeated. And then it goes down to the next sequential bit. Then it does this. Here's another loop that's going to run, and then here's a conditional it's going to run. And then when it's all done, we print out the last thing. And this is, of course, is the program that does, it figures out the most common word and prints that most common word out. And so this is a Python short story. It reads some data. It reads the name of a file. It opens that file. It talks about how to make a histogram. And then it looks through for the most common word. So don't worry too much about this. Over the next couple weeks, we'll fill in the pieces so that you absolutely understand every single line of this code. So, this is a quick overview of Chapter 1. Stick with us. You realize it will be Chapter 7 before this makes too much sense. You really have to trust that you are learning important things and that it all makes sense when we bring it together, like in Chapter 7 in a few weeks. Hello, and welcome to Chapter 2. Now we're going to continue to talk about the building blocks of Python, variables, constants, statements, expressions, etc. The first thing we have to talk about is constants. These are just things, we call them constants because they don't change. They're numbers, strings, etc. And we use them to sort of start calculations, or if something is greater than 40 hours, we're going to do something. And so 40 is the constant in that situation. So we have 123, we have 98.6, we have hello world, which is a string by enclosing it in quotes. We pass each of these things to the print function, and a side effect of the print function is that we see the output. So print 123, prints out 123, print 98.6, prints it out. So these are just really the syntax of constants, and without constants we can't write really much of anything. The other sort of foundational notion of any programming language are the reserved words. And like I said before, reserved words are these special words where Python is listening for them, and there are very special meanings. So when Python sees if, it's not just any other word, it means how Python implements conditional execution. Variables are the third building block, and that is a way that you can ask Python to allocate a piece of memory and then give it a name. And you can put stuff in that. Sometimes you just put one value. Later we'll see when we do collections in chapters 8 and 9, we will see that more than one value can be put into a variable. And the variable, how we control the variable is through the assignment statement. And as I said before, it's important to think of the assignment statement as having an arrow to it. So this is not saying x for all time is the same as 12.2. What it's saying is take 12.2, find a place, find some memory in your computer there, Mr. Python, give it a label x, we get to choose the x. That's the variable part. We chose it, right? And then stick 12 in it. And then the same is true for 14. Go find another spot, name it y, and then put a 14 in there. So think of this as an arrow every time you see that equality, the assignment in an assignment statement. Now, these variables hold one value. So now if we have these three statements, these two, and then the third one executes, it says put 100 into x, but that wipes out the old value of 12.2, and it rewrites it with 100. And so we can change the variables. That's another reason that we call them variable. There are some names, some rules for making variable names. You can start with a letter or an underscore. We tend not to, as normal programmers, use underscore. We tend to reserve those for variables that we use to communicate with Python itself. So when we're making up a variable, we tend not to use underscores as the first character. You can have letters and numbers and underscores after the first character, and they're case sensitive, but it's really a bad idea to use case as the only differentiator. So in this case, spam, eggs, spam 23, and underscore speed are all totally legit. We would probably not use this one unless we were actually doing it because Python told us to use that variable. 23 spam starts with a number, pound sign starts, and dot is not a legitimate variable character. And spam, capital spam, and all cap spam are different, but this is not something that you want to sort of depend on too much. So that's just the rule names. We tend to start them with a letter and then use letters, numbers, and underscores. Underscores other than the first character are generally pretty common, and you'll see those used a lot. Now, when we're choosing variable names, one of the things about variables is we get to choose the name. We get to choose the name x, choose the name y. And so sometimes we like them short, but sometimes we want them descriptive. And the notion of making variables descriptive is often confusing to beginning students. Sometimes it's really helpful to, if you're going to have a line of text and you name the variable line, that's great because the next person reading your program says, oh, that must be the line of text. Whereas it also can become misleading that the name of a variable somehow has meaning. So sometimes we'll have even singular variables and plural variables like friend and friends. And you're like, is plural? Does Python know about singular and plural? And the answer is no. So sometimes we pick variables that make no sense. Sometimes we pick variables that make a lot of sense. This is just something that you as a beginning programmer are going to have to understand, that we can pick anything we want. And so you'll see, I'll try to call attention to this in the first few lectures as we go through. So here's a bit of code with an assignment statement, two assignment statements, a multiplication, and a print statement. And you can say, what is this doing? Now, Python is perfectly happy with this code because it assigns it in there. You have said, please go give me this as a label. And then we assign two variables, and then we're carefully pulling these two variables back out, multiplying them together and sticking them into yet another variable, and then printing that variable out. That seems like, you know, we can figure out what it is. You just have to look really carefully. And a single character mistake in Python is going to be, you know, pretty unhappy. Okay? So that's one way to write this program. It's hard though, because any of those characters are long variables and they're random stuff. It's not very friendly to anyone who might read your program. Now this looks a little friendlier. It's the same program because Python just wants a correspondence. You picked A, you picked B, and you picked C, and it's really much easier for us to see what's going on. And so this is, in a way, going from here to here is much friendlier, but we can be even friendlier if we pick mnemonic variable names. So this is not mnemonic, this is short and convenient, this is long and inconvenient. Python is happy with any of these. Here, on the other hand, is another version of the exact same program. And now you think to yourself, oh, yeah, now I get it. 35 is the number of hours, $12.50 is the rate, and then we're going to multiply the hours and the rate and come up with the pay, and we're putting out the pay. Now, whoever wrote this program is helping us greatly understand what's going on, and that's good. Choosing variable names. Python, again, all three of these are the same to Python. Choosing variable names in a way that help your reader understand what's going on is a great thing. The problem is, the danger is, if you read this and you think that somehow Python understands payroll, that if you name a variable hours, that Python knows what hours means. The answer is Python really doesn't care what you name the variable as long as what you name it, you use it, right? And so you got to be careful. And so you'll see, I will, when I write my code in these first few weeks, first few lectures, I will sometimes write it with gibberish. I'll sometimes write it with extremely short but meaningless variable names. And sometimes I'll use meaningful variable names, and I'll call your attention to it, and it will get you. You'll start, when you look at this third kind, it has meaningful variables or mnemonic variable names, you'll just instinctively want to give Python more intelligence than it sort of deserves. I guess that's probably the best way to say that. So, we've talked about constants, we've talked about reserved words, we talked about variables. And so here we have a sentence, like we've already done some of these things, where we set x equals 2, we retrieve the old value of x and add 2 to it, so that becomes 4, and then we print 4 out. Print is a function that's built in, and we pass in whatever we want to print out. So this parentheses is part of a function call. Okay, so an assignment statement, you have to really get your head around the notion that it has this arrow nature, and that it evaluates this entire right-hand side before we change the left-hand side. And so you can think of this sort of as at time step 1 it does this, and then at time step 2 it does the copy. And that's how you can have something like x on both sides of an assignment statement. And so if, for example, we have x and x has 0.6 in it, what happens is that it sort of ignores this part right here and evaluates the expression. So it pulls the 0.6. Everywhere x appears, it pulls 0.6 out. Then it starts running these calculations, and then it has the new value. After all the calculations are done, then and only then is it going to put that back into x. And so it sort of takes that and puts it back into x, and then wipes out the old value. At this point, this has all been taken care of, and it's been reduced down to this 0.93, and so that is what's put in as the new value. So, up next we'll talk a little bit more about making more complex expressions. So welcome back. We're now going to talk about expressions. Expressions are a little more complex calculations that we can sort of do on the right-hand side of an assignment statement. So one of the things about expressions is operators. And the operators in computer programming are often very much the same as the mathematical operators, but we don't have all the fancy characters that we have in mathematics, and so we have to choose what's on the keyboard. And then we really go back to the 1960s and 1970s, and we used what was on the keyboard in the 1960s and the 1970s to make these operators. So plus is addition, minus is subtraction. We don't have a times sign or a dot in the middle, so we use the asterisk as multiplication. Division, we can't put two things over top of each other, so we use slash for division. Raising to the power, because it didn't have little characters back then, is star star, which is raising to the power. And then remainder. Remainder is when you do integer division, it's also called the modulo operator, it's the remainder, not the quotient. And I've got a picture of that coming up. So here's a whole series of little examples of this. Right? So we've already seen, the plus, x equals x plus 1. Keep remembering that these assignments are arrows, basically. Arrow, arrow, they have a direction. Multiplication, 440 times 12. Dividing this by, that's division, over 1,000, 5.28. Here we're going to put 23 into JJ, and then we're going to do modulo. So that says, take 23, divide it by 5, and give me back the remainder and put it in KK. So this is the expression that evaluates like this. Take 23, divide 5 into 23, 4, remainder 3. The 3 is what comes back up here. Okay, and so that is the remainder. It's also called modulo operator. It turns out that for things like picking a random number and then taking the modulo of 52 as a way to pick a card randomly. So this modulo operator is actually, especially in games and other things, super useful. So that's the various operators. It's important to know which of these operators goes first. That's called operator precedence. Now normally we put parentheses in, like, so if I put the parentheses in here, I'd say this goes first, parenthesis, then this goes first. Oh, actually not that one. Oops, got that one wrong. This happens first, this happens, then this happens. Okay, and so, but it's important for us to be able to know, if there were no parentheses, the order in which these things will happen. So the way things work in terms of operator precedence is parentheses are the most important thing, followed by raising to the power, all else being equal. Multiplication and division are all both equal, and then addition, and then within it's adding left to right. So let's see an example of how this works. And so if we take 1 plus 2 to raise to the 3 power divided by 4 times 5, and we print out what comes out of this. So the way I did this when I was taking exams back many years ago when I was first in computer science is I'd write it all down and I'd look for the highest precedence thing. Now parentheses would make this easy, but exponentiation is the first one. So that means we're going to take this, and that's going to be 8. 2 to the 3rd power, 2 times 2 times 2, 2 cubed is 8. Then what I would do is I rewrite the whole thing with the 8 there. And now I look across and I'm looking for multiplications because the power's been done. The multiplication is what I'm looking for next. And then there is both multiplication and division. They're equal. They're at the same level. So what happens is they're done left to right. 8 divided by 4 happens before 4 times 5. And so the fact that it's not 4 times 5 but instead 8 times 4 is because of the left to right rule. So then this gets rewritten to be 2. 1 plus 2 times 5. And this one, multiplication, is the top one. So that does this next. 2 times 5 becomes 10. I rewrite it again. And then 1 plus 10, addition, is the lowest thing. And that's how we end up with 11. And so that's how I would do these problems if I ever saw the problem on an exam. And it's a fun problem to put on exams because there is one and only one answer, and every programming class has usually at least one slide about this stuff. So like I said, the rules go top to bottom, parentheses, power, multiplication, addition, and then left to right within it. So we talked about variables and computing values to put inside variables, but the one thing you kind of also, maybe you noticed it as we go by, is we have different kinds of data. We call it type. Is this of type integer? Is this of type floating point number? Is it of type string? What is going on here? And Python is pretty smart about various kinds of types of data. And so, we're adding 1 plus 4 here, and Python knows as it looks at this that that's an integer and that's an integer, and we'll add it together and make it an integer. So that thing is an integer. We can also use this plus to concatenate 2 strings. This is hello blank plus there, and plus looks here, says, oh, that's a string and that's a string. So I know what to do with strings. I will concatenate those 2 things together so it becomes another string that gets assigned into EE, and it's hello space there. The plus doesn't add the space. I added the space by putting it right there. And so these operators are kind of smart in that they kind of know what they're dealing with, and sometimes they will do one thing or another depending on the kinds of values, variables, or constants that they're working with. And so sometimes type can get us in trouble. So here we have EEE, which is hello there because we've concatenated these 2 strings together. And now we're adding 1. And the problem now is that it looks on one side and says that's a string and that's a number, and says I don't know how to do that. This is another one of those annoying errors that you think that somehow Python doesn't like you, but it just is confused. If you look at these things, traceback. Traceback always means I quit. It means I stopped, I ran, I'm quitting now because I don't want to go any farther because I've become confused. So your program stops running and you say, here's where I stopped running. Because we're typing interactively, it's always line 1 here. Type it, but if you read carefully and you don't get too stuck on too much stuff, line 1 that tells us something in module type error, can't convert int object to stir implicitly. So that's an integer right there, and that's a string, and that's what it's complaining about, that little bit right there. If Python is so grumpy about types then we should be able to ask it about type. So there turns out that there is, inside Python, a built-in function called type, T-Y-P-E. So we can pass into type. So the syntax is calling a built-in function named type. Parenthesis is the parameter that we're passing to it. We're saying, hey, hello, tell me something about the type of the variable E. And so this is a function. The parentheses are part of the function call. And it says, oh, that would be of class string. And then we can pass in a constant and says, hey, what about hello? The string hello, it's like, oh, that's a string too. What about a 1? Well, that's an integer. And so we are asking Python through the type function what the type of either a variable or a constant is. And there are even several types of numbers, and we'll even see Booleans and others later. Like 1 with no decimal, that's an integer number. 98.6 with a decimal, that's a floating point number. And so, constants can be both integer and floating point. And I'm just asking over and over and over again, what is the type of what's in XXX, what's the type of what's in temp, and what's the type of the constant 1, and what's the type of 1.0. You can also use a set of built-in functions like float and int to convert from one to another. And so this basically says, I want to convert, let's go back. I want to convert 99 to a floating point number. So this is a function and it's participating in this plus, but before it can finish the plus, it turns this into a 99.0. The difference between 99 as an integer and 99.0 is that it's a floating point number. And that actually turns this computation, as it looks to the left and looks to the right, says, oh, I've got a floating point number on one side and integer on the other side, and so I'm going to make my calculation overall be a floating point calculation. I can also pass into the float function. I can say, take this variable I, which has a 42, also an integer, and then give me back a floating point. So that'll be 42.0. Pass that into F. We print it out, and it is indeed 42.0, and it's a float. And so it knows the type and value in any variable. This is an integer, a value 42. This is a float, a value 42.0. Integer division in Python 2 was kind of weird, and it was actually one of the big things that they changed between Python 2 and Python 3. This is a Python 3 course, so we're not worried about that too much. What's nice about integer division in Python 3 is it always produces a floating point result. And that means that Python 3's division is more predictable and it works more like a calculator. So in this case, I mean, you can go back and look at my Python 2 lectures and see how crazy it was in Python 2. 10 divided by 2 is 5.0. And the weird thing here is these are both integers, but the division forces the result of the calculation to be a floating point number. And this, 10 over 2 could be 5, but 9 over 2 is 4.5. And so that is accurate. In old Python 2, that would give us back 4, which is completely unpredictable and weird. The same with 99 over 100. As you would expect, if this were a calculator, you get 0.99. Actually, what you get in Python 2 is 0, because it would round it down. It doesn't round at all, it truncates it. So 99 over 100 is 0.99, and then it truncates it to 0. That's Python 2. We're not talking about Python 2. There's a good reason we're not talking about Python 2. Welcome to Python 3. Of course, if there are a floating point on either side, the result is still a floating point, and the result is still a floating point. So integer division produces a floating result in Python 3.0, not in Python 2.0. That is an improvement in Python 3.0. And that's why we're recording these lectures. I have a whole great set of lectures about Python 2, and now I'm going to have a great set of lectures about Python 3. Welcome to Python 3. Okay, so we've been talking about converting from integer to floating point, but you can also convert from string to integer or string to floating point. And so here we start out with a little string value. Now it only works for strings that are made of digits. So quote 1, 2, 3 quote is not an integer. It is a 3-character string that has 1, 2, 3 as the characters in that string, which is very different than 123. We say, what is the type of this? It's a string. We say, let's add 1 to it. And it says can't convert into string, so that blows up, right? Because this is a string. It looks to both sides. String plus an integer, not good, okay? But we can convert this. We can call the int function, which is like the float function, and pass a string in. So it says, hey, take this and turn it into an integer. So take the input of sval, which is the string 1, 2, 3, and give me back an integer representation of that, which is going to be 123. So we say, what kind of thing do we get back? Well, we got back an integer. We can now add 1 to it and get 124. And so you have to manage the type of things, and you can convert from one type to another. Now, int is not magic. If you send something into it, a string that doesn't consist of digits, then you're going to end up with another error. Invalid literal for integer with base 10, blah, 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 blah. So it's really complaining. It says, I want these to be numbers here, and you just gave me letters, so that's going to cause this to fail. Another thing that we're going to do with variables is, just like the print function takes something, a list of things, in this case, a string, comma, a variable, and then prints some output in the program, the opposite of that is input. Actually, input generally happens before output. Input is a built-in function, and we pass to it a prompt, a string of text that's going to be printed out for the user, and then it stops and waits. So it says, who are you? And then right here it just sits, waiting for us to type something. So we type blah, 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 and then hit the enter key. Right? We hit the enter key, and then this text ends up in this variable. So this is an assignment statement that Chuck is the result of the input call, gets copied into the NAM variable. So let's do that again. It's evaluating an assignment statement. Remember, it's kind of this way, or you can think of it as just do this right side first. It writes this out, writes that out, then it waits, wait, until we hit the enter, and takes this Chuck, and that becomes the result of this input, which is then assigned into NAM. Now then we go sequentially to the next line. It prints out welcome, comma, contents of the variable NAM. Now this one, this comma here, actually does put the space in here automatically. So it says welcome space Chuck. So it pulls there's no space in Chuck, just the CHUCK. And so print can take more than one thing separated by commas. As a matter of fact, print can have you know, a whole bunch. Oops, come back. Print can have comma, 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 parentheses, as many as you like. Everything you've seen up to now is kind of one thing in the print, but that doesn't mean that print only can do one thing. So I've talked about variables, we talked about constants, we talked about input, we talked about output, and now it is time to write our first meaningful program. And so this program has to do with those of you who have traveled internationally. If you traveled to the United States and you traveled outside the United States, you notice that there is an elevator convention that is different inside the United States. In the United States, walk in the ground floor in the elevator, that's 1. And if you walk in the ground floor in Europe or many other places in the world, in the elevator is 0. So we have written a small app that we're going to put on the App Store and get wealthy with called Elevator Floor Conversion App. And it's going to ask us, we're in Europe and we're lost, and you say, well, what floor would this be if I was in the United States of America? And so we have to read the floor that we are in Europe, and then we're going to convert it to a US floor, and then we're going to print it out. This is very silly, but it is a pure essential program that has input, does some kind of task on that input, and then produces some output, which is useful for some value of useful. Okay? So let's take a look at how we combine everything that we've learned in this lecture: input, processing, and output. It's a 3-line program, but it's sort of the beginning of something that programs do. Okay, you're going to do lots of programs that do this. So here we go. Program starts. We do the input side effect. It prints out this and then waits. We type in 0. That comes back here. And the 0, which is a string. Input gives you back a string. It doesn't give you back a number. It was a little different in Python 2, but in Python 3, input gives you a string. So quote 0 quote, which is what we typed here. We didn't type the quotes, it's a string, gets stored in the imp variable. Then we move to the next statement, and on this right-hand side, we convert that string variable to an integer, so that becomes the integer 0. We add 1 to it, and then that becomes 1, and then we assign that into USF. I've named this variable United States floor, right? So imp is the input and USF, that's mnemonic. It doesn't know anything about elevators, it's just I picked a variable that was quite friendly. And so at this point, USF has the United States floor that's equivalent to the European floor, and then I just fall down and I do a print statement. Print out US floor, comma, that's this space right here, and then whatever the contents of the US floor variable is. And you could see that I could write this on 4, and it would say 3. I could write this and say 7, and it would say 6. This is an amazing program. It converts floors in a European numbering scheme. Wait, actually no, I got that wrong. Hang on, let me clear this. I wasn't thinking clearly. I could type in 4 and it would give me back 5. I could type in 6 and it would give me back 7. See, I'm confused. Haven't been in Europe in a couple of months, and so I forgot all about the floors. But that's the idea. Now, this is a super simple program, not super useful, but you get the idea that we're going to pull some data in, we're going to do some intelligent thing. Soon this will be hundreds of lines of code instead of one line of code, and then we're going to present the results to our user. Now, another element of most any programming language is what's called a comment. A comment is a way for you to put in a program file some text that's to be ignored by Python or C or whatever language we happen to be using. In Python, comments start with a pound sign. So what you can do is put a pound sign anywhere in a line, and then after the pound sign, Python ignores everything after that pound sign. It can be the first character. So here's our recurring concept that we talk a lot about. We're not going to cover this. Remember what this does. This is counting how many letters. There's 16 thes, and there's in that file there was 6 2s or whatever it was. This is that code. We'll get back to this code. But what we've done here is I've added some comments that are really for human consumption. So this first paragraph is get the name of the file and open it. The second paragraph is count the word frequency. You know, maybe I should have said histogram here. Count the word frequency and assemble a histogram. And then here I'm putting this pound sign in, find the most common word, and then I'm all done. I print the stuff out, right? And so all I'm saying is comments are for people to read. Your next programmer or the person who's going to change your program after you're done with it. And they're nice, and you don't have to use any particularly weird syntax or variable naming conventions. You put a pound sign in and you can write anything you want from that point forward. Okay, so we've talked a little bit about variables and types and mnemonics and how we would choose variable names and how expressions work and the various operators, converting between different types, printing, input, output, and comments. So that just kind of gets us sentences. And coming up next, we'll talk about conditional execution, where we're really starting to move up to paragraphs. So see you in a bit. Hello and welcome to Chapter 3, Conditional Execution. In conditional execution, we meet the if statement. The if statement is where Python can go one way or another way, and it's the beginning of sort of our way of making Python make decisions for us. Sequential code, we just do some things. Sometimes that's useful, but now we can have our code check something and then make a decision based on that thing. So the conditional steps in Python are pretty straightforward. The keyword that we're going to use is the if statement. And so if is a reserved word, and the if statement has as part of it a question that it asks, and this is asking if x is less than 10. And the colon is the end of the if statement, and then we begin an indented block of text. And the way this works in this particular thing is this line is the conditional line. If the question is true, the line executes, and if the question is false, the line is skipped. And you can think of it the way this is, right? X is 5, ask a question, is it 10 or not? These questions do not harm the value of x. If it is, then we run this code, and then we sort of rejoin here, and we test this next if, and if that's true, we do this code, and then we do that. But in this case, it's going to be false because x is not less than 20, so it just continues down here. So if we look at how this works, it runs this line, then it sees this question, it skips that line. So this line does not run, and so smaller prints up and infinity prints out. Okay, and so that's the basic idea of an if statement. And the indentation, when we are done with an if statement, we de-indent back, and there's this little block. This is one sort of if statement, and this is another if statement. And these are the two conditional lines that either run or they don't run, depending on the question, the answer to that question. So we have a number of different comparison operators that we can keywords in the 1940s and 1950s, less than or equal to. So we didn't have fancy math characters, so we just concatenated less than equal to be less than or equal to. It's double equals. The asking, is this equal to? So that's a little tricky. Equal sign is that assignment operator. If I was building a language today from scratch, I would probably make assignment the arrow and the equals question to have an equals. Or I might say, somewhere I would say question equals. But I'm not building this language, so that's not up to me. So this is the question. Double equals is asking the question is greater than or equal, greater than, and not equal. So this is the exclamation point that's sort of like not equal. So that's sort of take a look at some of these and some examples. All of these are going to be clear because of the way x is set. If x is equal to 5, that's the question version. It's true or false. We'll execute that. If x is greater than 4, it's going to execute that. If x is greater than or equal to 5, it's going to execute that. Here's kind of a shorthand where if there's only one line in this block, you can kind of pull it up right on the same line after the equals. If x is less than 6, which it is, true, execute that. Then if x is less than or equal to 5, do that. And if x is not equal to 6, do that. Now, like I said, all these questions have been carefully constructed so that they're true, just to kind of show you the syntax of those comparison operators. Now, you don't just have to have a single line of text in the indented block. And this will be something you're going to get used to. So if we indent more than one line, then the conditional code is actually these 3 lines. So the idea is you have an if statement, you come in, you do an indent, and as long as you stay indented, you stay in that if block. If it's false, it just skips all of those. So the way this is going to execute, x is 5. We print before 5. Is x equal 5? That's the question mark, and that's true. So it's going to run all these, and then come back, and then continue on in the de-indent. So all this stuff is running, right? And then it says x equals 6. Well, that was false, so that skips all of them. So none of these lines of code run. So these actually don't run, and it says afterwards 6. So that's a mistake. Those don't run right there, okay, because x is not equal 6. Okay? So indentation is an essential part of Python. We use indentation in lots of programming languages, often to kind of demarcate blocks, to show where blocks start and stop. But in Python, it's syntactically correct. You can make an error if your indentation is wrong. After an if, you must indent. And you maintain the indent as long as you want to be in that same if block. And then when you're done with the if block, you reduce the indent. In this rule of indenting, comment lines and blank lines are completely ignored. So we're going to tend to like put 4 spaces. 4 spaces ends up being the normal thing that we do, and you'll see all the code that I write has 4 spaces for each indent. If I go in twice, I use 8 spaces. And we have this instinct of wanting to hit the tab key to move in 4 spaces. Now the problem is that it might look the same on your screen. A tab and 4 spaces might line up the same place depending on how tabs are set. But Python can get confused by that. So we tend to avoid using actual tabs in files. And so most programming text editors, like if you're using Notepad or Text Wrangler, there's a place to set the tabs to say, don't put tabs in this document, but every time you hit a tab, move over 4 spaces. And so you hit a tab, but it's like space, 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 space. Now the nice thing about Atom, and this is the text editor we tend to recommend in this class, because it works on Windows, Linux, and Mac, but also because it automatically sets this up. As soon as you save your file with a .py extension, you can sort of hit the tab key with impunity, and everything works perfectly. But the key thing here is that Python insists that you get this right, and if you don't get this right, you're going to get indentation errors, and they're just another syntax error. So if you're using something like Text Wrangler or Notepad, hunt around in the preferences and you'll find something about expanding tabs, or maybe how many spaces each tab stop is supposed to be. And so you check these, and what this really is doing is telling your text editor never put an actual tab in the document, but somehow simulate tab stops using spaces. And so here is a bit of code. It's got a nested block, but it gives you this sense that you have to be very explicit when you're reading Python code of whether the indent is the same between two lines, the same, increased or decreased. And so you've got, and when every time you increase it, you mean something, and every time you decrease it, you mean something, and literally if it stays the same, you mean something as well. And so if we take a look at this, here we have a line, and the next line has the same indent. This is an if with a colon at the end, so we have to increase the indent, and now we're maintaining it. Okay, so these two lines are part of that if, but now we have de-indented. So whether you choose to de-indent this word or whatever, where you do this de-indent affects the scope of how far this if statement lasts, right? It lasts up to, but not including, the line that's de-indented to the same level as the if. Okay, so this is a de-indent. Now we have a blank line, which doesn't matter, and we maintain it. Now we have a for, which we'll learn about in the next chapter, which is a looping structure. Let's do a for runs this 5 times. It has a colon, and it also expects an indented block. Now we have what's called a nested block, where we have an if and a colon, and we go in some more. So this is like 2 indents, right? So these are 1 indent, and these are 2 indents. And so this is a block within a block. And then we de-indent, so that means this print is not part of the if statement, but is still part of the for statement. And then we de-indent again, and then that means this print is sort of on the same level as that for statement. So if you start thinking about this, you want to be able to start thinking that these blocks are the start of the block with the colon line up to but not including this line that's been de-indented. So the for goes this far, right? The for goes up to but not including the line that's de-indented. The if goes up to but not including the line that's de-indented. So as you do this, you'll sort of mentally start drawing these blocks, and pretty soon you will start constructing them as blocks. And it takes a while, but doesn't take forever. But in Python, unlike other languages, you have this is very important, and it matters, and you can have syntax errors if you get it wrong, because you're really communicating the shape and structure of your code using these indents and de-indents. We already saw a nested indent. This is a nested if, so you can put an if within an if, and you can go as far deep as you want to go, like Russian dolls. And so here we have x equals 42. If it's 1, we indent 1, and then with this next thing we do, these are at the same level of indent, but now we see an if, and it has to indent further. So this is like 2 in, 8 spaces, and then we de-indent back. Actually, we de-indent back 2. And so if you watch this and you take a look at how this works, it runs to here. Oops, back up. Comes in here. The answer is yes, x is greater than 1. Prints this. Is x less than 100? Well, it's 42, so the answer is yes. So it runs this, and then it kind of continues back to there. And you can also think of drawing boxes around this. This is one if box, and then within that if box there is another if box. And again, it's the indent block up to but not including where the de-indent happens. And this here is like 2 backwards de-indents. So it ends 2 blocks. So 2 blocks are ended by where we place this. We could move this in, or we could move this out. We could have it all the way into here, we could have it to here, or here. And where we put that line depends on how the ends of these blocks are going to work out. So one form of that's a 1 branch if that we just saw, but then you can also have what's called a 2 branch if. And the basic idea of a 2 branch if is that you're going to come in, you're going to ask a question, and you're going to go one direction if it's yes, and another direction if it's no. We call this an if then else. It's kind of like a fork in the road. And the way to think about it is, depending on the output of this question, we're going to pick 1 or 2 of these, but if we pick one, the other one's never going to happen. So it's like an either or. We're either going to go one way or we're going to go the other way, but there is no path where we somehow go boot through both of them. That doesn't happen. And the syntax that we use for this is what we call the if then else. And so the first part is normal if with an indent, and then we de-indent, and then this is another reserved word, else, with a colon, and then we re-indent. And so this is really end up being part of a whole block here, and the else is the part, this is the part that runs if it's false, and this is the part that runs if it's true. The first branch of the if, the first indented block is what runs if it's true, and the second indented block is the one that runs if it's false. And so here we go, it just, if x is greater than 2, in this case it's yes, we're going to print bigger, and then we're going to be all done. And so we do 1, and so this one did run, and this one did not run. So basically with an if then else, one of the two branches is going to run, but there's no case in which both branches run. And again, you sort of draw these blocks around these things mentally, and in this one you sort of take from the if, not the else is really part of the block, up to but not including that print, which is back indented, de-indented back to the same level as the if statement. Okay? This Python is actually one of the more elegant languages, even though after a while this indenting, and when you get too far in, it gets a little bit complex, but this is a good way to visualize this with these indents. Coming up next, we're going to talk about some more complex conditional structures. So welcome back. Let's talk a little bit more about some more complex conditional statements that sort of build on this concept of if and if then else. The first thing we're going to look at is the multi-way branch. And so the idea is it's kind of like the if then else where you're going to pick one of two, but now we can pick one of three or one of four or one of five. And it introduces a new concept called the LF. The LF is another reserved word inside Python. And the way it works is it's probably best to look at this here where it checks the first one, and if it's a true, then it runs that, and then it's done. It doesn't check them all. It's not like it sees that there are two logical conditions. It actually checks them, the first one, and how you order these matters, as we'll see in a bit. And so if the first one is true, it runs. If the first one is false and the second one is true, it runs this one and it's done. And if the neither of them are true, it falls through, and there's an else clause that is otherwise, and it runs that. So basically, it's either going to run one and then skip the other two, or it is going to skip one, skip two, and then run this one. But it only runs in this case one of them. But the important thing is it checks these questions in order, and it doesn't check the second question until it finds that the first. It doesn't check the second question until it knows the first question is false. So if the first question is true, you're done. You're done, and you're done with this. You're done with the whole block at that point. So only one of these three is going to execute in that block. So here's sort of some examples of this. If we, for example, have x equals 0, it's going to come down here. X is less than true. That's true. So it runs this code, and then it skips down to that. And so it's like this. Runs that code and then skips to the end. Okay. On the other hand, if it's 5, then this is false, and it skips that, and it checks this. This is true. It runs this code, and then it's done, skips to the end. It goes like false, true, run, end. And then if x is like 20, for example, it runs, false, false, run the else clause, and you're done. So skip, else, run that code, and you're done. So in this case, we ran that, and we didn't run that, and we didn't run that. Again, one of them is going to run. They're checked in order. These questions are checked in order, not out of order. It doesn't look ahead. It just checks in the order that you wrote it. You're the one that wrote that order. And so there's a couple of variations on this multi-way. You can have no else. You can have no else, as in this case, and this just means that it might not run any of them. In this case, x is 5, so it's not less than 2, but then it runs this one. But if x was like 50, for example, if x was 50, then this would be false, then it would skip, and this would still be false, and it would skip, and neither of these two would run. So if you don't have an else, you're not guaranteed that one of them is going to run, because else is like the catch-all. If the other ones are all false, then the else is the one that runs. Similarly, you can have many LFs, but this is where it's really important for you to make sure you know what order they're being taken in. So that I've got, this, if this is true, it runs, it goes all the way to the bottom. If, this was, if it's false, 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 true, it runs this one and it's done. If, on the other hand, it looks at it as false, oops, go back. If it runs false, 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 they're all false, then it runs the else, right? This one has an else, this one didn't have an else. They don't have to have them. The key is you can have more than one of these elifs, okay? So I got a couple little things. I'll let you pause right now and look at, the question is, are there, looking at the 3 lines or 4 lines of code, x equals something. Are there lines of code that will never execute regardless of the value for x? And I'll let you pause and think about it, and then I'll explain it to you. Okay, hopefully you paused and thought about it as long as you like, but so let me now explain it to you. So we come in here, and if x is less than or equal to 2, it's going to run this first thing, and if x is greater than or equal to 2, it's going to run this, and if neither of those are true, then it's going to run this. Well, the weird thing is, all numbers are either less than 2 or greater than or equal to 2. I carefully constructed this to the point where it would never run this line of code. It is either going to run this one or run that one, but it's not going to ever run this one. So that was kind of like a weird dysfunctional one that I constructed. This other one is a little different. If x is less than 2, we do this. If x is less than 20, we do that. If x is less than 10, we do that. And if none of those are true, we do that. Well, the problem here is between these 2 lines. The problem is if something's less than 10, like 6 for example, it's also less than 20. So even though there might be values for which this is true, those also are going to have this true. So for something like 6, it's going to run here, and it's not even going to look at this. That's the point. It doesn't even look at this. And so that's, I mean, I could have made this more sensible if I'd have moved this little block of code up to there. So this is where the order in which you choose your questions, the way you put these elifs together matters, because it doesn't look at all of them. It only looks as long as it can. As long as it sees falses, then it keeps on going to the next one. But as soon as it doesn't see a false, it doesn't continue. So the last conditional structure we'll talk about is the try and except structure. And if you know any other languages like C++ or Java or JavaScript, you're like, whoa, that's kind of an advanced concept. But it turns out in Python, because of Python's propensity to throw tracebacks in situations where you kind of would like to recover, it turns out you kind of have to use it a little more and a little earlier in your programming skill. So the problem is what if there is a line of code and you absolutely know it's going to make a traceback, it's going to blow up, but you don't want to blow up. I mean, I don't want to have code blow up. If you're using my autograder and you see a traceback in my autograder, that's kind of like, I consider that a failure. I could put an error like, hey, you entered blank data, or you didn't enter a number, but a traceback, that just seems like I'm too lazy as a programmer. So we as programmers are supposed to anticipate parts of our code that are going to blow up potentially based on perhaps the user's input, and then do something about it. And that's what the try and except are for. It's you take this little dangerous piece of code that might break and might blow up, and you surround it with a try and says this might blow up, and if it fails, run this code down here. Okay, so that's the try, and if you get an exception, the except is kind of like if you get an exception. And the problem is if you are running code, here's a little bit of code, we put hello Bob in and we convert it to an integer, and we know from past experience that this blows up. Right? You can't take hello Bob and convert it to an integer. It's just going to blow up. The problem is, and here we are, it says, oh, you blew up on line 2. That's great. And I'm not very happy with hello Bob and whatever. But the important thing is your program stops. These other lines, they don't, oops, these other lines, they don't exist. Right? It doesn't go any further. Remember, the traceback is Python is really confused and I don't know what to do next. So Python is just going to be conservative and stop. So Python stops and your program stops. No matter how much error checking you put down here, it doesn't matter because it's gone. It's all gone. And like I said, we take this kind of personally because the code that you write is like you being put into the computer, giving it instructions. And if the code blows up, well, that sort of wipes you out. You're not in the game anymore. You're not able to do anything. So we want to be able to, especially in these situations where we can anticipate that an error that might happen in the normal course of your program's execution might be something that you want to compensate for. And that's what the try and except does. So here's a bit of code for the try and except. And we just have two little bits of straight line code. And so we put a string in here that's hello Bob, and then we're going to convert it to an integer. This is the dangerous code. This code in this case with hello Bob is going to do a traceback. And so we say try, and then we indent the dangerous code, and then we add this little except bit. If it works, the except is ignored. If this blows up, it runs the except. So in this code, it's going to come in, it's going to try this. This is going to blow up. But instead of giving a traceback, it's going to say, oh, I've got an available except. I'm going to run this except code, and then I'm going to continue on. And so that prints out first -1. So because we set this variable ISTER to -1, like a little flag telling us that something went wrong. And then we keep on going, and now we have put in 1, 2, 3, the digits 123, the digits 1, 2, 3, and now it's going to work, but we still have it in a try block, and then this one works, it does not blow up, and then it ignores the except block. So the except block is only triggered when something goes wrong in the code. It is ignored if something doesn't go wrong. So it's like you bought an insurance policy on this line of code, and when things go wrong, your except block springs into action and does whatever it is that you want it to do in the case of an error. Okay, so that's a pretty useful thing. You got to be a little bit careful that you don't overuse it, because if you put more than one line inside the try part and one of the lines blows up, it doesn't come back to the try block. And so in this one here, we have kind of a simple, silly one where we set the string. We're worried about some stuff. Well, the print statement's never going to blow up, so it's a bad idea to put it in try except anyways. Then we do this conversion, and that's the dangerous part. And in this one, it's going to blow up. And so then it's going to go to the except block and then run the except block and then continue. What it doesn't do is somehow go back and finish this. So these lines are gone. So if you look at it like this works. The try starts. Hello. This blows up. It goes to the except. It runs the except, and it continues on. Never runs that code. So it's not like you took out an insurance on the whole block. Any of those lines can blow up in the block, but whichever line blows up, that is the last line that's executing in that block. Okay? So you tend to want, in this particular example, you would probably, the print statement would go out there, and this print statement would come down here, and you would only put in your try block the single line of code that you think might blow up, because you kind of know print statements aren't going to blow up. So this is an example that's a more common real-world example where the user is going to type some data. And it's users that get us in trouble. So our program starts by asking the user to enter a number, and we know that this could be dangerous. So we're going to put the conversion from string to integer in a try block, and we're going to set -1 if that's a failure. And then if it's greater than 0, we'll say nice work, and if it's less than 0, well, not a number. So first time we run this program, out comes enter a number. We type in 42, which is a string. That 42 goes back into roster, runs in here. This runs, it's fine. That becomes a 42 number, so we skip the except block, and ival is greater than 0. We print out nice work, and we skip the else. Okay, so it says nice work. On the other hand, if we run it again, this time, the input says enter a number, and we're silly, we enter the word 40. And then they have an indented block, and then the indented block de-indents, and that's the end of the function. And so there's two statements make up this function. The key thing that you have to understand and get used to is this def part is actually not running any code whatsoever. It's actually remembering the code, and that's what I call the store phase. The def creates a bit of code and records it like a macro, although it's much more complex than a macro, and it names it whatever you chose. You gave it a name. We named this one thing. And so it, as a side effect of Python reading or parsing these 3 lines, it doesn't do anything, but it remembers. These 2 lines are what you would like to run when you invoke thing. So this is the definition of a function, and this is the invoking of the function. But so this doesn't do anything. So there's no output here from that stuff right there. But then what happens is you invoke it. And this thing looks like it's part of Python, but you in effect have extended Python with your def statement. And so when it sees thing, it goes up and runs your code. And so out comes hello fun. And then it comes back and goes to the next line, does print, so print comes out. And then it goes back and like, oh, this is the reuse part, but we get to reuse it. We define it once and we use it twice. Then it runs this code again and then goes to the next line and it's all done. So this little bit came out twice. And of course this is really simple so that I can fit it on a page, but you get the idea that I don't want to repeat. This might be, 15 to 100 lines of code, and I don't want to type those over and over again. So I say, hey, store these in a name that I choose, and then when I invoke them, bring them back and then run them again. Okay? So that's the basic idea. We actually have already been using functions from the beginning. The print is a function, right? Print is a function. Every time we see print, P-R-I-N-T, parenthesis, and then we have some stuff in here, we are calling the print function. This is the syntax with two little parentheses, is the syntax for functions. And so input's a function, type is a function, float's a function, int's a function. All these things are built-in functions that come with Python at the moment that we started. I mean, we installed Python and these came along. And then there's other functions that we define and use, and that's what the def is for. And in effect, we can create new reserved words of our own making that extend the Python language after we define the function. So it's just this bit of reusable code that takes some arguments. We haven't seen any with arguments. There's a little parenthesis, and we'll see how that works in a bit. We define using the def keyword, and then we invoke it. There's the defining phase, which actually doesn't run the code, it just remembers the code, and then there's the invoking phase. You define it once and then invoke it one or more times. Calling the function or invoking the function, we think of those two things as the same thing. Call, invoke, or just the terms we use. Most people would just say call the function, but invoking it is a perhaps more descriptive way to think about it. So here's an example of a function. It is built into Python. It's called the max function. And we can pass some parameters into the max function. So we pass the hello world string. Now, like much of Python, max knows what kind of thing is being passed into it, and it knows that it's looking for the largest character, the lexicographically largest character, and in this case it scans this little, that's inside the max code, it scans through and finds the largest character. So apparently lowercase letters are higher than uppercase letters because in English we get back a W, and so this is what's called the return value. So this is an assignment statement. Let me clear this and start over. So this is an assignment statement, so it has to evaluate this right hand side. And a function call is nothing more than like x plus 1. It's something to evaluate. It runs the function code, passes in this argument, and then this residual value, this is called the return value, we'll look at this in more detail, becomes the result of this little bit in the expression, and there's nothing else. We could have w plus 1 or something. And then the w is what's stored into big. Okay, so we print big, and big is a variable that has the letter w inside of it. And then we ask what is the smallest, and that finds the blank, and so we get a blank to see this. So there's a min function and a max function. Both of these are built in. These are built-in functions. They're always there for us. Okay, so here is another example of the max function, and so we can think of this as invoking or calling this function as this right-hand side is being evaluated. We are passing this variable in, and there's some code in here, and it's going to do some stuff, yada, 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 and then it's going to give us back a bit of stuff. That's its return value, and then that goes up into the big. Right? And so that's how this works. And so this is actually built in. Built in, or burnt in, I guess I can't draw. And so you can think of this as sometime a long time ago, when Python was being first formed, somebody wrote some code, and it's got some stuff in it. It's got a little loop that reads through all the letters. It has to figure out if it's a string or a list, etc., etc., etc. But this is store, except you didn't do the storing because it's already built in, and then this is the reuse, store and reuse. So we build these things into Python. They're already pre-built, as if before the first line of your code executes, way up here, someone put all this code in for you into Python and created a thing called max for you. Now we've been using this already in built-in functions. We've got type conversions. We've got like the float that takes a integer and returns a floating point version of that. And again, this is kind of like an expression. So it's like I want to divide this by 100, but before I do that, I've got to convert it to a float. So it has to sort of do these function calls as it's evaluating the expression. Okay. Sometimes, like here, we just have a prints out the return value. That's what this is. This is the return value. If you just type a function in a parameter, it can be in a constant or it can be a variable. And as we'll see in a second, we'll give you many of these if you like. So you can either just run it or take the result of this. This passes an integer in, converts it to a float, and then puts the float into that. Type tells us what kind of thing that is, and you can use this inside of an expression. And so it's like, what am I going to do first? Oh, I've got to do 2 times this thing. Oh, wait a sec. Pause just briefly for a moment. Call out to some float code. Pass a 3 into it, and then something comes back, the return value, the residual value comes back, and then that participates. In this case, it's going to be 3.0, participates in this 2 times 3.0. Okay? And so 2 times 3.0 then ends up being 6.0, et cetera, et cetera. But you can see as it's like, oh, wait a sec, I got to figure out what this is, call the function, get the return value, and then continue processing this expression. We've also done this with string conversions, partly because, just as an example, the input always returns a string. The input function returns a string. And so, you know, here's this string, could be coming from input, but we'll just take 1, 2, 3. We know that that's a string. It's not the number 123. And if we try to add 1 to it, we get a trace back. Cannot concatenate string and integer. Trace back. But we can't convert that string to an integer. And so int can take like a floating point number or an integer or even a string, and it says, oh, I know what I'm supposed to do with a string. I'm supposed to look at this, interpret these as numbers, and, you know, multiply by 10 and figure out what the hundreds place is and all that stuff. There's a little bit of work to that, and it does it. But then it gives us back an integer, and we say, oh, what is that? That's now the 123, but it is of type int. And now we can add 1 to it and get 124. And as before from this example that we're kind of reusing from a previous chapter, you don't want to try to convert, oops, sad face, sad face, sad face. Don't want to try to convert something that doesn't have digits using int, because it'll say, I don't know what to do, and then your program quits, right? You don't want your program to stop, tracebacks, and you can, of course, deal with that with try and accept, but that's like a previous lecture. Okay. So up next, we're going to talk about building our own functions, not just using the predefined ones. So welcome back. We're going to continue and start talking about building our own functions. So again, we use the def keyword to define a function, and then later we're going to invoke this. And there's a bit to it. We are defining the name of the function. In effect, we're extending Python and creating new predefined things that we can use, except it's our code. It starts with a def keyword, has some optional arguments, which we'll see in a bit. That's what the parenthesis is. And then the name. And the function names follow the same rules as variable names. And then you have an indented block, whatever code you want to do, and then you have a de-indented block, and that sort of defines the essence. The key thing here is this is not calling. It's not invoking, it's not executing, it's remembering, it's storing, it's figuring things out. So here is the output of a program that defines a function but then doesn't use it. So this is a sort of broken function. So here we go. We start x equals 5, print. You don't have to def, you have all the defs at the beginning. The def runs whenever. So, you know, out comes hello. And then we define a function, and this says, oh, you want to make a new thing here. So I'll make a new thing. It's kind of like a variable in a sense. And then it copies this stuff, copies it up there, and says, later you probably are going to want to use this, so I'm going to remember it. So it doesn't do anything there. No output comes out. Then it says print yo, and out comes yo. And then it adds 2 to x, so x is now 7, and then it prints x, and there's no 7. There's 7. These print statements never ran. They never ran. Why? Because we did not invoke them down here. We defined them but didn't invoke them. So let's take a look at how you invoke a function, right? You define it and then you use it. Sometimes you define it once and use it once, but more commonly you define it once and use more than one time. Again, the store and reuse pattern. The def is the store and the invoking is the reuse. So here's just a slightly different version of that last program, and so now it's going to actually invoke it. So x equals 5, print hello, def, so out comes hello. This produces, the def produces no output, right? But because there's a D indent here, that is the entire blob of the code that is part of print lyrics. So it prints out yo, and now we're going to invoke. This is the call. We're going to call the function. Now the function goes up. Let's clear this. So we're down to here. Now this like suspends at this place. It's like remember to come back to here when we're done. Go up, run this code, and then come back, and then continue on. So it like leaves like a breadcrumb of where it's supposed to come back to, and then it runs, and then the print lyrics, of course, produces the 2 lines of output, and yeah, that should probably not have. That day should be up there, and then x equals x plus 2, which makes it 7, and then prints out 7. Okay, so this is the invoke or call the function. Okay, you defined it, and then later you called it. Now, in addition to just call and return and invoking, we can pass parameters in. And the example of the parameter is in the max function, we have to say, this is the thing I want you to find the maximum of, the largest thing. And part of it is in the whole store and reuse pattern, we have a few lines of code, but sometimes we want to do ever so slightly different things in the different invocations. And so we use the arguments to subtly adjust, like finding the maximum is a general thing, but what thing to find the maximum of, that makes a function that's much more useful and reusable in a lot more situations. So arguments are the thing we passed in, and we define for our functions that we're going to build, we, on the def statement, so we say def, greet, name a function, and then this is the arguments, the things that are coming in. Now this lang variable, in a sense, only exists during the life of the function, and it represents sort of a placeholder. It's not a real variable in the same sense. It's a placeholder that refers to how you touch that first parameter that's sitting in there. Okay, and so lang, so lang is our first parameter, whatever it is. We don't need to see this part down here right now. All we know is we're going to make a function, and we're going to take a parameter, and this lang is the placeholder that tells us what that parameter is. Okay, so within the function, we're going to check to see if the language is Spanish. If we are, print hello. Else, if the language is French, print bonjour. Otherwise, print hello. We have a very highly simplified language translation system here. So the def, of course, does nothing except remembers that and defines the concept greet. So that comes down, and now we're going to call it. And that says, go look up the thing that I defined called greet. If you don't put this in, greet is going to give you a traceback. But because you extended and named it greet, so it runs in, it starts, suspends the code here, starts up here, but then lang is now an alias to en. So now we can run if that is yes, else if, I'm getting it all wrong now. Right, so en comes in as lang, we're coming in the code. If it's not es, it's not fr, else it prints hello, and then it comes back to the next line. And then we call it again, and this time es is lang, and so it runs this code and prints hola, and then next time it calls with this, and then it prints bonjour. You get the idea. So this is a placeholder so that on the successive calls or invocation of the function, we can get at whatever the programmer put in as that first parameter. And so we are saying in this definition, we are ready to receive a first parameter. Please call us with a parameter, and then we will be able to do something slightly different for the different values. So this is a reusable bit of function that prints hello in 3 different languages, and then we tell it what language at the moment that we're actually invoking it. So that's putting stuff into the function. Now getting stuff back out is the concept of returning. In the return statement is an executable statement that does two basic things. The first thing that it does is it finishes. Now this is a one-line function, so that's kind of redundant, but when Python goes into the return statement, it doesn't continue on to the next line. It just returns. That is the end of the invocation of that particular function. But even more importantly, it takes as its parameter. You can say return without a parameter, and it will stop the execution of the function, kind of like a break does for a loop. It's kind of a break for a loop. Get out, we're done. Don't run that next line, get out. But it also allows the specification of what you want as the residual value in an expression. So we're doing a print, and then we're saying greet. And what's going to show up here is whatever this function does in its return statement. And so that prints hello. We call it again, and it prints hello again. Okay? And so basically the return statement is I call this the residual value. It's like what shows up here when the function is all done, and it's the string hello. We call the functions that return values fruitful because they produce something, but you don't have to. You can just say return, or you don't even have to have a return statement. It goes to the last line of the function, and it does a return automatically at the last line of the function. So here's a little bit of a rewrite of our little language program. We are going to create a greeting program. We're going to take the language as the first parameter. And instead of just doing a print statement, which is what we did before, this is now more like a function because it takes some input and produces some output as a return rather than just printing. It's a little tacky for a function to print. And so here we return hola, bonjour, and hello based on the right thing. So now we say print greet en, so it runs the code once, lang is en, and then it runs this code, and the residual value is hello, so it says hello Glenn. And similarly, when it runs this code, it passes es in as lang, it runs through, and it runs this statement. If there was more statements, it wouldn't run them as soon as this return runs. That says that this bit right here is now HOLA. So hola Sally. And the same with French. Goes in, runs again, out comes the return statement, and then bonjour Michael. So you see how we can control as we're writing the application, we can control as we're writing the function what the residual value that we want to see in whatever expression is calling us. Sometimes we have returns and sometimes we don't have returns. So if you think of the max code that we talked about before, we can kind of see that somewhere inside that max code there's a return, and that's how it communicates the W back to us. So we pass in as argument hello world, it comes in as a parameter, and it's going to loop through this imp somewhere. It's going to loop over and over into imp, and then at some point it's going to figure something out and tell us what it wants to send back to us is a return statement, and so the W comes back and gets assigned into big. You can have more than one parameter, and there's just an order. The first one and the second one, 3 and 5. So 3 becomes A and 5 becomes B, and away we go. So we just use this to add two numbers, and so 3 plus 5 is 8. So you get as many as you like, and the order matters. And if you do things like you tell it you want parameters and you don't give it to them, then that'll become a traceback, and it'll blow up. You can also talk about optional parameters later. So you don't have to have return values, and that means that you simply don't call a return with a value, and return is always implicitly happening as the last line of the function. So that's kind of the basics of how functions operate, but I don't want you to get too excited about writing functions. Some programming classes are like, gotta write a function, gotta write a function. Functions, to be clear, are a very powerful mechanism. And as we write programs, 150, 200,000, 200 lines of code, 1,000 lines of code, 10,000 lines of code, the concept of a function is really important. We would go crazy if we didn't have functions. But if you're only writing 20 lines of code, forcing yourself to write a function is kind of pointless. So don't worry about maybe the lack of urge to use this. we are calling lots of predefined functions, and we will for the next couple of lectures. There will be a time when you go like, oh, I'm sick and tired of repeating myself. Oh yeah, time to write a function. So that's why we don't push functions prematurely. We just want you to know what they are, use them, and at some moment you'll be like, oh, I want to define one. But don't worry about, it might take a while before you really want to define a function. So that kind of summarizes our lecture on functions. And the keyword that we're going to start using is the while loop. We're also going to use the for later on. And the while loop functions very much like an if statement. The while starts it, and then this is just like an if statement. It's a question that leads to a true or a false answer. And then there's a colon, and then there's an indented block, and then we use the de-indent to determine how long the loop is, and so this print is de-indented, so that indicates the end of the loop. And so at some level, what's going to happen here is it's just going to run, and if this is true, it's going to run this code. And if it's false, it's going to skip the code. In that way, it functions like an if. The place that it doesn't function like an if is after it's run the code once, it goes up and then asks the question again. And so you can think of it going back up kind of to the top of the while loop and then re-asking the question. Like, okay, is this going to run again? And then it's going to do that some number of times, and then it's going to finish. And so that's the loop, that's the iteration. And we're going to make a variable, we're going to construct very carefully a variable that we call the iteration variable, and that's n. And it's a variable that's going to change, and it's our way of running the loop but not running the loop forever. So let's just run this. We come in, n is 5, is n greater than 0? Yes it is, so we're going to run this code. So we're going to run this code, we're going to print out 5, then we're going to subtract 1, and then we're going to go back up and ask the question, is n greater than 0? And the answer is, since it's 4, the answer is yes. So then it runs again. Then it prints out 4, subtracts it again, checks, prints 3, subtracts it again, prints 2, subtracts it again, prints 1, subtracts it again. Now n is 0, and so it comes back up. Is this question has now become false? So it's going to take the exit. So it's going to come down and run this line right here. Then it prints blast off, and we can kind of print out the residual value of n just to sort of prove to ourselves that it ran until n was no longer greater than 0, and then 0 was the final value for n. And we carefully constructed this n equals, oops, go back. We carefully constructed n, we set it to 5, then we carefully subtracted 1 each time through the loop, and then we're using that to control when to exit the loop. And so you can think of this loop as, for now, running 5 times, true, 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 and then false finally. So this question was true for a while, and as long as it was true, the loop ran, and then when it finished, when it turned false, the loop stopped. And so this variable that we construct to control the loop is called the iteration variable, because it tells how many times this loop is going to run over and over, or otherwise known as iterate. So this is a badly constructed loop with an iteration variable that we didn't do very well. And so if we take a look at this, we start out with n5, and then this is greater than 0, so it's true, so it runs it, and then it runs it again, and n is still greater than 0. So you can pretty much see, because we're not changing n, this is going to be true, 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 dot, 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 forever, true forever. And so this is an infinite loop. And it's just going to run until your computer runs out of battery, or you hit the button. This is the kind of thing where you often see your computer spinning like a spinning beach ball, or some other indication that your computer's super busy. It's in some kind of a loop, really tight, and it's running something, and it's using up all of the processing resources of your computer. That's an infinite loop. And so the problem is we did nothing with the iteration variable. Now here's a different loop. And so this one demonstrates a different idea. So in this case, we start out with n is 0, and it comes in here, and is n greater than 0? Question mark, and the answer is false. So it skips it. It doesn't run these lines of code at all. And so this loop doesn't run at all, because it comes in, asks the question, it says no, and then it skips right around it. So never run, never run. And so this actually is, sometimes you write a while loop on purpose like this, not quite as simple as this one, but the idea is this emphasizes that these loops are what we call zero trip. They are not even guaranteed to run once. They're going to run maybe 0 times. And in this respect, it functions exactly like an if statement, right? Meaning the first time through the loop, if it's not true, it's just going to skip right by it. So there's a couple of ways of getting out of loops. In this case, I'm constructing an infinite loop because remember the kind of definition of an infinite loop is if this is going to stay true. Well, true is the constant true. So this is going to run forever. And what it's going to do is it's going to prompt with a little arrow and then let us type and read whatever we type into the variable line. And then if the line is done, we're going to break. Now break is an executable statement, and if you hit the break, it exits the innermost loop out to the place beyond the end of the loop. So when this runs the first time, and we say hello there, line is not done, so it prints it, so it prints out hello there, and then goes up, and then we type in again, we type finished, and so it's not done, so it prints it, so now comes that print statement, and then we type in done, and now this becomes true, and it comes out and runs the code beyond the end of the loop. The key is it doesn't go back. It's like once you've done a break, that loop is done. And so you look at basically, you know, the block that is the loop. So here's kind of the loop block, and then the break goes to the line after the end of the loop block. And you can think of this as sort of like just a hyperspace jump. There is nothing really, this could be literally hundreds of lines with if statements, and you could be running and doing all kinds of stuff and running and doing all these things, you know, and these things could run all kinds of ways, right? The point is as soon as you hit a break statement, however much stuff is down here, however much stuff is up here, it exits to whatever the next line is beyond the end of the loop. Continue is another loop control statement, but it works differently than break. So break says get out of this loop. Continue effectively says stop this iteration. We're done with this iteration. And so continue says go up back to the top of the loop. Oops. Yeah. Go up back to the top of the loop. And so here we read a line. If the first character is a pound sign, line sub 0, if that first character is pound sign, we're going to skip it. And this is a way for us to make like little comments in our typing. And then we print, if the line is done, we get out, and otherwise we print it. And so that's why there is no printout here, because it comes in, runs, oops. It comes in, this is true, and that goes back up. But it comes back and prints out the next one and does another thing. And so the loop continues, whereas the break ends the loop. And so again, the same kind of notion that you're sort of doing all kinds of complexity. Wherever you're at in this loop, you hit continue, and it doesn't go any further. It goes back up and runs the question mark. It asks the question mark. And so, I mean, asks the question, and it might exit the loop in that particular case. But this one here is this is an infinite loop that I've constructed. This is not an infinite loop because at some point the break gets us out of the loop. And so it's an infinite loop with break to escape it. And that's another common way to construct a loop. So these loops that we've been drawing so far, the ones that use while as their keyword, are what are called indefinite loops. And that's because they kind of go for a while, till a break hits or until some value becomes true. I mean, as long as that value remains true. So all the ones we've done so far are easy to look at and know that they look pretty good and they're probably going to finish. But there are sometimes, if they're long and complex and their exit or termination conditions are a little more complex, it's not clear that they're really going to terminate. And so we can use while loops for a lot of things, but for most of our looping, we're going to use what are called definite loops, and that's what we're going to talk about next. So definite loops use the for keyword, and the idea of a definite loop is it's going to loop through some set of things. It might be a set of lines in a file, it might be a set of characters in a string, it might be a set of strings in a list of strings, but whatever it is, it's sort of going to run a finite number of times depending on the thing that it's looping through. And we like this. And it's an easier way to construct it, and we actually don't have to deal with the iteration variable. The for loop includes a mechanism to construct the iteration variable for us. So it's definite loops iterate through the members of a set. So here's a very simple for loop. And so you see the for keyword, and in is also a keyword. And the iteration variable is something we put right here. This I is declared. This I is like an assignment statement. And I is going to take on successive values. So I is going to be 5 the first time through the loop. Then I is going to be 4 the second time through the loop. Third, 2, 1. So I is going to be assigned 5 different times to 5 different values. And then the loop is going to run. It's going to run once with 5, once with 4, once with 3, once with 2, and once with 1. And so this block of code we have contracted, say, execute it 5 times with these values of I. I is that iteration variable. I is the thing changing through each iteration of the loop. Okay? And so that's why this prints out 5, 4, 3, 2, 1, and then when it's done, it finishes it. And so this is a much more direct syntax for looping 5 times and setting an iteration variable. You kind of all combine it into this one thing, right? All into one thing. So it's quite nice. So you don't have to be going through a list of numbers. There's all kinds of things that we can iterate through with for. And by the way, while I'm sitting here, I named my variable friends, because that's a list of strings, and friend, which is the iteration variable. I'm using singular and plural because it helps you read it. Python doesn't understand singular and plural. So just because you say friends doesn't mean Python knows it's a list. Python does know it's a list, but it doesn't know by the name of the variable I've chosen. That's your basic mnemonic variable warning. These are cool variable names, but I don't want you to be confused by them. So you can loop through a variable. So we're going to take this list of 3 strings and stick it in friends. And so friend is going to iterate through that. So the first time through, friend is going to be Joseph. Second time through, it's going to be Glenn. Third time through, it's going to be Sally. And so that just says run this loop, run this code, the indented code, 3 times. Each time the variable friend takes on a successive version of a successive value that's in the friends array. So it says happy birthday Joseph, Glenn, Sally, and then we come out of the loop and we print done. So if we try to draw a picture of what this is really doing, the for loop is actually doing a whole bunch of stuff that we would have to do with maybe separate statements in the while loop. First, it decides how many times to run the loop, so it's answering the done question, which way do we go? And it is also then moving I ahead. It's managing the iteration variable. If you go back to it's initializing it too. If you go back to the while loop, we had n equals 0, while n greater than 0, n equals n minus 1. So we had like 3 lines to control the loop to manage the iteration variable. But with a for loop, we don't have to do that. And so that's all taken care of. And so that basically says, you know, the for loop, by you using a for loop, are we done? No, we have 5 things to work. Well, set out of the first one, run it. We're not done because we got one more. Set it to the second one, third one, fourth one, fifth one, and now we're done. And that is all handled in a single line of code that includes the iteration variable and the set of things through which we are going to iterate through. I really like the word in. It is mathematically, it reminds me of the set theory where you say this is a member of this set, or the for each. Math isn't important here, but if you do know math, the vertical bar means such that, right, is a member of this set, and that kind of stuff, member of this set. I'll erase the math stuff so we don't over math. But it's like, for each of the values in the set 5, 4, 3, 2, 1, run this loop setting the iteration variable I to the members of that set. So in reminds me, for those of us who are math oriented, in reminds me of a really nice concept in mathematics. Okay? Now, you could think of this as sort of this looping structure where the for loop, and this is pretty much how it actually runs inside the computer, right? Where it initializes it, it runs this thing 5 times, and then executes. That's one way to think about it. But you could also think about it in a somewhat more abstract way, and think of it as all we're really doing is we have a contract with Python that says we're supposed to run this code 5 times, and I is supposed to be 5, 4, 3, 2, and 1. So you could imagine this might be what's going on. The for loop sets I to 5, runs our code. The for loop sets I to 4, runs our code. The for loop sets I to 3, runs our code. The for loop sets I to 2, runs our code. For loop sets I to 1, and runs our code. All we know is our code was ran 5 times, and by contract, each successive time, we're get a different value for I, and the value for I is taken from this set. And so this is just one way to think about it, to say to yourself, oh yeah, this is one way to think about it as it's actually, and this is how it really works. But this is also kind of logically the contract that Python is making for us. So up next, we're going to talk about taking this notion of doing something to a lot of items, but accomplishing something with that, and I call these loop idioms. So now we're going to talk about loop idioms, and loop idioms are patterns that have to do with how we construct loops. We have the mechanics of fors and whiles, but ultimately we want to get something done. We want to solve a problem with a loop. And often what we have to do is, if we have a set of things, whether it's lines or strings or characters or numbers, we're looking for something like the largest or the smallest, or we want to add them up or something like that. And so we can't just say add them up. We have to say go through each one and do something to each one and somehow achieve adding them up. And the pattern that we're going to follow is we're going to have this loop that's going to do run once for each thing, right, in some chunk of data. And then, but we're going to set something at the beginning, and then we're going to do something to each one, and at the end we're going to kind of get the payoff. We're going to get the result. So if we're doing sort of summing things, we're going to have a running total, and so this will be like t equals 0, and then this will be t equals t plus the thing value. And then, but this is not the real total, it's the running total during the loop, but at the end it is the real total. And so we're gonna look at what you do at before the loop starts, during the loop, and then what you get after the loop and how you can use that. So we're going to use this loop. It's just going to loop through a set of 6 numbers over and over and over again, right? So we're going to do something before the loop, we're going to do something after the loop, and then we're going to run the loop some number of times. And in this case, thing is our iteration variable because I'm using unmnemonic variables now. So it's going to run 9, 41, 12, 3, 74, and 15. So it's going to run and print these things out. So it runs this loop 6 times, and away we go. Now this loop does nothing except print stuff out. Of course, I like to do that first, is always print things out to make sure that sort of my brain is functioning. So to kind of understand how these loops work, I'm going to ask you to function as a program. And I'm going to show you some numbers in succession, and I want you to mentally figure out what the largest number is, but more importantly, think about how your brain is solving this problem of what is the largest number, given that I'm only going to show them to you one at a time for a little while, and your brain has to do something. And imagine I was going to show you thousands of numbers. I'm not, but imagine I was. How would you organize yourself in a way so that for like an hour and a half you could sit here as I showed you numbers and you keep track of the largest number that you've seen of all the numbers? Okay, so here we go. Here's your first number, second number, third number, fourth number, fifth number, sixth and last number. What was the largest number? What was it? Well, it wasn't too hard. It was 74. But that's not the question. How did your brain arrive at 74? So here's all the numbers. If I'd shown you all the numbers and asked you what's the largest number, your eyes would have sort of gone, and then you got to 74. And you wouldn't do it in any particular order. Your eyes would just like see the 74 and it would just throw smaller numbers away, and it would move really quickly to what the answer is. Even if there was several hundred numbers on the screen, your mind would sort of move fluidly wherever it felt like moving and then arrive at it. And probably what it would do is it would do something like, kind of move like this, find this, and then sort of check to make sure that it's okay, and then say like, okay, I got 74, I'm done. That's not how computers do it. That is not how computers into smallest. And so we see a 9, and the smallest so far is 9, which is the first value. And again, we're assuming we don't know what the first value is before the loop starts, so we use the first iteration through the loop as the moment where we capture that. Okay? So, smallest is the value, and then we print it, and we go back up, and now it runs again with 41. 41 is not none. There's only one thing that's none, so it is not equal to none. Smallest is not equal to none, or is not none. So this is false, so it skips over here. Then it asks the question, is the value we're looking at 41 less than smallest? Well, smallest is 9 in this case, and this is 41, so that's false, so it skips that and goes on. So we see 41, we don't take it, and then you can see that this will never become true again. This is pretty much false for the rest of the iterations of the loop. It's false for the rest of the iterations for the loop. So it just is going to run down here and ask this question. And at some point we see a 3, and we run this code, we capture it. We see 74, we don't capture it. We see 15, we don't capture it. So then the for loop skips out, and at the end we have the smallest. And actually this would be a good technique for the largest as well, because it really is just a technique to put a marker in this variable so that we snag that first number or first whatever as we read and parse through them. So the is and is not operators are very useful in Python. You can think of them as like the double equal sign. They're asking a question, and they're asking a question, and they return a true or blank is blank, returns a true or a false. It is stronger. Double equal says, are these things equal in type and value? So just as an example, if I were to say, is 0 equal to 0.0, it would say, yeah, that's true. But then if I says 0 is 0.0, that would be false. So that's because these two are the same value-wise, and these two are not the same type-wise. So is stronger than equals, meaning that it demands equality in both the type of the variable and the value of the variable, and no conversion is done. And so that's just a very strong. Don't overuse is. If you're dealing with numbers or even strings, use double equals, don't use is, because sometimes it gets a little confusing. So use is sparingly. I tend to only use is on Booleans and on none types. I don't use is on integers, and I don't use is on floats, and I don't use is on strings. Just none or true false. And also is not is also an operator. So you just say blah 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 is not none, or blah 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 is not false. Okay, so we've been looping around and doing loops and loops of loops. We looked at the indefinite loops, the while loops that kind of run for a while. The definite loop, and we looked at break and continue as a way to either escape completely from the loop or go back up and discard the current iteration of the loop. We looked at none. We looked at Boolean variables. We have for loops, definite loops, where you've got some kind of a set or a list or some kind of sequence that you're looping through. And then the concept of loop idioms, where you do something at the top, something to each item, and then you sort of get a benefit at the bottom. And so that gets us through iterations. Hello and welcome to Chapter 6. In this chapter we're going to talk about strings. And Chapter 7 is the payoff chapter, so we, up to this point we're still learning sort of basic building blocks, and actually we're going to write a real program in Chapter 7. So just learn this, and the payoff's in Chapter 7. So we actually been using strings from the very first lecture, because if you print hello world, well, that's a string. And so we've been doing things. This slide here is all review. We use plus to concatenate strings. We use print to print them out. Print's just a function that takes as a parameter something, strings, integers, etc. We can put digits in strings, but we can't add to them. By now you figured this out, but you can use things like ints to convert the strings to integers and then print things out. So, you know, we've been doing this for a while. We've been talking about strings all along. Now today, what we're going to do is going to just get into strings in more detail. We input data with the input function. Input returns us a string. And if we want to input a number, we have to run some kind of conversion, like we have to do on int before we take this data that we read from input, you know. And so there's things that we've got to do, and we've been doing all these things in programs so far. But if we look in a little more detail inside strings, we can index within strings each character. So each character has a separate position and a separate index, and they basically, the letters have positions, and the positions start at 0, and the best way I explain this to remember this is it's the elevators, as we used in one of our examples a long time ago. Elevators in Europe start at 0, and so strings start at 0 as well. Turns out in the old days there's some efficiency with the notion of lists of things starting with 0. These days the efficiency isn't the issue, but there's a certain elegance starting at 0, even though intellectually you might think 1 would be the first character in the string. Might make most sense to be sub 1, but it's not, it's sub 0. But just remember that. And so we have this operator called the index operator, and it's square brackets. So, you know, fruit is a variable that contains the string banana, and then fruit sub 1 is the character that's in position 1. Now that actually is the second character. I'll keep reminding you until I get tired of reminding you. So that assigns A, the letter A, into, the letter A into the variable letter. Of course, that's a badly chosen. It's either a well-chosen variable name or a badly chosen variable name. And the thing that goes inside this can either be a constant or it can be an expression. So this is x equals 3, and then fruit sub x minus 1, well that means 2, which is position 2, which is an n, and so that gives us an n. So the index is an operator, and you can add this bracket syntax to the end of a string variable. You can't index beyond the length of the string, so if I say zot sub 5, well, there's only 3 characters, which means 0, 1, 2, but sub 5 doesn't work, and of course we get a happy little trace back. So you have to be careful when you're starting to pull stuff out of strings, although some of the things allow it, some of them don't, and then you'll kind of get used to that. We can ask how long a string is. And so we use the len function. We pass the string variable, and we pass it into len as parameter, and len gives us back the length of the string, not the position. So it's 0 through len minus 1. So it's 0 through length minus 1. So length is just another function that we've been doing functions now for a while. You pass in a parameter, and then len does some work, and out comes 6, and that goes back into x because the function has a residual value. It just happens to be a built-in function. And so, you know, somewhere deep inside Python there is code that takes this, and somebody wrote a loop or looked something up and then returned a return value and sent back a 6 to go into our x variable. And so a function is there, and like I said, we've been using this for a while. Another thing we tend to do is to look through strings and look at strings and dig data out of strings. Python is excellent for doing sort of these kinds of lookups. And so we can write a simple loop. We can write a for loop that creates some kind of a iteration variable like index. And given that we know that these positions are 0 through 5, we can set this to be 0. And then write a while loop while the iteration variable is less than the length of fruit. And remember, this is 6, so it's going to be 0 through 5. 0 through 5 are the values we want to generate. And then we can look up one at a time, pull out fruit sub index, so fruit sub 0, fruit sub 1, 2, 3, 4, 5, and then print out the position and the letter index, and then add 1 to index, and it runs. This will run 6 times, 0 through 5, and out we go to produce this output right here. And so that's one way of looping through strings. That is a basic Indeterminate loop, but we construct carefully an iteration value, and work our way through that loop data. The other way is to use a determinate loop, a for loop. And generally when we are able to use a while loop or a for loop, all else being equal, we generally prefer a for loop. And so here we have the for keyword and fruit, and it's an in. And so for letter in fruit, well, that just says letter is our iteration variable, and it's going to take on the successive values of each of the characters. So this loop is going to run 6 times, and letter is going to be B-A-N-A-N-A, banana. I'm always terrified when I make these slides that I'm going to misspell banana, because somehow I always think that there are 2 N's somewhere. I don't know. It's not one of my favorite words to spell. I actually didn't choose banana as the constant. The author who I borrowed the textbook from, Alan Downey and Jeff Elkner, they used banana, and so I'm still using banana. So some of the jokes in the book aren't my jokes. They are the jokes of Jeff and Alan. So here are just 2 equivalent, so you can have the while loop. They sort of both do the same thing. They both just print the letters out one time through. Each of these loops runs 5 times. But you can see how the determinate loop, the for loop, is a prettier loop, unless you truly somehow need to know this number as you're going through the loop. But if all you're doing is going through and you want to touch in order each of the characters of the string, you then simply write a for loop, because it's more elegant. The less code you write, the less chance there is for you to make a mistake. And so the fact that these are equivalent, this is 2 lines of a loop, and this is 4 lines of a loop. That's twice as many places as you could make a mistake, because you might, misspell index or something. I mean, why even make an iteration variable if you don't need to make an iteration variable? And so we can do things that harken back to our iterations and loops chapter, where anything that you can do in those things, like look for the largest letter, look for the smallest letter, search to see if a letter exists, or say count the number of A's in the word banana. And so that's what this is doing. And so we have a counter. So again, we do something at the top of the loop, we're going to do something in the middle loop, and then we're going to print it out at the bottom. So we start our counter at 0, we're going to loop through all the letters, and then if the letter is A, then count equals count plus 1. This is kind of a pattern in a loop where we're noticing something, and instead of like we did it earlier where we said found equals true, well, we're going to count them this time. So if we have 1, we'll get 1. If we have 0, we get 0. And how many ever there are, but there should be 3, because it's going to run 3 times, and there's 3 A's in banana. And so this is a conditional within count. We've seen counts, we've seen conditionals in loop in prior chapters. And so again, I love the in keyword in Python. It again reminds me of set notation in algebra. If you're a math whiz, if you're not, don't worry about it. Or maybe you will be a math whiz and you'll say, whoa, this set notation reminds me a lot of the in keyword in Python. So again, it's for iteration variable letter. Again, don't get stuck with letter. I just happen to be using it here in banana. And that is for each character in the string banana. Run this loop once, changing the variable letter to be the particular character that we're pointing at. And so it's taking care, for is taking care of a lot for us, right? And so this is sort of this really smart for loop. The for loop is, both deciding how many times to run the loop, in this case 6, and it's advancing the letter. So advance, print, decide whether you're done, 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 advance, print, decide whether you're done. I am now done, because we're done with that particular string. And so you can think of the for as, magically doing all of this for you, of both deciding how long to run the loop, when you're done or not, and moving down through all the successive letters in the loop. So up next, we'll talk a little bit about additional things that we can do with strings. So now we're going to dig into strings a bit, and we've already looked at how you can pull out a single character in a string, and now we're going to look at what we call slicing, and that is pulling chunks of a string out. And again, we're going to use the square bracket operator. And so S, and the way I say it is sub, S sub 0 through 4. That's how I read this. S sub 0 through 4. So I look at the colon as through, I look at the brackets as sub. And so S sub 0 through 4 says start at position 0 and then go up through, but not including 4, right? So we don't include 4. So that's probably the hardest part of this. Up to, but not including. Up to, but not including. This seems counterintuitive, kind of like starting at 0 seems counterintuitive, but after a while, you get used to it, and there'll be situations where you're writing code like, oh, that's why that works better. But just for now, remember it. Up to, but not including. It's just kind of a little thing. We'll come back to when that is useful for us. 6 through 7, well, that ends up being starting at 6, up to, but not including 7. So that's why we only get the P out. Now, one thing that Python is pretty nice about is it's not going to give you a traceback. We might expect that 6 through 20, well, there's no 20 characters, but it's like, that's okay. We'll just let you stop at the end, and we'll start at 6 and go all the way to the end. Oh, no traceback. It's almost disappointing sometimes when Python doesn't trace back, when you think, if you're so obsessed about everything, I would have traced back in that situation. But hey, I guess if you're allowed, you're allowed. And so there we go. Now you can eliminate or omit the first or last. If you eliminate the first, it assumes the beginning of string. If you eliminate the second, it assumes the end of the string. And why you would do this, I don't know, but that's from beginning to end, so it's the whole string. So whole string, 8 through the end is thon, and up to but not including 2 is mo. All right, so you get that. So that's pretty simple. Once you've got the rest of slicing and the rest of string indexing, the notion of eliminating the first or the last of the colon expression, the first or second of the colon expression, I think is actually pretty intuitive, pretty nice. We've already been concatenating strings together. We overload the plus operator, and there is no space added. Remember, when you're doing print, x comma y, this comma does turn into a space, but that's not what's happening here. There is no automatic space being added, and so we see hello in there, and it just is hello there with no space. And so if we want, we just have to concatenate the space explicitly if we want to put spaces into strings. The problem is you might think it's more convenient to add a space with concatenation, but then you have to think, well, what about if I want to concatenate things and not put the space in? Then I'd need a different operator. So that's kind of why it works that way. We can use in differently as a logical operator, so we're using it as an iteration structure in for loops, but we can also use it as a logical operator in if statements. So it's kind of like the double equals or not equals or less than or equals or something like that. It's like those guys, and it returns a true or a false. Is n in fruit? So that's a question, and the answer is true. Is m in fruit? No, that's the answer to a question. Is nan in fruit? Doesn't have to be a single character, it can be more than one character, and the answer is true. And then you say something like, if a in fruit. And so this is the logical value that returns a true or a false, and yes, we found it. So that becomes true in this particular case, so it runs the little indented bit. So in is an operator in this particular situation. In a for loop, in means something different. And we'll use in for other things as operators, as logical operators, coming up in a bit. You can compare strings, and this has to do with the character set of your computer, the character set that Python is, but in general, it is lexicographically less than and lexicographically greater than. Uppercase and lowercase are a little weird. I think when we used the max function earlier, the way my computer was set up, uppercase was less than lowercase. But in general, uppercase is less than lowercase. But in general, it's bad to assume case, but there is a deterministic way to sort strings. You can, have something equal to or less than or greater than, and all those operations work naturally. The less than and greater than, you have to kind of be aware of uppercase, lowercase, things like where punctuation sorts less than or greater than letters. That's kind of unpredictable and depends on the character set of your computer, and something you just play with and figure out. If you're doing sorting stuff by first name and last name, as long as the case is kind of the same, if you were sorting Chuck with an uppercase and Glenn, the fact that these uppercases, they'd sort right and these lowercases would sort right, but if you were to subdue instead lowercase Chuck and uppercase Glenn, then that would sort weird. As a matter of fact, the G would come before that. And so case can mess this up. But in general, other than case and special characters and other things, it technically works. It's just hard to kind of predict it. A lot of what we do is use the string library. And so the strings are objects, and we'll talk later about what that really means. And objects have these things we call methods. So a string object has some built-in capabilities, and one of the built-in capabilities that the string object has is, here is a string object, and because greet is a string object, if we said type, we'd see that it was an str. Dot lower says, hey, dear string, make a lowercase version of yourself. It's like calling this function lower and passing greet into it, and then give that back to me. Now, it doesn't actually change greet. It gives me a lowercase copy. So here I have hello Bob with an H and a B uppercase, and what I get back in Zap is hello Bob all lowercase. And note that greet is unchanged. So hello Bob is still there, and you can even call these methods on constants. So this is a string object, quote, hi there, quote, dot lower, that says call lower on this bit of string and give me back a lowercase version of it. And so it prints out as the residual return value. This is like a function call. A method call is a kind of special form of a function call. It's a function call where you say the thing dot the function name rather than function name passed in as a parameter. Like len, for example, is non-object oriented. Len of x, that's non-object oriented. Object oriented would be x dot something, parenthesis. But so constants are objects as well, and taking the lower gives us back lowercase hi there. And so that's just one of the things that you can do in the string library. These are built into string variables and constants. They're just always there. As soon as you make a string, they're part of it. And when you do type and it says it's class str, we'll get to object oriented. Don't worry, we'll get to object oriented. Okay, and so you can do things like use the type. If you're just, look, this used to say type stir, but it's class stir. Kind of, this is more of an the word class is an object-oriented concept, but it is a string. And you can use the dir, and of course there's extra stuff up here. And this is showing all the different methods or capabilities, things we can do to strings. So, x dot something, parenthesis. Well, what can we do there? This is all of those things that we can do to x's that are built in and come with come with strings when we build them. And Python, of course, has great documentation online for all of these string methods and what they do and how they work and why they work the way they do. And so here's some of that Python documentation. We'll look at a few of these, but don't hesitate to say Python string uppercase, and then I'm like, oh yeah, that is upper, right? And so here's a few things that we can do and use. Some of the ones I use a lot, and we'll look at each one of these things. So the find operation says find me a substring within a string, right? Find me a substring within a string. So find me the first NA and give me back the position. So that gives me back 2. And then I can say go find a Z in there. Well, there's no Z, and so it returns me -1. So that's what the find does. So we're going to use this kind of stuff a lot, and we do a lot of looking in strings. Converting things to upper or lower case, there is an upper method and a lower method. So greet.upper, and that means the uppercase NNN is hello Bob. Greet.lower That means that www is the lowercase hello world, and greet is unchanged. Greet is still hello Bob with upper and lower, because each of these methods basically say I'm going to give you back a uppercase copy or a lowercase copy of the original thing without changing the original thing. Search and replace is super useful, super duper useful, and it's pretty clean. Here we have a string and we use the replace method. In this case we're passing in the old and the new. Bob, replace all Bobs with Janes, and so that takes this hello Bob and turns it to hello Jane. Again, greet is unchanged. Greet is unchanged, and it does more than one thing. So this says go find, well, let's clear that. This says go find all the O's and replace all the O's with X's. And so it goes and finds 2 of them, and then out come 2 X's. And so that really is a replace is not just replace the first one, but replace all of them. White space, as we'll see, is a big deal. And white space is not just blanks, although the most common thing, but it's also sort of non-printing characters like tabs and new lines and other kinds of things. And so we have a number of different ways to strip white space. So here we've got some spaces at the beginning and spaces at the end. And we print out, we do an L strip, and that throws away the spaces at the beginning. That's the left, so that's a left strip. It all takes any, if there's nothing there, it doesn't harm it. R strip means throw away all the blanks on the far end. And then strip says go take both sides for strip, and so that pulls out all the spaces on both sides. This will be useful because sometimes when you're tearing stuff apart, you'll find yourself getting extra spaces, sometimes at the beginning, sometimes at the end. And it can be tab or new line. It's sort of white space that is kind of not visible, clear. That's what white space is. It's like if you were on a piece of paper, it's the white space. It's like X. Well, that's not white space, but right here, oh, that's white space. It's any character that doesn't cause printing to happen, if that makes any sense. It's any character where nothing would be printed. And there are characters like that. There's like even bell characters, but we don't use them very much. We can ask very conveniently, we can say, hey, does this line start with a particular string? And so, you know, line, does this, this is a question, going to return a true or a false. Does this line start with please? And the answer is true, it does start with please. Does this line start with a lowercase p? No, it does not. And so again, you'll use this in the context of if something, colon, some block of text, some block of code. So we can combine these things to tear stuff out. And so let's assume that what we want to do in this case is we want to take a from line. This is from an email format from a mailbox. And this has got the from with a space and the person's email and then @ sign in the school they're from and a space and then the rest of the stuff like when this mail was sent. And this is a real mail message from this guy Stephen from the University of Cape Town in South Africa. And it's really Stephen, and this really is the first line of a file that you'll get to know pretty well by the rest of this course. Hi Stephen, we like you. You are the example in my class and have been for a long time. People actually who know Stephen have taken this class and they're like, Stephen, I saw your picture in the class. So if you're ever in Cape Town at the University of Cape Town, say hi to Stephen and tell him that you saw him in the class. But okay, that's neither here nor there. What I really want to do is I want to extract his school from this email line. Okay, so now eventually we will do things like the data will come from files, but this is still chapter 6. So this is the data we're going to search through. And so we can say, hey, let's go find the @ sign. Search up to this position and find the @ sign. So data.find @ sign. And give me back where that's at. That's in position 21. This is position 0. Then what we're going to do is we're going to look for the next space after the @ sign. So we're going to start at the @ sign and tell find to start here and look forward until it finds a space. So data.find, look for a space starting at the position of the @ sign, and then that'll be in position 31. So 31 is what we get in the space position. So now what we have is we have in 2 variables, we have position, the position of the @ sign and the position of the space after the @ sign. Now what we really want is this bit right here. So we have to go one beyond the @ sign, and we don't want the space. So we say, we're going to use slicing here, data sub at position +1 up to but not including the space. Oh, smiley face, because we didn't have to say space -1 because that is up to but not including. And so we get that little bit right there. So we don't have to say -1 there, because this is not actually included. The thing that's at the position, the space is not included. So that's already a little benefit for the up to but not including. And so when we print this variable out, host, we get exactly just the school that Stephen works at and probably went to, as a matter of fact. I don't know if he went there or not. So this is just kind of a note for non-Latin character sets. You know, all programming languages from the 60s on tended to work in what we call the Latin character set, which is the United States and England and Europe, and lots of places use this ABC character set and the special characters. But it's really common to want to use different characters. And so if you're going from Python 2 to Python 3, and we'll talk about this a little later when it matters more. Luckily, we're in Python 3, and so one of the big things about Python 3 is that all the internal strings are Unicode. In Python 2, there was sort of some confusion as you went between strings, and this is just a little bit of code. And so I'm putting in here, you know, some Asian characters. This is Korean, actually. Asian characters into X, and then I say what kind of a thing this is, and that is a string. And then there's this Unicode, and this comes from Python 2. If it's a Unicode operation, it's still a string. Whereas in Python 2, if you put international characters into X, then it was a string, and then there was a separate kind of a constant called a Unicode constant, and it was a different type. And there was ways that you had to mess with these Unicode variables as you did things like read them from files and put them back into files and did other things. So it was much more difficult in Python 2, but we're doing Python 3, and in Python 3 it natively understands non-Latin character sets, international Asian character sets, you know, Spanish, French character sets. And so this is a good thing for Python 3, and this is one of the real benefits of using Python 3. And as we start doing stuff where we're exchanging data with the outside world, this will come into play, and I'll have to show you how to use it. There was weird things that you had to do. It just makes a lot more sense in Python 3. Okay, so we've talked about strings. We learned about the string. We're converting it. We've done a whole bunch of stuff, and this is, again, you know, we're not yet doing anything super useful. We're learning sort of how to like slice and dice, even though we're sort of not making the meal yet. Up next, we're going to talk about files. We're going to read some data, and we're going to slice and dice and use all the things in the next chapter that we've learned up to this time. So see you in a bit. Hello and welcome to Chapter 7. This is the chapter where it all really starts to pay off. We have been learning bits and pieces and doing little 2 lines, 3 lines, 4 lines of code to learn the basic building blocks of Python and learn some of the syntax and find lots of terms. But now we're actually going to start doing something. So if you look at what we've been doing so far, you know, we're inside this little computer, and you type up, the Python says what next, and you give it its command and it does something, and you do something else and does something. And you do this 3 or 4 times, unless you write a loop, and then it goes like, 10, 20 times, and that's it. And then maybe we write a thing that reads something from our keyboard, gives us something back, and then we write something to print something out, print a few things out. And so we've been pretty much using the keyboard, the screen, the CPU, and the memory. That's kind of where we've been living. And while it's important to talk to the keyboard and the screen, the real world is things like databases that live out here, files that live on our systems, and connecting to the network and reading data from the network. And so that's what we're starting to do right now, is we're starting to be able to work outside kind of our code and create things that are permanent. And so we're going to be talking, initially we're going to work on files. We'll later talk to databases and the network and other stuff, but for now we are talking about files. And so really kind of we're stepping out a little bit and reading things that are permanent and creating things that are permanent. The kinds of files that we're going to talk about mostly are text files, and you can think of these as a sequence of lines in a file that are easily read by Python. You've been making text files all along. Your hello.py, that file is a text file too. You're using a text editor to create that file. You put your Python commands in a file, you run those files, and that's what it is. And so a file can be thought of as a bunch of lines, 1, 2, 3, 4, 5, 6, 7, a blank line here. That's possible. And but the reality is that these are actually just lines, and we have a special character called the new line that we'll talk about in a second. So to read a file, you have to call the open function. And open returns what we call a file handle. Open doesn't actually read the file. Open makes it possible so that you can read the file. So the parameters to open are, it takes one parameter that's required, which is the name of the file. Another parameter that's optional, whether or not to read it or write it. If we're reading the file, it doesn't harm it. You can read it over and over. If you write it, it actually, if there's already data in that file, it truncates it and writes something. And we're not going to really write files, we're mostly going to read them. And so open sort of, you pass it in a file, it gives you back this file handle, and then you have a variable in which you store it. I often call it fhand to be mnemonic. You'll see my code, I use fhand all the time to indicate that that is a file handle. And so if we were to run this in interactive mode, we'll open mbox.txt, and that is a function built into Python, and then it gives us back a handle. It does not give the data. You can kind of see this when we print out the file handle using the print statement. It doesn't print the lines that are in the file. The lines that are in the file are sort of out there. There could be like 10 million lines for all we know, lines in the file. The handle's like a little opening outside of your program, and you can talk to the file by opening it. Then you can read stuff. You could, if you're writing the file, you can write stuff, and then you close the file to shut the handle down. But handle is a thing that allows you to get to the file. It is not the file itself, and it's not the data in the file. It's just a wrapper that kind of allows you. So this, if you print it out, it's like that's the file we opened, we're reading it, and encoding has to do with the different kinds of character sets, which we talked about at the end of the last lecture, that Unicode character set, etc. UTF-8 is a great character set. It's probably the most typical character set that you will run into, although you can have different character sets of files, but most of them are UTF-8. So, of course, this is Python. If you make a mistake and there's a file that doesn't exist, we get a traceback, and it blows up. We'll show you in a second how to deal with that. Now, the new line character is an important part of file reading. And in files, in strings, we can put the new line character in by this \n character. And the \n is the character that indicates that we're supposed to go to another line. Go to a new line. Go to a new line. And so we have, what is this? Well, that's a \n. That's a \n. And so if we print it out, we print it this way, we see that the \n is in there. This is how we type it. We actually type \n to Python to indicate that we're supposed to put that there. But if we do a print statement, it actually interprets the \n, and so the \n causes kind of this movement to the beginning. Now the print actually, at the end of this, adds another \n. So the \n that we put in by putting it into this string is that one, and then print always puts a \n at the end. There's actually a way to override that \n behavior by putting something on the print statement, which we'll talk about later. Now, it's important to note that the \n is one character, right? And so even though this x\ny prints this, and then print adds another new line to go down to here, if you ask how many characters, what is the length of this? Well, it's only 3. That's because that's a character, the \n is a character, and the y is a character. So it's a 3-character string. So the \n is a character like all the rest of the characters, but it's only, we encode it by typing \n. It's called an escape, where the \ is the escape, \n is a way to say new line, because we can't see it. It's a way for us to encode in a string this non-printable character, this invisible character. The white space, it's part of white space. So as we're reading through the file, we can think of it as a sequence of lines, and we can read these a line at a time. We can also read them a character at a time if we want. And so, but it's more common to say read this line, read the next line, read the line after that, etc., etc., etc. But the way to best think about this, it doesn't really matter. You can think about it as lines, and we will in most of the programs that we write. But realize that the way when we see this, when we see it like this, it comes back to the beginning, it comes back to the beginning. There's a character in the file at each of these points to say go back to the beginning. It's like hitting the enter key on your computer. And that is a new line. So you have to think that in the file, in order for your text editor and Python and everybody to know where the lines end, you put new lines in the file. And that's another character. So, you know, this looks like an empty line. This line here looks like an empty line, but really it has a single character, and the character is a new line. And it turns out that in a bit we're going to need to keep track of the fact that every line is ended by a new line. So up next, I'm going to talk a little bit about how to read files in Python. So we're going to find that there's a number of different ways that we can read through the file, but the most common way that we're going to read through the file is to treat it as a sequence of lines, and we're going to use the determinant loop, the for loop, to do this. And so what happens here is we get back this handle that opens the file and gives us back the handle. That handle x file is the variable I just named it x file. That's not the data, but it is a sequence. It is that file handle represents to Python a sequence that we can potentially walk through and then get all the lines. And it's the simplest, most beautiful, elegant way to read all the lines in a file. We use the for loop, and we have an iteration variable. This is going to take, when we talk about the file, cheese is going to be the first line, then the second line, then the third line, then the fourth line. So it's like going through a string, but you're going through a file now, and you're getting it line by line. So that's each line. I just picked a variable named cheese so you didn't get confused. Later I'll call this line, but Python doesn't know anything special by naming that variable line. Okay, and so this is, it's the for and the in, and so for, I read this as for each line in the file x, the file handle x file. So it'll run this loop one time for every line and then print it out. So it's actually really quite simple. Okay, other languages like C or C++ or other languages, they have to write while loops with end of file conditions and all kinds of things that make this very difficult. But this is one of the prettiest things that Python has. It's a very, very pretty thing. Okay, so let's talk about what we might do. And we're going kind of back to iterations now. What if we wanted to count the number of lines in a file? Well, this is a basic loop counting pattern. So we open the file, and then like in all these loops, we do something to sort of prime the loop to get it started, set a variable count to 0. And I'm going to use the variable line that's going to go through each of the lines in the file, for line in fhand, down the file. And it's going to run this loop once for each line in the file, and the variable line is going to change. But all I'm going to do is add count equals count plus 1. And so that's just like from counters, that's just how you detect. So every time we see a line, we're just going to add 1 to the counter. We're not printing the line, we're not even looking at its data at this point. And then when the line is done, however many times it has to go, out it comes, and we print out line count equals count. And so if we open inbox.txt, this is going to do all this work and then print this line out and say line count is 132,045. So this is a little 5-line program that shows you how to count the lines in a text file using Python. Again, simple and elegant and not too much syntax for you to have to learn. Now it's also possible to read the file as a series of characters all in one go. Read the whole file in. Now you got to be careful depending on the size of the file. This is going to lead to a string variable with a lot of data in it. Now if it's 100,000 characters, that's actually kind of a small thing. But if it was 10 million lines, that would probably not be good. You'd want to read it one line at a time and process each line and then do something. But mboxshort.txt is a small little file. So we open it and we get back a file object, file handle object, and we call the read method, and that says, look, go through and read all the text and give it back in one big blob, one big string, and I'll put it in imp. And so that's where you have a line, a new line, a line, a new line, a line, a new line. It's not really lines, it's just a sequence of characters with new lines in there to punctuate them. And now you can split that, later we'll see how to split that into separate lines if you want. Now I picked a file that was short, and so this imp variable now has a string in it, and I can use the len function, pass a string into the len function. It says, oh, 94,626 characters. That's kind of a small little file, and perfectly okay to read it all in one go. And so now I say just print the first 20 characters. That's, you know, beginning to up to but not including 20, and so it shows the first 20 characters of that little file is a from line, because this is a mailbox file. Now, let's say we're going to do a searching, and we did this loop where you're looking for something. And so we're going to search for lines that have a prefix of from. Okay, that's what we're going to do, and we're going to print those lines out. So there's lots of lines in this file. You know, line, 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 from. Line, 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 from, right? On and on and on. And we only want to show these lines, the ones that match, right? That's what we want to do. And so we are going to write an open statement, and then we're going to loop through, and we're going to ask the question, if the line starts with from, print it. So sometimes it's going to skip, 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 and then it's going to run it, and then skip, 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 and it's going to run it, skip, 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 and then it's going to run it. Okay, so that's the basic idea, and that'll finish when it's all said and done. And so this is like a criteria. This is like a search. We're looking for lines that match the string, that have the string from as their prefix. Now, when we look at the output of this, it's kind of weird. We see kind of these little blank lines that show up. Blank, 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 blank. What's going on here? What's going on? So let's take a quick look. The problem is new lines. Well, I mentioned that the file has new lines in them. And so when you do the for loop, it doesn't throw the new lines away. As you might expect, it would be kind of nice if it did, but it doesn't. It actually shows you, when you read, it reads that first line up to and including the new line and gives you that back as the variable. So that is the first new line, so that means it's going to go down. And then the print statement actually adds another new line. So that's the second line of the file has a new line at the end of it, and the print statement adds another new line. So if we take a look at the code, there is a new line. Oops, come back. If we take a look at the code, this variable line has a new line in it. Oops, where am I at? I'm on the wrong slide. There we go. Yeah, this is the one I want to do. If we look at the code, there's a new line in here, and then the print adds another new line. So the print adds a separate new line. And that's how we get two new lines. The print statement's new line and the new line from the file. Here's how we fix it, and you're going to write this code a lot, because when you're reading text files, you end up with a new line, and often you don't want the new line. But thankfully, as we saw in the previous chapter, there is a nice little function in Python for strings called strip that allows you to throw away white space. And to review, remember, white space is anything that doesn't print. And this new line is not a non-printing character. So our strip gets rid of it. So it's a way to get rid of white space. And our strip does it from the right end. So it's the right end of the string. And so if we just are going to loop through all the lines in the file, we say line equals line r strip, and then this variable no longer has the new line at the end of it. We have our little if statement, and if we print it, then this line, the data has no thing, and then the data has a no new line in it, so the print only goes down one. And so now we have single spaced output. And so you're going to be doing that a lot. It's really common to read through a file and then just strip the new line or any trailing space off the end of that. Now, there's a couple of ways to do a loop like this, and let's just think of this as we're looking for a file with lots of different lines in it, and we want to ignore all the lines except some, say, good lines, and we want to do something with those good lines, or the lines we're looking for. Needle in a haystack. This is like searching for a needle in the haystack. So if you look at this code at a high level, we're going to loop through everything, and then we're sort of picking which lines are, and these are the good lines down here. Now often we have a bunch more code that we want to do, and we're not just printing them, but we're going to do a lot of code. So sometimes you actually structure the loop a little bit differently. And so the way to do it, and this is going to do the exact same thing, it's just a little different way of thinking about this loop. So the top part is the same, we're stripping it, and what we're doing here is everything's the same here except we add this and not. If the line does not start with from, that's the translation of that. If the line does not start with from, continue. So basically we have a skipping pattern. So the lines we're not interested in, we skip. So we come down, we skip a lot of lines. And then we find a line that's good, and then we fall through. So this is the good code. And then we have all the other good code that we want to do to that line. We have that showing up down here. And so there's just two patterns, two ways to do the exact same thing. So another way to select the lines that we're interested in is to use the in operator. So we talked before about the in operator and how that works. So we're basically, and I'm going to use the continue skipping method. So we're going to read all the lines, these first few lines. If uct.ac.za is not in the line, skip it. And so this is going to print out all the lines that have the string uct.ac.za in them. And so you see this is the output of the program, ... Sometimes you'll have programs that want to read different files. Often I give assignments where I say, show me how this program runs on the short file, and then show me again how it runs on the long file, just like this. And so the way we do that, to input the file name, instead of making the file name be a constant to the open call, we make the file name be an input. So we just run an input statement, which gives us a prompt, and then we type mbox.txt, and then that shows up in this variable f name. It's of course a string all the time. And we pass that into open, and then we open it, and then we do, the count operation. So if we enter mbox.txt, it counts 1797 subject lines in mbox, and if we give it mbox short, it says there are 27 subject lines in mbox. And again, this is another one of those ifs, and it's just counting, but only counting lines that match a particular pattern. Okay, so now the user can also type bad file names, and we need to be able to deal with that as well. And so we're taking a small change to the code. The dangerous code is this line right here. This line right here is going to trace back if that file doesn't exist. So what do? Well, we're going to just expand that. The rest of this program is exactly the same. The only thing's different is we've got this line. We took out insurance on it, and we know that it might blow up, and so we have it in a try and except block. So here's how the code runs. So, the input runs, we type in a good file name, it comes in here. This works, and so it skips the except, and so it runs the code and prints out the count. So that's the good pattern. The bad pattern is here, where we type in a bad file name, it comes in the try except, this file name is nana-boo-boo, and it's going to blow up, so this line blows up, so it jumps down into the except code, prints out, file cannot be opened, so it prints this out. Now this quit is really important, because if we don't put this quit in here, it's going to continue down here, and that's going to blow up here because file handle is not defined properly at this point. And so what we have is, we have this quit is a special function where it comes in and never returns. So this is a way to terminate the entire Python program silently with no traceback. All right, so we put in our own error message, so we look like we're professional, say, oh, could not open this file, and then we stop. If you don't, it's going to come down here and it's going to trace back right there. It's going to blow up. So the quit is useful when you want to stop executing because you've detected some kind of an error. So that's a quick zoom through opening and reading through files and doing some patterns. Most of the rest of the programs in this course are going to say open for rstrip, look for, and then do something interesting. That's going to be our loop that we're going to do over and over and over again. And now we see how this looping and if and iteration and variables are starting to come together, and you can actually sort of do a program that does something useful. But before we get to too many more programs, we got to switch a little bit, switch gears and talk up structures, but lists are probably our first real data structure that we're going to think about and design and make use of effectively. But before we talk about what is a collection, we should talk about what is not a collection. So we're familiar with what a variable is. We know that a variable is a little piece of memory that's got a label on it. And then an assignment statement, you know, sticks a 2 into X, and then and then 2 is in this little cupboard. And then it goes to the next line, and then 4 goes into X, and so the 2 goes away and the 4 is there. Now, a key thing is you can't have more than one variable at any given moment, right? And more than one value in a variable. So when we move to collections, collections are more like suitcases. We can put lots of things in them. We have ways of organizing them, and as we go through lists and dictionaries and tuples, we'll see how there are different ways to organize them. And as a matter of fact, we've been talking about lists for a while. Every time we use one of these square bracket syntaxes in earlier programs, we've been working with lists. And so this is technically a 3-item list with 3 strings, got commas here. Joseph is one string, Glenn and Sally are another string. And here's another one that is another thing. And the list is basically, it's a list constant, and it's being assigned into a variable. So this friends variable has 3 things in it. So that's different than what we've been talking about before. So these bracket structures with square brackets are those lists. And so the print is just a print with parentheses to get the print to work. But 12476 is a 3-item integer list. Red, yellow, and blue is a 3-item string list. But it doesn't all have to be integers or strings. Python can handle different things and different kinds of data in different positions in the list. So red, 2498.6, a 3-item list with a string, an integer, and a floating point number. And while we're not going to use this too much for now, this outer list is a 3-item list, and the second item is another list. So this is kind of alluding toward what we'll do when we start talking about data structures, and that is we have a structure and then we have another structure inside of it, and sometimes this can get quite complex. And we're doing this for a reason. This here has no reason, just to show you that it's possible that lists can be made up of lots of things, including other lists. And of course there is also the notion of the empty list. And like I said, I have had to be able to tell you about lists all along. We use them in for loops. We can put lots of things here. We can put file handle here, we can go through the file, we can put a string there, we can go through the characters in the string, and in a list. And the iteration variable then goes through the successive elements of the list, and that's why this prints off y 4, 3, 2, 1, and then the loop is done and it prints out blast off. So we've been using them, and we've been actually iterating through lists with for statements all along. So the for statement has been something we use with lists, and when you just need to go iterate through the list and go through every item in order, the for is a great way to do that. So friend is our iteration variable, friends is our list variable, and so that says friend is going to successfully take on the value Joseph, Glenn, and Sally and print out, Happy New Year, Joseph, Glenn, and Sally. It runs 3 times, once for each of the values, and the iteration variable advances. Now, I do want to make it really clear that the choice of friends and friend singular and plural is arbitrary and capricious. It happens to be convenient and intuitive that the iteration variable is 1 and the list variable is more than 1. But Python has no idea about singular and plural. As a matter of fact, Python would care. It would be totally equivalent for Python to do the same thing, to have the list variable be z and the iteration variable be x. X will take on the successive values of these 3 things. Now, am I being nice to you by calling this list friends and this iteration variable friend? I am, but I also don't want it to confuse you if you're just a beginning developer. So, just like strings, we can sort of look within lists. Part of the thing is when you put more than one thing in a data structure, you need to get them out. And so lists have positions, they maintain order, and so the first thing in the list is the sub-0 position, sub-1, sub-2. Just like strings, they're 0-based, just like European elevators, they're 0-based. So if we take a look and we say, oh, friend sub-1, that's how I read that. The little square brackets, when you take a variable here and you say friend sub-1. Remember, singular and plural don't matter. Friend sub-1 means Glenn, because this is the 0 and that's the 1, and then Sally's the sub-2, and so that's what prints Glenn out in this particular thing. Now, lists are mutable. Mutable is another word for changeable. They can be changed, meaning that a list has 3 things. You can change the thing right in the middle if you want. To take a look at what's not mutable, strings are not mutable. So if I take a look at assigning banana into fruit, well, fruit sub 0 is a capital letter B. Could we imagine for the moment that we could change fruit sub 0 to lowercase b? Well, the syntax would be how you would do it if you could do it, but it turns out that strings are not mutable, meaning they're not changeable once you create them. And that's why when we do things like lowercase or uppercase, we take a look at the fruit and we say, give me a lowercase copy of that, and then we take the return value from this and we store that in x, and that's how x becomes a lowercase banana. But fruit is still the original one, so fruit has not changed. Compare and contrast that with a list though. Here we have a 5-item list, 2, 14, 26, 41, and we're going to do the sub 2 position, and the sub 2 is 0, 1, 2, so that's that one right there, and we're going to assign a 28 into it. So that 28 is going in here, going to wipe that out and put 28 in. So we can do item assignment in lists by putting a bracket syntax on the left-hand side to say, don't just put it in the variable, put it in this position within the variable. So that's what that's doing. And when you print that out, the 28. Everything else is unchanged, meaning the whole list is there. There could be 1,000 items in the list, and then you're changing the second one. We have a function called len. We've been using this len function all along to take a look at how long strings are. It counts the number of characters in the string, so that's a 9-character string. If we have items in a list, len tells us how many items there are. It's not like how many characters there are, it's the number of things. And each thing doesn't have to be a number. It could be a number, a string, or even another list. And len is the way to say, hey, how many things are in there? There's a function that returns a list of numbers, and we use it, as we'll see in a second, to construct specialized loops to go through lists. So let's take a look at this range function just for a minute. So range takes as its parameter the number of numbers that you want returned. So I'd like a 4-item list with the numbers 0 up to but not including 4. And so it just turns out that that is really useful for constructing for loops that are counted for loops that go to 0 to the 1 to the 2, as compared to the the definite loops that go each way, go through each one. And so it's a common thing to say, okay, we know how many things are in this list. There are 3 friends, and if I combine range and len, so I take len friends, which is 3, and then I take range sub 3, I get 0, 1, and 2. And so the interesting thing is this 0 corresponds to the first one, 1 corresponds to the second one, and 2 corresponds to the third one. Okay? And so we'll use this to construct loops, especially when we need to go through an array and remember what position we're at. And so here's just an example of 2 different loops. This is a for loop that's just going to go through whatever's in this list. So friend is just going to take on the successive values, and so it's going to print out these 3 things just as you would expect. And if you don't need to, while you're going through the loop, know the position, your relative position from the top in the loop, that's okay. But sometimes you want a little more sophisticated loop, and instead you want to be able to loop through where you know the position. And so what we do instead is, instead of looping through the list itself, we do range len friends, which gives us 0, 1, 2, and then I takes on the successive value 0, 1, and then 2. So this loop is going to run 4 times, and I is 0 the first time. And we might even just look up the value inside that sub-0 value, so we get Joseph the first time, so prints out Happy New Year Joseph, goes, and I becomes 1 now, and so it gives us Glenn, and that prints out, and away you go. So if you look at these 2 loops, they really do the exact same thing. The only difference is this we allowed the 4 to find its way with the iteration variable through, and here we created our own I variable that went through the positions, and they're dense, there's no gaps in here, so it's 0 through 2 that it goes through. So these 2 are equivalent. There will be times when you'll want to use one in the other. I tend to prefer the first one because it's prettier as long as it works for me. So that gets us started with loops. We'll be back in just a bit. Okay, so we've taken a look at loops, and now we're going to just take a bit of a look at some of the operations that you can do with loops. Python has this, as we'll soon learn, object-oriented approach to its operators, And the plus can add strings and it can add numbers. It can add floating point numbers, integer numbers, strings, etc. And so the plus similarly works this way with lists. The plus looks to its left and looks to its right and says, what am I adding? And in the case that I'm adding the list 1, 2, 3 and the list 4, 5, 6, it concatenates them together. In this way, it sort of functions like a string, and so we get 1, 2, 3, 4, 5, 6. It's just concatenate this list to another list. And it doesn't change A or B, just like in any kind of assignment statement. Calculations on the right side don't change the variables, and they produce a new variable and then assign that into C. You can also use list slicing, and it's easy to remember. If you remember how strings work, list works exactly the same way. So it's, of course it's a little tricky. The first number is the starting position. They start at 0. So 1 is right there. So it's the 0 position, the 1 position. Start at 1, right? But go up to, but not including 3. There's 1, 2, 3. So this goes up to, but not including 3. And that's why we get 4112 out of that. So up to but not including. I'll just say that over and over and over again. If we do, you can leave the first part out. You can leave the first part out here, and you can say, oh, up to but not including 4. So that starts at the beginning, goes up to but not including 4. And so that's how we get that piece right there. We can say start at the position 3, 0, 1, 2, 3. Start at position 3 and go to the end. Now the fact that the number 3 is in here is sort of irrelevant. 3 to the end is those 3 numbers. And then you can do the whole list with slicing as well. Again, these pretty much are the exact same examples I used when I was doing strings. They're pretty much the same. There's a number of different methods, and you can look up all the documentation in list. I often just use the dir command to remind myself of them. Append will look at. Count looks for certain values in the list. Extend adds things to the end of the list. Index looks things up in the list. Insert allows the list to sort of be expanded in the middle. Pop pulls things off the top. Remove removes an item in the middle. Reverse flips the order of them, and sort puts them sorted order based on the values. So let's look at a couple of these. So if we build a list from scratch, we have a way to ask for an empty list. There are a couple of different ways to ask for an empty list. We could use just 2 square brackets next to each other, but this is a form we call the constructor form, where we say, hey Python, make a list. In this case, the word list is like a reserved word to Python. It's really a reserved class, but say list parentheses says make me an empty list, and then assign that list into stuff. So stuff is now it's a list object, it's of type list, but it has nothing in it. And then we can call the append method, stuff.append, and stick book in. And then we say, oh, and that knows how long, the stuff knows how long it is, where the end is, and how to add something to it, and then add a 99 to it, and we print it out. We got book and 99, reminding ourselves that lists, while they're often the same types of variables, same types of values in the various positions in the list, it doesn't always have to be that way. Then we say, oh, we'll stuff that append cookie. You can keep on going, and then we end up with 3 things and the cookie. We have an in operator. It works pretty much like the in operator in a string. Is 9 in my list? And that's pretty simple, and the answer, of course, is yes, 9 is in my list. Is 15 in my list? Looking through, no, it's not. 15 is not in my list. And then there's the not in operator. You can think of that as kind of like one operator. Is 20 not in the list? And the answer, since it's not there, is true. And so that's a way to just, it's kind of like starts with or in for strings, same kind of stuff. Lists are in order, and they're sortable. And so this is something that we take good advantage of. A lot of what computers want to do is sort stuff. Look all these things up, append them, and then get them sorted. And so there is this method inside of list that's just the sort method. So here we put 3 values in 0, 1, 2 position, 0, 1, and 2, Joseph, Glenn, and Sally. And then we tell the list to sort itself, and then we print it out. Now this is actually sorted the list in place, which is different than upper and lower, because if you remember, strings are not mutable, but lists are mutable, and so you say, hey, just sort yourself. Okay, and so just sort yourself, and then it sorts it, and then it's in alphabetical order, Glenn, Joseph, and Sally. I happen to be clever. I only put strings in there, and I put my uppercase and lowercase in a very consistent pattern, but the list is changed. And if I look at list sub 1, that is the second item, which is Joseph, that prints out right down there. There's a whole bunch of built-in functions to help manipulate lists. The other things I was showing was sort is a method that's part of lists, but there are other functions that take lists as their arguments. We already talked about the len function, tells you how many items there are. There is pretty obvious max, it says go through and find the largest. Min, go through and find the smallest. Sum goes through, adds them all up. And we can say let's do average by taking the sum of all of them and dividing it by the length. And you might think to yourself, oh wow, I wish we'd have known this a few chapters back when we were having to write all those loops to do max, min, sum, largest, smallest, etc. You can kind of think in your mind that inside each one of these functions is a loop that does pretty much what you did in those chapters. And part of the reason we did that back then, even though these things were here, was they're kind of easy loops to understand. And so those are there. And basically there allows two different ways of building loops to do the maximum minimum. Now it's not necessarily all that much easier to to do something using these, because you either can do them the old way or you can make a list and then use these functions. So let's take a look, and I'll just say that these two bits of code are doing the exact same thing. And what they are is they're implementing a program that's going to repeatedly ask for numbers until we type the word done, and then it's going to compute the average and tell us what they are. And so using sort of the stuff from the loop chapter, we start with a total variable and a count variable, set them to 0, and then we read a number, we check for done to break out, but then we convert it to a floating point value. And then we say total equals total plus value and count equals count plus 1. And so this is going to run over and over and over again, however many times we're going to do this. And then it's going to pop out, and when it's done, it's going to have this value of total. The running total will become the overall total divided by count, and it'll print the average out. Okay? And so that's kind of how we would have done this before we knew how to do this with lists. Now, let's take a look at the other one. In the other one, we say, let's make an empty list. Remember, this is that constructor syntax that says to Python, make me an empty list and assign the empty list. It has nothing in it, right? But it is a list, has nothing in it, into the variable num list. Now we're going to write another loop. This part here is the same, these 3 lines. Read the number, if it's done, quit, and convert to value. But instead of doing the actual calculation right now, what we're going to do is just append it to the list. So the list will start out empty, then the 3 will be in the list, then the 9 will be in the list, then the 5 will be in the list. So we're appending, each time through the loop, we're appending into the list. So we're just growing the list every time we read a value, instead of actually computing something with the value that we've got. So in either case we get value, and in one case we append it to the list. And then finally it finishes, the break happens, and then we just say, oh, hey, Python, sum up everything in the list, add these 3 numbers together, and then take the divided by the length of all those things, and you'll have the average. And so these two things give us exactly the same output. Now there is one difference. If there was like 1 million or 1 billion numbers, they actually have to all be stored into memory simultaneously, whereas here it's actually doing the calculation of the billion numbers and not using up so much memory. For most of the things that you're going to be doing, the difference in memory, there is a difference in memory. This one here uses more memory, but I can't draw very well. More memory. It uses more memory, but it doesn't really matter by the time it's all said and done. And so for you, do some parsing, read some data. As a matter of fact, we're going to read through our famous mailbox data, look for lines that begin with from space, and extract the third word. As a matter of fact, we already have some of this code already written. We're going to debug it. We're going to look at code and we're going to debug it. And so here we go. Here we have it, and it's a pretty basic program. It opens a file, loops through the file, throws away the white space, splits it into words, and checks to see if the 0th word, the first word, is from, and if it's not, we skip and read the next line. And otherwise, if we find a line that starts with from space, then we print the third word, which is word sub 2.
Okay, so this is what we've got, and we carefully saved this file into the same folder that we've got, ex08. And so let's go ahead, cd desktop python for everybody, ex_08. And so this is some files. We got our day of the week Python in our inbox short, so that's sitting there, okay? And so let's run this program. This is the program that we've got right here, Python 3 dow.py, and it doesn't work. Now, by now you've seen a few tracebacks, and there you go. So, you know, when you look at a traceback, you think to yourself, well, I made a mistake, and you've gotten pretty good at looking at that line. So there you are. You're like, this is the line. There must be something wrong on this line. And you want to change it. But that line's not actually the problem in this particular thing. And so you got to be careful sometimes. And one of the things that you didn't notice in this one right away is that it actually worked. It printed the first line out. So if we take a look at our data set, it found the line started with from space, it split it, and printed out the third word. And it blew up later. And so part of the problem is we don't know what it was doing when it blew up. And so the first thing I'd like to do in this kind of a situation is find the line and make sure there's a print statement right before it. And so I'm going to print words colon and then comma WDS. I want to print right before the line that blows up so that I know really when this finally does blow up what was going on in that line. So I'm going to run it again. And oop, did I forget to save it? No, I forgot to save it. Look at that. See the little blue dot? Forgot to save it. So now we see a whole bunch of output, and we see that it's actually doing a whole lot of work before it's blowing up. And so you see that it prints the words out from that first line and prints out Saturday, which is exactly what we expect. It's the third word in the line. And then reads a whole bunch of stuff, and it's actually, what's doing now is ignoring. Let me just put something here. I'm going to say print ignore, so I can keep track of when these lines are being ignored. So let's run it again and have the word ignore pop up, right? And so it's doing a lot of ignoring. It finds these words, prints out Saturday, reads this line and ignores it, reads this line and ignores it, reads this line and ignores it. So a lot of stuff's going on here that you might not realize. And so we have to take a look at what the problem is. And so it is now blowing up word sub-0, and now we can scroll down and we can look at exactly what happened right before the traceback. So we really now know exactly what happened before the traceback. And the interesting thing is that there is an empty string. I mean empty array. There's an array with 0 items. So I'm going to print the line out too. Print line colon. Now I haven't changed my program at all. I'm just trying to figure out what's going on here. So I'll save that and I'm going to run it. And we've got a lot of stuff and it's still working. It reads a line. It reads a line, splits it into words, and then prints out Saturday, which is the third word on the line. Now here it reads a line, and this line is a blank line. And it has, because it's a blank line, the split returns no words, and that's what blows up. And the problem now is, oh wait a sec, list index out of range. So word sub-0 is not valid, which is the first word, when there are no words. So this is a statement that works most of the time. Now you might think, oh, I want to just put a try and except in there. Well, the right thing to do is to say to yourself, oh, wait a second. If I don't have enough words, if the length of the words is less than 1, continue. So basically it's going to come through here, it's going to split it, and if we don't have any words, meaning it's a blank line, then we're going to skip it. So let's run that. So now this ran all the way to the end. It did a lot of stuff, and it did not blow up specifically, it didn't have a traceback. Another way to protect this would be to we'll take this part out. This is called a guardian pattern. Right? Guardian pattern, because this is dangerous. This could blow up, but it won't blow up if it makes it past here, and it won't come through there under the conditions that are causing it to blow up. Another way to do this might be to protect it as follows. To say, oh, wait a sec. If the line is a blank line, no, continue. So now what we're going to do is we're going to skip blank lines. I even say this. Print, skip, blank. So if it's a blank, we're going to skip blank and keep going. This will skip blank lines. It'll come through here, and this will skip lines that don't have from. But because we're not processing blank lines, word sub 0 always works. So I can run this code, and it works again. So here we have a blank line, we skipped it. Here we have a blank line, we skipped it. Now here we had a non-blank line, so we parsed it, but then we ignored it. And then up here we'll find a from somewhere. Let's find a from. Here it comes. Oh, no, there's ignore. I got too much debug print. I can't find it. Here, I'll just hunt for from with find. Okay, so there we go. There's from, and we print the thing out. So we're getting a lot of extra stuff. So I'm gonna comment out some of these debugs, and I'm actually just going to get rid of this whole skipping of the blank line. I'm going to do it with the words. I'm going to go back to the guardian we had before. If the number of words that we got, len of words, is less than 1, continue. Okay, so now this is going to be a working program. Oops, I gotta take another print statement out. Gotta take another print statement out. We sort of know what we're doing here. Okay, so this looks like a pretty safe thing. This guardian is protecting this dangerous. I get rid of that one too. This is the words that are traced back, and nothing else in this thing changed from when we started except we've added this little guardian. Now the interesting thing is if it comes through here and prints word sub 2, what happens if somehow we find a line that has from as its first word and there's only one word on? This is going to blow up. So we can make our guardian a little stronger. And we can say, you know what? We're going to skip this line if it doesn't have 3 words in it. So it has to have at least 3 words. And if we see less than 3 words, we're going to skip it. And that just makes the guardian a bit stronger. And so the program works safely, and you see these things where sometimes you want to check to see that your assumptions about the data are reasonable, and skip things where the data is not reasonable. Now so that's one guardian pattern. Let me show you a slightly different way to do this, and this is with an OR statement. So I'm going to take this code, copy that, and put it here with OR. Get rid of all this stuff. Well, this is the guardian in a compound statement. So what we're saying is if there are less than 3 words on the line, or if the first word is not from, continue. Now, we're doing this in order because the way it works is OR is true if either that's true or this is true, but if it knows that this is true, then it doesn't bother checking this. And the checking of this is what blows up, what causes the traceback. So if we flip this order, it would fail. If we do it in this order, it will work. So let's do this one right. It works. But if I get this backwards, it's going to check this before it checks this. And we're going to go back to failing again. So you got to get the order of these things right. The guardian comes before, in the or, the guardian comes before. And if this is true, then it doesn't check this. This is called short circuit evaluation, where it knows that as long as this part's true, it doesn't evaluate this second part. And so now we have a guardian in a compound statement. You'll see this a lot. Sometimes if it's more complex, you do it in multiple statements, or you fall through, check for sanity, and only run the code. So I hope that that was useful to you, looking a little bit about how to debug, where you don't just start chopping on the line that had the problem. It's not always that line, because we never did change that line. Although we did change it a little bit at the end. We added this guardian here, but we also fixed it without it. Sometimes you add some print statements to figure out what's going on before you just start chopping on that line. So again, I hope this helps. Thanks.
Or it's a sort of like a mess. And so the idea is you have these labels that you put on everything that you're going to throw in. Like I'm going to put, hope it won't stick to my keys. What else do I got here? I'm going to stick a label on my pen, a Chuck label, and I'm going to store a pen in my dictionary with the Chuck label. And so it's like having a purse or a bag or a backpack where you have things labeled, and you can throw things in and label them, and you can shout into your bag and say, give me the calculator, or give me the candy, or whatever it is that you have labeled them. You have to come up with the labels, and then you can use the labels to get things back out. And like I said, they're probably the most powerful thing, and they're basically this concept that's generally referred to as associative arrays, which means they're like lists, but they have these keys. And so the associative means the association between a key and a value. Whereas in a list, there's a position in a value, and the position is less powerful and less flexible. Most modern programming languages have this notion of associative arrays. If they don't, they're sort of unpopular, because once you get using them, you're like, whoa, they're so powerful. If you ever find yourself in a language that doesn't have them, you'll freak out. They have different names like property maps or hash maps or property bags, depending on the language you're using, but they all are the same thing. They're key value pairs. So the idea of a dictionary is that, or the idea of any collection, is putting more than one thing in, and then the difference is that you have ways of indexing it. So this basically line says, let's make ourselves a dictionary, just like we constructed an empty list, and I want to store 12 into this dictionary, and I want to label it money. And so on the left-hand side, when we use this money, that's the label that we're going to give it. And so 12 is being placed in the dictionary. That's like taking the 12, throwing it in the dictionary with a label of money. 3 is going in with a label of candy, and 75 is going in with tissues. And we say, what's in there? And there's no order to it. And sometimes the order can even change inside of a dictionary. Although there are more advanced versions of dictionaries that maintain some kind of order, but for now, let's just not worry about the ordering of them. If we say what's in there, you say, oh, there's 3 things in there. There is 12, 75, and 3, and stored under the keys money, tissues, and candy, respectively. We can ask, using the index operator, what is per sub candy? And that's like saying, hey, give me back candy, and out comes the number 3, which is that. We can update stuff. So we can say, go grab the candy version, add 2 to it, make 5, and then store that back into candy. And so now we see that candy has been set up to be 5. And and so if you look at the difference between lists and dictionaries, they both can have new items added to them. We haven't talked a lot about deleting, but items can be deleted from them. The difference is the indexing mechanism, how we look things up, how we store things, and how we look things up. So we make an empty list, we make an empty dictionary. We add 21 to the end, and we add 183 to the end, and we ask it and it says, oh, position 0 is 21 and position 1 is 183. We don't see the positions when we print it out because it's sort of implicit. Here we're going to mark 21 with age and stick it in, and mark 182 with course and stick it in, and then we're going to print it out, and there we got course and age mapped. And we can add a 23 and stick it back in age, and that overwrites. So the 21 becomes the 23. We can do the same thing in a list, except we say lists of 0, because in lists the indexing is position, and so this 21 becomes 23. And again, you just look at them and you can think of each of these as pretty much doing roughly the same thing except the indexing mechanism. The values are the same, but the keys are different. So in lists, the keys are always the position, and you don't get to assign those other than the fact that the order in which you put them in implicitly assigns a position. And in dictionaries, the key is a string. You can actually use other things. I use strings a lot in this lecture, but that's just to kind of keep things simple until you get good at it. You can actually use numbers as the dictionary index, the dictionary keys if you want. But the values are things you put in and manage in those dictionaries. So we can, just like lists, we have dictionary literals. And what's nice about dictionary literals is that they use the exact same syntax as the printout. And so it starts with a curly brace, ends with a curly brace, and then has a series of key colon value, key colon value, key colon value. And this is sort of the associative array bit. We are associating 1 with the key Chuck. We are associating 42 with the key Fred. We're associating Jan and 100. Then we print it out, it kind of looks exactly the same. And so the print statements in Python are nice in that you ask what's in a thing, you show the stuff, and it shows you in the syntax that if you type that into Python, that would be how you do a constant. And if you just say empty array, you see me also do DICT. This is constructor where you say make a new empty dictionary. This is an empty dictionary constant. These two things are pretty much the exact same thing. This is a shortcut to doing this. The empty curly braces is a shortcut to do the construction. So up next we're going to talk about sort of one of the really common applications of dictionaries, and that is counting. So now we're going to talk to you about one of the common applications of dictionaries, and that is making histograms. It's counting the frequency of things. And so if you think of a histogram as, it's a little graph, and there is, how many A's, how many B's, and how many C's, and there's a histogram that says, oh, there's this many of that and this many of that. And these are like buckets. These are frequencies, and this is how many times it happens. So a histogram. But we're going to do this thing where we're going to count people's names, and we're going to kind of count how many that we see. But the interesting thing that we're going to solve, just like many of the things in the computer, is we can't just sort of look at the data. We've got to look at the data iteratively, one piece of data at a time. So I'm going to give you a little problem. Okay, I'm going to show you a series of names, one at a time, and I want you to count for each name, make a little bucket, and then keep counting how many things for each of the different names. Okay, you'll notice that you have to start with 1 and then you move across. So just watch this and tell me what's the most common name of the set of names I'm about to show you, and how many do we see? So what was the most common name and how many times did you see it? That's the question. Now, here comes the reveal. So for humans, it's so much easier for you to just look at this and you think, how did my brain look at that? And you're like, okay, what is pretty common? Oh, maybe Chen is common. Oh, Chen, no. Maybe Zhen is common. 1, 2, 3, 4. Yeah, anybody else have? Marquard's got 3, C7. And so you'll notice how our minds, without computers, we just sort of like bounce, branch and bound. We have hypotheses, and then we decide, yeah, it's Zhen. That's it, and there's 4 of them. Now, how did your brain think about this as we were going through them one at a time? Well, my guess is if you really had to do this a lot, you would make a little picture like this. And then what you would do is if you saw a new name, XYZ, you'd add it to the list and give it a tick mark of 1. And then if you saw like C7 again, you'd give that a tick mark. And if you saw XYZ again, you'd make a tick mark. and then you'd keep adding to these tick marks, right? And that's how you would do it. And you wouldn't, like many of the things we do in a loop, you wouldn't really know what the most common one until the end. And then you'd sort of take a look at these numbers and you say, okay, that's the most common number, and then you'd be done. But you have to watch them one at a time. You can't just bounce around. And so that's how we're going to use dictionaries to achieve that. Again, instinctively as humans, we just look at the stuff. But if you had a million things, you probably want to write a Python program and use dictionaries. And so this is the idea, and there's two basic things that happen. One is the first time you see a name, you got to say, is this name there already? If it's there already, you really just want to add 1 to it, right? That's the adding of a tick. And or you want to see for the first time, you know, blah, 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 and give it a 1. And so you can use the name as the key, and then 1 is the value. And then first time you see Chen, you stick 1 in there. And so at this point, inside the dictionary, sort of dynamically adding, as soon as it sees a new name, it adds another slot in here. But then if you see the same name again, like Chen again, then you end up with a 1, add 1 to it, and so it's 2. And so at that point, Chen is 2. And so you can see how you can both extend the dictionary by encountering a new name, or adding when you see a name that you've already seen before. The problem with dictionaries is, like everything in Python, there are rules about what you can and can't do. And one of the, I think, kind of frustrating things about dictionaries is that you can't just look for a key that doesn't exist. So this is a fresh brand new dictionary, we do a constructor there, and we print out some csev, and boom, it blows up, and that's bad. But we can solve this by the in operator. The in operator we've used in the for loops, we've used it in lists, we've used it in strings. So that is a question. It's saying, is csev in ccc? Well, this is this empty one, and so it is, no, it is not. Csev is not in ccc. And so using this in operator, we can avoid the traceback. We can say, if it's not there, put it in. If it is there, add 1 to it. And that leads us to this bit of code. Okay, and that is the kind of code that we're going to build a history. This is going to histogram code, okay? And so this is going to have name as our iterator, names. Sorry, I made them singular and plural. That's nice, but so name is going to be csev, chen, csev, gen. Now normally we'll be reading this from a file, but for now we'll keep it easy. We're going to go through this. And we're going to have counts as our dictionary. So that starts out empty, and we're going to do a simple if-then else every time through the loop. If the name we're looking at is not in the dictionary already, is the key, then set it to be 1. If it's not, go get the old value, count subname, and then add 1 to it and stick it back in. So this line right here is new, adding a new thing, and this line right here is adding some things to existing things. And you do this long enough, you start with an empty one, and you do this long enough, at the very end, it will print out the histogram that you're looking for, the histogram you're looking for. And so you say, oh, we've seen csev twice, gen once, and chen twice. And so that's the idea. And so this can run 1,000,000 times if you want. Now, this notion of checking to see if a key exists and doing one thing if it doesn't exist and doing another thing if it does exist is such a common practice that the dictionary object has this method called get that collapses these 4 lines into 1 line. And so the idea is you're going to do one thing if it's in there and you're going to retrieve the current thing. Otherwise, you're going to pick a default value. In this case, we'll pick 1. I mean, pick 0. This is like the default, right? Meaning what is not there. And if you say counts, now counts is a dictionary, .get, that's like string.upper, that's a method. You give it a key and then a default. And if the key exists, you get back what's in the key. If the key doesn't exist, you get the default. Okay? So, and with no traceback, this works. So the best way to think about this is those 4 lines are equal to that 1 line, because X is either going to be whatever was in there before if it exists, or it's going to be 0. Now, the nice thing about 0 is the next thing we're going to do is we're going to add 1 to it, so that's going to get us to 1. So collapsing that loop that we saw before, we can make it just a 1-line loop, and this will become an idiom. This will become something that you will get used to and you will use over and over and over again, and after a while, right now you're looking at it, boy, that's a lot of syntax and semicolons and whatever. After a while, you just type this and not even think about it. It's an idiom. It's basically encoded in this idiom is how to both create new entries in dictionaries and update existing entries by adding one to them. So everything else in this is the same. Name is going to go through these 5 values, and we're going to say counts of name equals counts.get name, comma 0 plus 1. And so if, for example, this already has a 1 in it, then this is going to be 1 plus 1 becomes 2. If it's not, it's going to be 0 plus 1 equals 2. And so this is the idea of if new, set it to 1, not 0, set it to 1. Because the first time you see something, the count should be 1, not 0. So that's why we make this default. Now the get can be used for anything. It just so happens that 0 is a common default because it's really common that we're using this to basically make a histogram, right? Little histogram of A, B, C, right? And so we need to make a D, but then the histogram has to start at 1. So that's basically the simplified counting with get. And you know, there's a lot of things that we're going to do inside of Python that do have to do with frequencies and how many times certain things happened, and this pattern is a really good pattern to absolutely know. So now what we're going to do is we're going to switch from just looping through strings, but instead loop through files. And it's going to take a little bit of work because we have to open the file, and we'll bring a lot of things together at this point. So here would be another task, and that is here's a bunch of text from the book, and you can just split this into words and count and find out what the most common word is and how many times it occurs. So go ahead and try to do this for a second. Feel free to pause. Actually, don't bother pausing. This is too hard. We should write a program for this. It's not easy. Humans don't like this. It makes you concentrate. And so here is a counting pattern where we're going to take a line, and then later we'll read this in a file. And so this is just an adaptation, improvement of the previous thing. So we're going to start with an empty dictionary. We're going to ask for a line of text and read it in. And then we're going to use split. So remember the list of words? Well, what we're going to get here is a list of words. We'll print it out, and we'll run this counting. This is the little loop. For every word in whatever this was, we're going to do this idiom of either adding a new entry or adding one to an existing entry, and then printing that out. So let's take a look at what we get there. So if we run this, we can give it some text, and I've got this will be all one line, and then it splits it into words, and you see that these words here are split, 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 split. I mean, that's strings and splits. Remember, strings and lists and split. And so now the counting is going to go through this list. The clown ran after the, and it's going to build a histogram. The clown, one clown, the up, of these things are going to go up, right? That's this histogram. And then when it's all said and done, we end up with the histogram. And so counts is the dictionary that ends up with a histogram, and we can, by inspection, see, oh, the is the most common word, and there are 7 of those, right? So if we sort of take a look at this, we start out, we make a dictionary, we read in a line of text, the text goes in, and then we split that, and we print the words out, so these are the words, right? Then we have a for loop that's going to loop through all those things, and then produce a dictionary. And when we print the dictionary out, that's what we're going to get. And the is 7, okay? So that's one line of text. That's how you walk across the words in a line of text after you've split the line into separate words. So now we're going to look at ways that you can loop through dictionaries. We just produced a loop that can build a dictionary, but now we're going to look at a dictionary. And so we'll start with a very, very simple example, and then we'll work to a slightly more complex example. So here's a dictionary, just the constant. Chuck is 1, Fred's 42, and Jan's 100. And so we're going to use a definite loop with the for key and counts. Now it doesn't have to mean key, but key is a good name because these are keys and values. K, V, keys and values. I just mentally think of this as keys and values and keys and values. So this iteration variable is going to walk the keys. It's not going to walk the values. It's going to walk the keys. Chuck, Fred, Jan. Not necessarily in that particular order. As you see, it goes Jan, Chuck, Fred, because just because I typed it in this order, it's not like a list. It doesn't stay in that order. It might move around a little bit as we add data to it or as we set the data up. And so you can, in the loop, you can get the key, and so that's what prints out the Chuck, Jan, Chuck, Fred, but then you can also get the corresponding count for each one of these by just pulling it out of the array.
I mean pulling it out of the dictionary, right? And so we can pull out the corresponding value, and so we print out Jan 100, Chuck 1, Fred 2, and that runs this loop 3 times. So if you just use the in and you give a dictionary here, remember all the different things we've been able to put there on the end of a for loop, and dictionary is another thing we can put on, and we get a list of keys. Now there's a couple of methods that allow us to get the keys, and so we have, we can say turn this into a list, and we get a list of the keys. So this is a dictionary, the same dictionary. We get a list of the keys. You can also get a list of the keys by using the keys method. So that's take this dictionary JJJ and give me all the keys, which gives me a list, which is kind of the same thing. And then we can ask for the values, and they give me just then the values extracted out of this dictionary. So that's nice. Now the one thing is that while I said you can't predict the order, if in 2 statements you ask for the keys and then the values, they at least come out in the same order, even though you can't necessarily predict the order that they come out. They come out in the same order. And then there is a third thing that we can do, and that is ask for the items. And we can say, give me the items. And that gives us a list. This is our first really kind of composite combined data structure, where it is a list, a 3-item list, 0, 1, 2, and inside that there is what are called 2 tuples. Jan maps to 100, Chuck maps to 1, Fred maps to 42. Coming up next, we're going to have a whole chapter on that, and so just take a look at that for the moment, and we will come back to that in some detail later. This whole items idea that gives us back a list of key value pairs, because it's not just a list of keys or a list of values, it's actually a list of key value pairs, allows us to write in Python a very clever and elegant loop. What we can do is actually, this items gives us back, each item in the list has a key and a value, and we can actually take 2 iteration variables. For AA, comma BBB, this is 2 iteration variables, and if you're coming from another programming language, this is super cool, and it's a Python only feature. I never have seen another language that's capable of doing something this simple and that elegantly. So what this basically does is says we're going to simultaneously advance these 2 iteration variables. So this is going to be the key and the value, the K and the V. Key and the value is going to be Chuck 1, then they're both going to advance. Fred 42, Jan 100. And so that means in this simple loop, if we just print them out, we're going to get the key value pairs, of course in the order. And so it's sort of AAA and BBB simultaneously walk down these key value pairs. And so that's really pretty, and it makes for a very succinct loop. The syntax is a little sort of disquieting when you first see it, but it's a super elegant thing, and you just have to say items. If you don't say items, you just get the keys. If you say items, you get the key value pairs, and you have to have 2 iteration variables. If you don't have 2 iteration variables and use items, it'll complain and say, what are you doing? I'm giving you 2 things, and you don't have 2 variables to receive them. So 2 iteration variables and items are basically related. Now, we're going to take a look, and this is code that I showed you perhaps many weeks ago about, I said this is a little story about how to read a file and count all the words in the file. And now we're back to it. And at this point, you should understand every single character of this program, every single concept of the program. You should literally stare at this and look at it, code it, play with it until you absolutely understand it. So let's take a look. Again, I showed you this weeks ago. So we're going to ask for a file name. Then we're going to open the file name. Then we're going to make an empty dictionary. Again, this is all stuff you've done before. And then we're going to have an iteration variable that's going to go through the lines in the file. Right? So line is going to go line, line, line. Then we are going to split that line, each line into words. Chop, 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 chop. So that's words is the list of the words in one line. We're inside of a loop that's going to go through all the lines. And then what we're going to do is we're going to have the word iteration iterate through each word in the line. And then what we're going to do is take each word in the line, and we're going to do this histogram. Right? So we're going to, this is going to run not only just for every line, but for every word in every line. So we have a nested loop for every line, then we split it, and then we go across the line. So it's almost like a typewriter where we go ding, ding, and that's what we're doing. Ding, ding, ding. So it's like the outer loop is going down, down, down the lines,
and the inner loop is going across the words, and eventually we are going to see in this last line every single word in the file, and we're going to do the counts get word plus one, which is our magic histogram making line that if you don't remember what that is, go back a couple of slides, I just talked about it. At this point in the code, and it's important to be able to draw these lines, at this point in the code you have the histogram and it's in the variable counts. Now we want to find the largest one. Now we have written loops that can find the largest in a list, but now we want to find the largest value in the key value pairs of a dictionary. So we're going to start with we're going to know what the largest count is and the largest word has that count, and we're going to set them both to none because we're going to prime our loop. We have to prime our loop, and we're going to say to none. And so then we're going to write one of these cool things that says for word comma count. So word and count are going to go through the key value pairs because we've got items here. So it's going to go through the key value pairs, loop through each key value, whatever it was. There could be a million words in here. We're going to go through every one. And what we're going to do is we're going to make sure that big count is the current largest count we've seen so far. And if it's none, well, then we haven't seen anything. Or the count we just read is greater than the big count so far, we are going to jump in. And this is sort of like, oh, this is a new personal best count for this particular data set. And so we're going to remember the word in big word, and we're going to remember the count in big count. So this is just a max loop. It's a maximum loop with the extra thing that we're recording in addition to what count is the largest, what the word that was associated with that count, recording it. So again, this is a starting part of the loop. We're going to do some work, and then when we exit the bottom of this, big word is going to be the word that is the most common, and big count is the number of times. And so if we run a file, we say, oh, in that file, 2 is the most common word, and it's 16 times. If we run the clown file, well, the is the most common word in 7. And so this now and this could have a very large file and give you the most common word. And so that is sort of a really good application of dictionaries. So dictionaries are the most powerful, they're the most powerful collection we've seen so far. It is good to see both lists and dictionaries to understand what collections are. They are things inside of Python that can handle more than one item inside of it, and we'll learn about another collection about tuples in a second.
And let me start by making a new folder. For my Chapter 9 exercise, and then I'm going to go and make an untitled file. That was from the previous one, and I'll do what I always do, print hello, and save it. And save it here into exercise 09 and ex09.py. So now I have a folder that's in my py4e folder, and that happens to be in my desktop. py4e is my folder on my desktop, and now I have all of these subfolders, cd ex08, ls is dir on Windows, ls, oops, I got to go up one, ex09 ls. So I've got that file right there. Now I'm going to want to read some files, and so I'm going to bring some files down, a couple of files, Python for Everybody code 3 intro.txt. So I've got this URL, and I'm going to save it, save page as, and it's really important that I save it in the same folder as I'm going to write my code, just so that when I open this file it knows where it's at. So I've saved that one, and I'm going to also take this clown text. I'll use this to make my life simple, so I have a real short thing that I can show you how it works. And so now if I go back to my terminal, I see I've got exercise 09 Python, intro.txt, and clown.txt. Okay, so let's go back to my text editor and get started. I will prompt for the file name, input, enter file, colon, space. Now I'm going to do something. If the length of the f name that I just read is less than 1, I'm going to say fname equals clown t clown.txt. I do this so that I can just hit enter and it defaults to clown.txt. If I want to give it a different name, I can. So this, if I just hit enter at this prompt, then this will give me a string that's 0 length. So if it's less than 1, I'll just assume that. So let me open that. Handle equals open fname. And let's read through it. For line in handle, we'll strip it. Line equals line.rstrip to take the white space off the right hand side, and then we're going to say print line. Again, I'm not just doing this. I really, when I write code, I just saved it. When I write code, I do these kind of stuff all the time just for my own sanity checking. And so now I'm going to run Python 3 ex09.py just to test that. I'm going to hit enter now, and it's going to assume hopefully clown.txt if it all goes well, and yep, it read one line. Okay, so that part's working. I'll just leave that print statement in. The next thing I want to do is kind of a classic thing where we're going to go read a bunch of lines and then go horizontally across those lines in words. So I'm going to split that. WDS equals line dot split and print WDS. So I'll print that, and I'm going to save it and test it. I really love to test things over and over. There's the actual line. This file, clown.txt, only has one line, and it breaks it into words, and so I have those words. Let's just run it again with intro.txt. So this will have a lot of lines, line, lots of lines. Every line prints out the line and then prints out the words that we split it into. Okay, so now one of the things that I do here is I want to believe, now I sort of can believe everything from here up. Like, oh, it's going to open the file, it's going to read through the lines, and going to split them into words. And so then I'll just kind of behind it, I'll just say, okay, I'll just comment that out. Now I need another for loop for W in WDS. Now words is a Python list and has some number of words in it, 0 or 12 or whatever was on the line. And now I'm going to print out the word. Okay, and so now it will go through that horizontally. Now I'll just do clown.txt so that you see I'm not printing the line out. That's the words that have been parsed split from the line. And now we got this loop. Now, one of the things that's interesting is just to make sure that you're going through all the words. And I like a print statement here to know that W is going to successively take on literally all the words of this file. So if I comment this print statement out and I run it again, clown.txt, that for loop starting from here is every word in that file, which happens to only be one line. But now if I do the same thing for intro.txt, it's just going to go through the words. And in a sense, by nesting these two loops, we're going to hit all the lines. And that's a lot of stuff, but it hit all of the lines, all the words, and away we go. Okay, so here's where a dictionary comes in. I'm going to make a variable called di for dictionary, and I'm going to say give me a dictionary. Now dict is not something you can choose. That's saying that's defining the type of dictionary. Di is a variable that I chose. Okay, so the key thing to this dictionary is we're going to make a counter, and we're going to use W, the word, absorb, elegant, whatever, and we're going to use that as the index. So the simple thing to do is to say if W is in di, then we can say the dictionary sub the word, which is our key in the key value store of the dictionary, is equal to the value that we had before in that area, d sub W plus 1. And if it's not in there, else di sub W equals 1. And I'm going to print print new So every time we see a new word, it's going to say new. And I'm going to also then print W and the current value of the counter for W as it's going through. Now notice how far in I'm indented. This is all part of this inner loop. So this is the loop that's going to run every single word. Okay? And I'm going to run this first with clown. So it runs slowly. Okay, so we saw the was new, and the count is 1. Clown is new, count is 1. Ran is new, the count is 1. After is new, the count is 1. Now we saw the again, but now we made the count be 2. Let's print here. I'll say existing. So you can kind of see it. Now in the print, I'm printing this. Let's make it even a little more verbose. Print W. And then I will make it so it prints the word before and the count after, and then whether it's existing or new. So we're put a lot of print statements in. Print statements are cheap. Okay, so now we see the word the. It's the first time we see it, and we set it to 1. We see the clown. It's the first time we see it, we set it to 1. We see ran, new, 1. Later on, we see the. It's already in. So existing means it was already in the dictionary. W as a key was already in the dictionary. Okay, and so that's why we added 1 to it. So the old value was 1, and then we added di sub the equals di sub the equals di sub the plus 1. W is the string the, the. That's what that string is. Okay, and so we've made it all the way through, and you see the in this one line occurred ultimately 7 times. So now I want to print out the contents of this dictionary at the very end of both loops. So I got to de-indent twice, and so that will give us the counts. And so this is what we get when it's all said and done. The happened 7 times, but it just worked through its way through. Okay? So you got that. Now, this is a pretty verbose way of doing this, but I did it sort of the slow way to show that there are 2 situations. If it's already there, you increment it, and if it's not there, you set it to 1, effectively inserting it, right? So you insert it and set it to 1 with this di sub the equals 1. Okay? But let's get a little less verbose here, get rid of some of these print statements because we kind of covered all that. Get rid of this line. And go back to printing W and DIW at the end. We'll leave that one in. So what I want to do is I want to look at this bit of code right here. This if W in D I else. We do this so much with dictionaries that there is an easy mechanism to do this that combines these 4 lines into a single kind of contraction. And so I'm going to do this. I'm going to print, let's put 2 stars out, then the word and di.get of the word, comma, negative 99. Okay, and so this di.get of the word is the important part. The way it is this is a dictionary. .get says in its first parameter is the key to look up, which is word like the or fell or clown or whatever, and 99 is the default value that we get if the key doesn't exist. So this is in effect an if then else. Right? This little di.get w99 negative 99 is, if it's in there, do one thing. If it's not in there, do something else. Okay, so let me show you how this works, and you'll see that the 99 will happen when okay. So the first time we see the, get returns 99. Right? So let's move it over here. The first time we see the is not in the dictionary. So this di.get of the word the in the dictionary gives us back the negative 99. Okay? And this still is working, and so the is 1, clown is whatever, but away we go. Okay, let's do it this way. Let me comment this out. Let me comment this one out and run it again so it's a little clearer what's going on. Okay, so the first time we see the is not in the dictionary. The first time we see clown, and we know it's negative 99. But here we asked for it, and the is 1 because we'd seen it before. And so that's just this get mechanism allows us to get the new value, or get a value out if the key exists, and specify a default if it's not there. So I'm going to go old count equals di.get w, 90, 0. So instead of using 99 here, I'm going to just get rid of all this. Is what I'm saying is look up in this dictionary. Get is a function that's part of all dictionaries. Look up using the key w, which is the, and if I don't get it, give me back 0. And so I'm going to say print word, comma, old, comma, old count. And now what I can say, whatever the old count is, it's either the value that was in there or 0. And now I can say new count equals old count and now, let's see, new count, and I can say dictionary sub word is equal to new count. So instead, I'm going to get rid of this if then else then. This is basically saying look up the old count that we have. If you don't find one, use a 0. We'll print that out. And then I'm going to say afterwards, I'll print the new count. Now, and so we'll print the old count. Here are some of these blanks. Print the old count. And you can see the old count with the, because the doesn't exist, was 0. The new one's 1. Clown's old is 0. New is 1. Clown's old ran, old 0. But now we get to the, its old count was 1, and now its new count is 2. Okay? So by using this get and saying if we don't find it, we'll assume the count is 0. That makes a lot of sense, right? You know, if not there, the count is 0. If the key is not there, the count is 0. Okay? So that's what this line does. If get the value from under the key associated with the key, or give me 0 back. And then I can take that old number and just add 1 to it and then stick it back in. Now this is ultimately not how we tend to do it. Okay? We tend to blend this all into one big long statement. di sub w equals this part plus 1. Okay, so that says get the old value from this key or 0 and then add 1 to it, because that really combines all of these lines into a single line. Okay, so I'm going to delete them now. And now we've combined this all into one, what effectively is an idiom. Retrieve, create, update, counter, all in one line. I'll still print out, in this case I'll just say di sub w, and then we'll see the counter. Okay, and so now I'll run this. We don't, we have a new, but now we see it the second time it's 2, and so we see car the first time, we see that the second time, we see car, the third time, we see car the second time, and away we go. Okay, and so That's pretty straightforward. And so it really kind of, a typo there. So let's just get rid of that and run it with the clown stuff, and we get the right data there. And let's run it with intro.txt. And there we go. Okay? And so it's tearing out a bunch of words and giving us a dictionary. So that was a lot of work to get to this line 16 that has the dictionary in it. Now we want to find the most common word. And so we're going to loop through this dictionary. And part of it is like, once we printed this dictionary out and we verified that it's right, don't worry too much about the code up here, right? Matter of fact, I can take out some of these print statements, and we can kind of trust all this. And so now we're going to work on this. Okay, now we want to find the most common word. Now this is like a maximum loop. So if you recall, we have a whole set of key value pairs. Communicate goes to 2, is to 2. Skills is 3. So we have these key value pairs, and we're going to loop through and look for the maximum. Now, in a dictionary, we can loop through the key value pairs with the following syntax. For, I would call these variables k and v for key and value, but in the dictionary's name dot items. And items is a method inside of all dictionaries that says give me the key value pairs, and we need 2 iteration variables. So this is like an assignment statement for k and v. K and v take on the successive values for the key and the value. Okay? So if I just now print k comma v, and I'll take this print statement out and then run the code on, oops, what I forgot to, oh, I fell back into my Python 2 days. Need parentheses for my print. So there's clown, and it just prints it out. And it's kind of the same thing, except it's pretty, where we're putting each one on a line. Okay, so the v is the value. So we're looking for the largest value. Oops. So the thing is, we know that the values are always numbers that are greater than 1. So I'm gonna do kind of a quickie maximum loop. Largest equals -1. Now in previous times we've seen that this is a bad assumption, but because we know these are counters that are always positive, it turns out this is not a bad idea. And so I can say if the value is greater than the largest we've seen so far, largest equals the value. Okay, and when that loop is all done, we can print the largest. Okay, and so this is just a max loop, and we're using this value. That's the number. The value is the second thing. Oops. Can't type Python. Oh, it's a typo. Yeah, I'm not using value, I'm using v. So largest equals v. Let's try it again. Okay, so we're all done with 7. So these were the things that we were looking for, and it was looking for the maximum, and it just dutifully found 7 was the largest. But we also want to know what the word is. And so what we can say here is we can say the word is none, meaning it's just like we don't know what the word is. And then whenever we catch this new largest number, we say the word equals W. So I like to think of this as capture, remember the word that was largest. Right? That's what I'm doing. Remember. Right? That's R-E-M-E-M-B-E-R. There we go. So we're gonna this trick here is not only knowing what the largest number was, but the word that was associated with the largest number. So now I can print out at the end the word and the largest, and that's the count. Okay, and so now we know that. Oops, did we make a mistake here? Okay, that does not look good because it says car and 7. If V is greater than the largest, oh, it's not W. I used a really bad variable. See, that's the old value there. There we go. It's K, which is the key. Key. I was going to say that was quite the bug. See what happened there? I had this as W, and it just happened to be it was the last word on the file. Car, the last word in the file, because I used a wrong variable. Right? No, little mistakes, little mistakes. The and 7. Okay, so let's get rid of this print statement because we kind of know what's going on here. And away we go, and this should now work if we run it. We can even get rid of the word done here. There we go, the 7. Now, the cool thing about this is this code runs just as easily with one line of code or the intro of the book, intro.txt, and not surprisingly, the is still the most common word in the introduction.txt. I seem to like that word, and it's 226 times. Okay, and so that is the basic pattern of reading some. This is just a.
And when you want to make a connection across the internet to the far end, you say, oh, hey, dear socket, extend yourself across the internet. Make the phone call to this host, data.pr4e.org, and on that port 80. So that's making the phone call. This is like the phone number, and this is like the phone extension. So that's, we haven't sent any data yet. We have simply rung the phone of a process, hopefully living on port 80. If it's there, great. This might blow up. This one here won't blow up, but this line here could blow up. If there's nothing sitting on that process, it would come back and say, oh, you tried to call, you got no answer. That's a legitimate thing to happen. Maybe you don't have a network connection, or maybe that service is down on that server, or the whole server's down. But so it's kind of amazing that we're sitting here in Python, and in 3 lines we have probably 500,000 engineers who built this thing called the internet, all these protocols and all this software, and we just made use of it in 3 lines of Python. And I guess this is one of the reasons that people absolutely love Python. Absolutely love Python. So now that we have a socket, we have to ask ourselves, what kind of data are we going to send, and then what kind of data are we going to expect to receive across that socket? So now we have a socket, we are going to talk about what we're going to do with it, right? So the socket basically functions at this level. Your application is saying, make me a socket, which is sort of this endpoint, and then the connect actually connects to an application on the far side. And there's a port involved, so that might be port 80. And this is the far host, and that could be www.py4e.org or data.py4e.org. Okay, and so the socket is solving this, and the question then is, what are we going to send and what are we going to expect to get back? And that's what we call the application protocol. So we know that these two have made a phone call. It's no different than making the phone call and saying, you know, hello, right? And everyone knows that when the phone rings and you pick it up, you're supposed to say hello. And that's part of our protocol. So who talks first, right? So the dominant protocol that we use on this in this section is the HTTP protocol. The key is hypertext transfer protocol. It's dominant. It's really easy to use. That's why I use it as an example. But realize that there are many others like mail and file transfer and remote login and all kinds of other protocols. Each is a different application protocol. They all use sort of sockets at their lower level. But then on top of that, they layer the rules of the road for retrieving hypertext web pages. And we have used these for all kinds of other things. So the protocol, like I said, is like who answers the phone first, what do they say, what happens if the person doesn't answer right, can you hear me now, those kinds of things. And it's a real simple thing, and all you really need to do is so that both sides can agree, you have to write a thing that's like the rules in the middle and say, okay, everybody, as long as we all do this, we'll be fine. It's as simple as picking on which side of the road the cars can drive on. It works fine no matter which side, but if each car randomly picked, it would be really kind of a mess. So if you look at the typical URL, and this is one of the things that the web innovators in 1980 really invented that was wonderful, and it seems second nature today, but in 1990 it was rather revolutionary in that these uniform resource locators included in themselves a protocol, the host to connect to, and the document to retrieve. So this is one of the clever ideas that the web came up with, because we used to have to pick a program like FTP or Telnet or whatever, SMTP, then we had to go to the right host, and then we had to talk to that host a certain way. So in HTTP, it's a really simple protocol invented in 1989 and 1990 by Tim Berners-Lee and Robert Caillou at CERN. And they created a protocol that we have grown to know and love and use for way more than retrieving documents, as we'll see in the upcoming chapters. So we're going to talk a little bit about what happens when you click on a page that has a link. Now, there's all kind of fancy stuff that can go on, but this is the basics. And so let's just imagine for the moment you are sitting looking at a web page, drchuck.com/page1, and inside that there is a hyperlink. It is a indication that says when you clicked on this page, go to a different page. And in that you see the name of the page that you're supposed to go to. So we click on this link, and that is a browser. This is an application, this is a process or an app that's running on your computer. This is the browser, okay? And when the browser sees the click inside your computer, then the browser makes a connection to port 80 on the web server, drchuck.com, and sends the request. This request that it sends is precisely specified by a standard, which we will see in a second. Then the web server does some magic work. Oops, let's go back. Then the web server does some magic work in here, reads some files, runs some code, does whatever, constructs an answer to our phone call, and sends it back. And it sends, in this case, back a web page in the format of HTML, the hypertext markup language, which is different than HTTP, which is the protocol that we're exchanging. HTML is the format of the document we're getting back. And in this has an anchor tag, href, and the end of anchor tag, and some highlighted text. And now your browser gets this back and then renders it according to the rules of HTML and CSS and JavaScript, etc., parses it, and then makes a pretty web page. And this web page happens to have a link back to the first page, and if you click there, it will do this over and over and over again. And that is the request response cycle. And that's governed by a series of internet standards. These are standards that were built from the 60s, 70s, 80s, and 90s and continue to this day by a group called the Internet Engineering Task Force, or IETF. The documents they produce are called RFCs, which stands for Request for Comments. The word RFC is kind of like a sort of joke, as it were. They're trying to be kind of funny in that, funny is not the right word. It's ironic in that they're trying to say, even some of the protocols of the internet that we've used for several decades, they're always interested in improvements, and that's what the RFC stands for, and they're all named RFC-whatever. And if we were going to cruise around, we could find some various RFCs, and this is RFC 2616. It might have been revised since then, but this is like a document, and this is what they look like. Hypertext Transfer Protocol version 1. And so you're reading this document, you're going to write a browser, and you want to talk to the application protocol that is HTTP. This is one of many documents that helps define what HTTP is. So if you look down and said, oh, here's what a request looks like. This is how I'm going to get a document from the server. And you keep reading and you keep reading, and it says you're supposed to have the request method with a space, with the request URI, the request method with a space, with the URI with a space, the HTTP version, and the carriage return the line feed. That's what it's saying. And so it looks kind of like this, right? We say get the document followed by a space. There's got to be one space. You do two spaces and it's going to be quite frustrating, okay? And so this is an example that you can run on a number of on Linux operating systems and Macintosh operating systems with no changes. If you install Telnet on your Windows box, you should be able to run something like this as well. So Telnet is a program that we used in the old days. It used to be how we logged into servers, but because it doesn't encrypt your data back and forth, we don't use it anymore. But it basically is a program that can open a socket to a host on a port. And I'm saying Telnet to this host on port 80. And at this point, I am connected, and whatever I type on my keyboard is going to be sent to that server. Now, if you're doing this, you probably want to cut and paste this really fast, because if you take too long, most web servers will be like, you're a human. I don't want to talk to humans. I want to talk to programs. So remember to type this fast enough, and then you have to hit Enter twice. So you have to have a blank line here. Just type this exactly as it's shown, and then you will get back the server. If you do it right, the server, and the server is properly configured, the server will give you back some headers. And this is metadata about the document you're going to get. For example, it's saying it's got text/HTML, which means that the remaining stuff is going to be in HTML, hypertext markup language. It has a blank line, and then the actual document, and then the connection is closed. And so if you do this, you can set this up in a way that you can run this on your own computer, and in effect, hack through the back door a web server. Now, you can't hack the secure web servers, and mail servers used to be easy to hack, but they're harder to hack now because they challenge you for information. But part of the reason I'm so obsessed with the command line is this is how real hackers work, and they know how to talk some of these protocols more directly. And so we think of this beautiful, sophisticated application talking to some other thing, and it's all pretty, and we got wonderful clicky buttons and nice usability. But the reality is, like in the Matrix Reloaded here, the kinds of things that really talented hackers are doing use command lines, and they really know what's going on, and that's how they do it. They understand what's going on better than the developers of the computers that are trying to be resistant to the hacking. So I come from a long line of using the command line, and that's why I encourage you to use the command line in this course. So the next thing we're going to do is we're going to go up into the application layer, and instead of typing those commands by hand, we're going to actually send them from Python and write a very simple Python web browser. In this section, we're going to write a web browser using Python. So we've already got a socket. We know how to write a socket. In the previous section, we played with the protocol and used Telnet to do it by hand, and now we're going to do it in Python. And what you're going to find is it's not that hard. So here we go. So the first three lines of this program: import socket, make the socket. Remember, the socket isn't really got the connection. So when you make the socket, again, we're going to make a stream-based socket, and it's suitable for going across the internet. The connection, it's like ring, phone call, connect to data.pr4e.org and port 80. And so that basically says extend the socket across and connect to a web server. And so there's got to be a piece of software running, and this will blow up if the software is not running. Okay? So then, now we've got a phone. We've made a phone call. Now, whether or not the remote side says hello or not is up to the application protocol. And in this case, the web servers say nothing, and they wait for you to talk first. So we're the web browser in this case, and so we're going to talk first. And we know what, because we read the documentation, we know that we're going to send get blah 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 space blah 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 ht1, and then two new lines: return, return. Remember, you had to have a blank line. We'll talk a little bit about this encode. It's preparing the data to go across the internet, and then we say send it. And so this basically takes that little string and sends it across the network, and then this piece of software is waiting for it. And then the software goes and reads a file or does some other stuff, and then it starts sending us data back, which we can then choose to receive. So now I write a real simple loop. We're going to receive these things 512 characters at a time. So we're going to loop through, receiving 512 each time. And if we get 0 characters, that means it's end of the stream. The stream is closed. And if you look at the little example from the previous one, you saw connection closed. When the connection is closed, we get an indication that it is because we ask for some data and we get 0 data. Otherwise, if there might be more data, this will wait. If the network is slow, you'll see if you do a print statement in here, you will see that this will pause from time to time on a really slow network. If your network is fast, it'll just go blank and it'll be so fast it won't matter. But this is how we go. So this is basically until the entire socket, until the socket is closed, we're going to read this data. And because this data is coming from the outside world, we have to decode it before we print it. And then when we're all done, we break out of here and we close the socket. So literally, that is an entire web browser written in 10 lines of Python. And again, this is why everybody loves Python. So this is what this program will show if you run. The get is sent. It looks exactly like doing it by hand. You get some headers. Again, this is metadata that tells you something about the file. In this case, one of the important things is what kind of thing is coming next. There's always a blank line as a break between the headers and the actual data, the metadata and the data. And then here is the actual text of that romeo.txt file. And then it's going to run this, going to print data.decode. All this is coming from the print statement. If you were going to parse this, you have to know that you're going to read the headers up to a blank line. The blank line is your indication as a software developer that the headers have stopped and the actual text begins, and you know the syntax. This actually could be a JPEG or a PNG or some kind of image, right? And this data would here look like blah. So if you type this and you change that code to actually go retrieve a JPEG URL, gibberish will come out, okay? And so that's exactly what you will see. And so now you have built a very simple web browser.
Of code here. So if I do an ls, you'll see I got all these files here. And so we'll just leave those there. And so this is the one I want to work through right now, is this socket1.py code. And basically what we're doing here is we're simulating what is going to happen in a web browser. And the cool thing about the HTML, the HTTP protocol, is that we can do this by hand. And I'm actually going to hack this HTTP protocol. This is going to go to data.pr4e.org and retrieve a document. And so I'm going to do telnet. Now you can do this on a Mac and Linux, and if you put telnet on a Windows box, you can do it here, data.pr4e.org. And I want to talk to port 80, and the port 80 is a different port. It's a non-standard port, but what we're doing here is talking to the HTTP port. And so I'm going to be able to hand send commands to the web server and retrieve a document. So I'm going to cut, I've already copied this string, this get http romeo.txt. I'm copying that into my buffer because if I wait too long, this won't work. So here I go, and now I'm going to type that, and I have to hit enter twice. And that literally was the HTTP protocol. What I typed there was the HTTP protocol, and the web server responds with some metadata about the document, how much data there is, the kind of data is there. A blank line separates the header information from the body of the document. If I was to go to this in a browser, right there, you would see, and if I turned on Developer Console and I went to the network, let's make this a little bit bigger, you would see that it retrieves this file romeo.txt, and it gets back that it tells us, it shows us the headers, and it shows us the response. And so this is all the same way of doing the same thing, and that is how to do the HTTP protocol. Okay? But now we're going to do this in Python, and so here's the code we're going to write. So we're going to import the socket library, and we're going to make a socket. Now this doesn't actually make a connection. Think of a socket as a file handle that doesn't have any data associated with it yet. And then what we're going to do is we're going to reach out and connect that socket to a destination across the internet with the domain name of data.pr4e.org. And the second parameter in this tuple, this is a function call with a single tuple as a parameter. And so tuple sub 0 is data.pr4e.org, and tuple sub 1 is the 80, which says I want to talk to port 80. That could fail. It will make the connection, and And if the port 80 is there, away it goes. And then we're going to actually send the HTTP command. So get, this is the HTTP rules, followed by an end of line, followed by a blank line. So you saw me do this. This was what I typed here, and then I had to type a blank line. Now if you want to go read the RFCs for how to do this, you can figure this out. So the only other thing that's kind of weird here is we have to add this dot encode. And that's because there are strings inside of Python that are in Unicode, and we have to send them out as what's called UTF-8. And encode converts from Unicode internally to UTF-8. So this command is a set of UTF-8 bytes that we're then going to send. It still has that same set of characters in it, and now we're going to send it. And that's after we've made the connection, we're going to send these two things, and then we're going to wait. And my sock is like a file handler at that point because it's been opened and we've sent data. The HTTP protocol told us what we had to send and the fact that we did have to send it. So now I have just a simple while loop, and I'm going to ask up to 512 characters and receive up to 512 characters and get that back. If I will know that this is the end of file if I got no data back. So if the length of the data, the byte array that I got back is less than 1, then I'm going to quit. Otherwise, I'm going to print the data, and I'm going to use this decode, which is kind of the opposite of this encode. What I'm getting is UTF-8 encoded data, most likely, and decode basically converts it to the internal format called Unicode that runs inside. And so this is going to run a bunch of times, pulling in the blocks, basically 512, up to 512 characters at a time, printing it out, and then when it's all said and done, we will close that connection. And so it's not too exciting. Python 3 socket 1.py, and you'll see that it's just going to, Python is now going to do what I did by hand. Now of course the interesting thing is these are all in strings, right? And so this way we could write code that does stuff with this, but all we're really trying to do in this, probably better ways of expressing it than subclassing. So here's a bit of code. Let's take a look at this. This code's unchanged. It's the party animal code that we've been saying all along. It's the one that we construct and put a name in. And now what we're going to do is extend it. And so you'll notice that this code down here is the part that's doing the extending. So we're making a new class, football fan, and by putting in parentheses before the colon, party animal, that says football fan inherits everything that is party animal, meaning the X, the name, the init, the party, all those methods and data are sitting there. And now we're going to add a new variable. So football fan has, in addition to all those other variables, it has points, and it has a touchdown method. And self points is added. We add 7 of the points, and then we call the party, and that does that. So this is calling this method because football fan includes X, name, and party, and init, and everything, and all this stuff. This constructor. So this football fan is really an amalgamation of all these things together. Party animal is just this stuff, right? And so we still have 2 classes. We don't just have one. We didn't erase the party animal class. And so if we take a look at the code that we can run here, we can say, oh, okay, let's make a party animal, Sally. And so that constructs an object like this and then stores that in S. And with an X starting out at 0. And then we call S party. Better change that color. Starts out at 0, and then we call the party method, and that changes it to 1. Okay, and so this bit of code, it's as if this part doesn't matter at all because it is a party animal, it's not a football fan. But now if we take a look at this code down here, take this code down here, we're going to construct a football fan and pass in Jim. But football fan has no underscore init, so that actually uses the underscore init from party animal because we extended party animal to make football fan. So we inherited all of the good that was in there. So there it's going to make a name, a variable X, which is going to start at 0, a variable name that's going to have Jim in it, and a variable points is going to have a 0 in it. So this J variable has more things in it than the S variable has. And so we can call the J party, and if we call J party, that goes here and adds 1 to X, right? So that adds 1 to X, and then we call J touchdown. Well, that comes down in here and adds 7 to the points, right?
and then calls party within us. And so self.party is the current object, i.e. self and J are the same thing, right? Self.party, and then it goes up here and passes self in, and it adds 1 to the X, in this case of this J variable. So this becomes 2. And that's where it prints out, 7 and 2, and away you go. And so it's a way for you to kind of take all this stuff and stuff it into a class by making a new class and just add the extending bits, the bits that are in addition to the other stuff. So like I said, inheritance is a powerful and wonderful concept. It's a form of, excellent form of reuse, but basically the whole purpose of this lecture was so that I could in the future just use these words and you would understand them, as compared to, I just want to say method. And I've been saying method all along, and it's high time that I defined it. So let's just review one last time. Class is a template. It is not actually a thing, it is a shape of a thing. And we define it and say, when we make one of these things, it's going to have these variables in it, it's going to have these methods in it. Attributes, variables within a class. Method is a function that's inside of a class. Object is once we construct a class, we get back an object. And so object here is the snowman cookies. Class is the snowman cookie cutter. And a constructor is a bit of code that sets up our object, our instance, when it first is created. And inheritance is this ability to create a new class, but take all and import and affect all the capabilities of an existing class. So, object-oriented is awesome. For the rest of this class, we're not going to write any object code, we're not going to use class at all, but we are going to use objects, and literally you've been using objects from the beginning of this course. As soon as you said print, whoops, as soon as you said, x equals high, that's an object. And as soon as you said x.upper, you were calling a method, right? You've been calling a method all along. When you're doing something like fh equals open, this thing you're getting back, that's an object. And then you do fh.read or whatever. You're calling a method in the dot operator. So you've been using objects all along. I now am just finally explaining to you when I say call the read method or call the upper method, or what's this little dot and why is that there? So again, it's time for us to understand that, but it will take you a long time before you encounter a problem that's large enough where, as part of your solution, you're going to make a new object. But when you do, it's really a powerful thing. I mean, it's a really bad idea for me as a teacher to say, oh, write a bunch of objects. It's like, it's premature for that. It's later is when you will actually learn how to use objects, and you'll be like, oh, thank heaven that these objects are here. Okay? So, that's all for now. Thanks for listening. See you on the net. Hello, and welcome to our chapter on databases. We're going to learn a lot in this chapter, learn a whole new programming language, SQL, and learn how to use that. So you're going to need a new piece of software to run all of the exercises that I'm going to do called SQLite Browser. We're using a database called SQLite. Go ahead and download this. You might have to pause and come back if you like. Go to sqlitebrowser.org and download it and install it. While you're doing that, we'll talk a little bit about the history. So in the old days, 1960s, 1970s, I started doing computing in 1975. We didn't have a lot of storage. I mean, this is, 16 gigabytes right here, and, we didn't even have megabytes. I mean, the computer I had a few megabytes of stuff. So we didn't have a lot of disk drives, and so permanent storage was often sequential. And these tape drives that we had, tapes and tape drives were the scalable part of storage, because you could just make more tapes and you could rack them up, and so that was our way of greatly increasing the storage of the computer. The problem they had is they were sequential. You read it, it advances, read it, advance, read and advance. Now, interestingly, we've been writing programs that do this, that everything we've written so far pretty much reads the whole file, reads the whole web page, reads this, everything we read it either a loop or read the whole thing. And that's because we have plenty of memory, but we're still reading sequentially. And And so the way you would do this when you didn't have enough spinning storage or online storage is you'd use offline storage, but the trick would be that you would sort it. So let's imagine that you're a bank and you have a bunch of accounts, only a few of which are active on any day, and you have a tape that has, in account number order from low to high, the prior balance, last night's balance of every one of your bank accounts, and then you do all the transactions and you record how much money was taken in or out for each account number, and then you sort those transactions. And then what you do is what we call a sequential master update, and that is you would write a program that would read the first transaction and hold on to it. Say, okay, this is account 45. Then it would read the first account, like 1, and it would copy 1, and then it'd read 2, and read like 7, 8, 42, 43, then it would read like 44, and then we'd read 45, but it would change that and write the new 45 and read the next thing. And so this might be 60. And it would read a bunch of stuff and copy a bunch of stuff, and then it would finally get to 60, and it would merge the add or subtract. And so the old balance ended up here, and the new balance did here. And you had to only make one pass through the data. So it was super efficient. So we had all these mechanisms to sort. We used to do punch cards and have sorters and all these things. And then those things would run for hours. And if you watch old TV shows, these tapes are spinning and these things are running back and forth. These are simply reading and writing tapes. And that's how we did a lot of data processing, because we could store far more on a tape drive than we could on a disk. And with racks of tape drives, we could scale the storage that our computers had. And so that's the way we did data processing, but it meant that the only way you knew what the old balance was it was the balance as of this morning before your bank started. You don't know what the balance was for the day, and that led to things like you can never you can never withdraw more than $100 a day or something like that, because you don't know what the old balance was, or you might go withdraw $100 at a couple of different branches, and so they weren't able to look your stuff up right away. Now, it didn't take long until the disk drives got better and better and better, and you could store the entire accounts, all the accounts and their current balances, on computers. And then the problem becomes is what happens if sort of in the middle of the afternoon you want to update a balance? Well, do you want to read all your data and then write a brand new one? And say that takes like 10 minutes. That means for that 10 minutes, only one person can be updating their bank balance. And so because we could randomly access this data, we didn't have to read it all sequentially. The trick is how do you spread the data out, and then how do you make it so you can change a balance? This is of course second nature today, but how do you make it so you change the balance here without changing the balance there, and you can have multiple people going simultaneously to these things, and make sure that you can't say to withdraw money at 2 different locations simultaneously and somehow have your bank balance get corrupted by that. So there's a lot of debate on how to do that. And in early days, we just did sequential master update. But increasingly, we wanted to make better use of the random nature of our computers and our storage. And so that's what led to databases. Databases are the science of how you make use of rotating random access data, permanent data, in a way that allows you to read, modify, and update that simultaneously from many different locations and yet keep the data completely consistent. And so this led to let's do that. Let's bring that baby right up and turn this into a single quote. That's short enough, right? But triple quote is just, this one here is a little longer, so I'll use triple quote. So we're going to drop table. That's going to do nothing first time through. Then we're going to do a create table. Now sometimes your application will have like a README or something. It says go run these commands to set the database up, but we're able to just set this database up in this particular application. We'll see later ones where we're going to leave the database and not start it fresh. And in this one we can do the same. And so, but in this one we could, but we're just going to start fresh by dropping the table. So we'll create it. We're going to have a email and an account. We're going to basically what we're doing here is we're really going to pretend that this is a dictionary. If you recall, when I said dictionary is like an in-memory database. Well, now we're using a database to do a database, but the first thing we're going to do here is pretend it's a dictionary. So that's a little crazy. So these next lines of code hopefully are pretty familiar to you, right? Get a file name, loop through it,
check to see if it's grab inbox short by default, so we can press the enter key and then loop through it, right? And so this little part right here, this is our basic loop that we're doing, and so that is pretty normal. And if we look at this line right here, that line right there is the line that is that line right there makes sure that we can only get the from lines. We've done that a bunch of times, and we're going to split it. We're not going to strip the right because the split's going to take care of that. And then we're going to grab the email address, which of course in the from line is the second part, and then we will have that. So now we're going to do some database. So the first thing we're going to do, this bit right here is kind of like the dictionary part. So the first thing that we're going to do is we're going to select count from our database, that is an integer, where email equals. And this part right here bears some explaining. This is going to be c7@umich.edu or whatever. Now, it is dangerous to put those strings, especially from user-entered data, into your SQL. You technically could. I could make this be a email equals single quote c7@umich.edu. I'd have to escape the quotes and stuff. But this question mark is a placeholder. And this is a way to basically make sure that we don't allow SQL injection. Go Google SQL injection to get a sense of what that is. It's more of an issue in online applications, but in this application we're just being good. And so the way this works is, this is a placeholder in this SQL that will ultimately be replaced by this. Now you could have several question marks. We only have one in here. And so you give a tuple. And if we just put email, it won't turn into a tuple. This is a one tuple basically. This little weird parenthesis email, comma, parenthesis, that is a tuple with only one thing in it, and that's just the weird Python syntax. It's rare that I apologize for Python syntax, but that's a little bit less than pretty, but it's okay. It's a tuple. And normally if there were like two of these, then there would be email, name, da 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 da. Okay? So this cur.execute is actually not really retrieving the data. In a way, it's looking at the SQL and making sure that maybe it might verify that the table name is right, or if there's any syntax errors, etc., etc. So this actually is not really reading the data. So, but we have prepared this cursor. This is kind of like the opening of a file, but what we're opening is a record set. We're opening a set of records that are going to, be this wherever it's true. So it's like we're going to read this like a file. Now later things will loop through this, but we're only going to say, hey, grab that first one, right? We could have even put maybe a limit clause on there or something. Grab the first one and give it back in row. And so row is going to be the information that we get from the database. And so that is, if there are no records that meet this, then row is going to be none. So here's kind of, again, like the get. Here's like the get, where if the row wasn't there, because the way we're doing this is we're going to end up with this row in the database. Here's this database, and there's going to be two columns, and there's a bunch of rows. And then here's going to be CSEV 4 and Jen 3 and Stephen 6, right? So these are the counts. And so we're grabbing this variable out, if it's CSEV that we're grabbing, and that's going to come into here, right? That's going to show up in here. And that row is actually, it turns out that the row is a list, but we're only getting one thing. And what we really are doing is if we search through and we got through and there was nothing, then row is none means that there was no, and we're seeing like Chen's for the first time, and we have to insert it. So if row is none, we're going to run an insert statement, insert into counts, email count. Now we've got to set it to 1 because it's the first time we've seen it. So values, and then again the question mark. The question mark basically says, hey, I'm going to have a value in this tuple, and there's an ordering to the tuple, and so there's only one question here, one question mark placeholder here, and then 1 is the initial count. So email question mark count 1, away we go. And so then we have, again, we have a tuple that gives to this execute statement, just like in that execute statement, the corresponding sort of strings or integers that are to be replaced by each of the questions.
So when this runs, there's going to be a new record, and there's going to be a 1 that's put in there into that new record. If, on the other hand, we pull back a row that exists, we're going to get this 4 number. And you might think we want to take this 4 number and add it, but in databases it's always better to do an update, because there might be multiple applications that are talking to this database at the same time. So no matter what update does, is in a single atomic operation, it turns whatever this number is into 1 higher, and we don't have to worry about other pieces of code potentially modifying it. Now in this case, we don't have to worry about that because we're the only piece of code, but using update to increment something is way better than reading the value and then doing an update to adding 1 inside of Python and then updating the new value, that's 2 SQL statements, but it's also not atomic, okay? So if the row is none, if the row exists, we just know that it exists, and we just want to add 1 to the number. We do have the number sitting here in the row variable, but we don't need it. And so we're going to say update counts, set count equals count plus 1, column name, where email equals, and then another placeholder, and then another tuple for the question mark, okay? And so that's what this little bit of code does. That is kind of the read it, parse it, check to see if it's there. If it's not, insert it. If it is, update it. And so then we see this con commit. And this con commit, basically the way it works is that the database is efficiently keeping some of the information in memory, and at some point it has to write all that stuff out to disk. So you can choose at times where you put this commit. Right now we're going to commit every time through this loop, but you might commit every 10th time through the loop, because the commit will take some time because it forces everything to be written to disk, and these can run really fast, and the commit is the slowest part here. So sometimes we do things like commit every 10th record or every 100th record. If it's an online system, which is not what this is, you have to commit at the end of every sort of screen paint. But for this kind of a system, because we're putting so much in, this is kind of a bulk insert, we might come up with a thing where we, every 10th time we do a commit. But ultimately what this will do when this is running is it will build up slowly but surely, adding new records, and then 1, 1, and then it'll be a 2 and a 3 and all these things, and add another one, that'll be 1. It'll do this thing, right? And then at the end of the day, that is what's going to be in the database. Now, so let's take a look what's in the database, and now we can actually read the database. And so in the database, we're going to run a select, and we're going to select the email and the count from counts, order by count, descending. So look at that, isn't that cool? We're getting in the top 10 because databases are good at sorting, and they're good at all these other things. So we're going to then execute this, and then we're going to ask for the rows one at a time, and the rows are going to be a tuple, and row sub 0 will be email, and row sub 1 will be count. So we run all this stuff, and then we close the connection, and away we go. Okay? So let's go ahead and run this. Let's go ahead and run all this stuff. Python 3 emaildb.py. It asks for a file name, mbox short. Well, I can hit enter, right? Mbox short. And that's it. And it looks just like that, and it counts it, and away we go. Now the difference is, at this point, we have a file, emaildb.sqlite. And we can run the SQLite browser, and we can then open this database, and we can see what's in there. So here we go. It has made an SQLite database. We have a table of counts, and then we can take a look at the data, and there we go. We've got the data, and we can do this. And so let me close this. It's important at times when you don't want necessarily to have, well, let's see if we can cause it to lock up. Let me run this again, and it's going to drop this table. So I'm going to run the code again. But this time, I am going to do the full one, mbox.txt. Now, we'll see what happens here. To teach advanced databases, because they're always so contextually grounded. Something like a Twitter or or Google, the databases are so specialized. By the time you make, everyone can do small to medium-sized databases using the basic techniques, but at some point, once you escape medium-sized databases, you end up in these sort of narrow things and optimize each database very separately. And so I just tell people, you know, learn the basics really, really well, write programs, and then go do real work. But database design is the act of figuring out the data that your application is going to want to store and spreading that across multiple tables. But we don't just do it randomly, we do it very much cleverly. And if you look at a data model, this is what it looks like. And what we're showing here in this data model is we are showing 5 tables, and this is a kind of a calendar kind of a system. And we're seeing the columns that are in each of the tables, and then we're seeing the relationships between the tables. And even in these relationships, there's kind of a little bit of code. And when you have an arrow that looks like that, there's many of those to one, and this is a many-to-one relationship. Many-to-one relationship. We'll talk all about that stuff. But if you go into an organization and you have a really large and complex data application, they might have something printed out on the wall that looks about like this, which shows the database tables and connections, et cetera, et cetera. And they might say, oh, your job is to go down in this little corner and add one field there, and then do this, and then connect it with this thing over there, and then make a screen that shows all these things that pulls from this table, this table, this table, and that table. And that's your job if you're a programmer on a large software development project. These database models become sort of like the core backbone of the knowledge that applications are managing and using. So the idea is that you take your application. We're going to start really simple. We're going to take your application and you have to draw a picture. And the basic rule, and literally you could spend course upon course learning about database normalization, but I'm going to distill it into one basic rule, and that is never put the same string data in twice. So my name, Charles Severance. If I build a database well, you should go into that database and you'd say, okay, the words Charles Severance, which is the name of a person, me, in that database, only shows up once. And what we do instead is we connect things together and model my name as a connection to the record that has my actual name in it, rather than putting my name all these other places. And so the idea is to pull duplicate data out and make only one copy of it. So there is the users, and in there is the user's name, and the username shows up only here, and everything else points to the particular user entry. So that's the idea. And so here is our first application. We are working as a startup. We just quit all of our jobs, and we are going to build a music management application. I mean, what a great idea. Don't you think that'll be quite successful? And so we have mocked up and we have figured out that this is what our music management application. We want to track people's tracks, know something about what artists and albums and genre they are, and we want to have ratings and how many times we played them and how long they are. Well, that's the data that our application needs to represent. And we've done testing on this and wireframes, and everyone loves this. A great user interface. And so this is how it's got to look. But we're going to have billions and billions of tracks in these things, and so we want to come up with an efficient database to handle this. And so we're going to take a look at this and look at each of the columns, and we're going to ask ourselves, is this column part of one of our existing objects, our existing tables, or is this object have to create a new table? And then once we've defined those different objects, we connect the tables together and model the connections. Now, a little trick to kind of make it a little easier on ourselves is we can look in these columns and look in the columns that have duplicate information vertically that's string information. So a rating is just a number like 0 through 5. So we don't worry too much about integers and numbers and that kind of stuff or whatever, but we do look for strings. And the problem here is we got like these strings occur many times. And so these are the problems. And so we have to put these things where there is replication of string data kind of in the vertical dimension. We have to put those in different tables. And so we'll start out. Now the first question that you have to ask yourself when you're going to draw this picture of how this data is in multiple tables and connected together is, what is the first one that you're going to write down? And this is an interesting debate, and often people are sitting in a conference room, and people who have experience kind of know what to do. Usually if it's a multi-user system, like a learning management system, the users might be the central concept. Perhaps the courses might be the central concept. This is a single user system, and so you can think, well, what is really this application about? It's not about people, it's one person, but it is about tracks. And so we can say, okay, here we'll take the track is probably the sort of most foundational notion of this application. And then we can take and say, okay, now that we've decided that tracks are the foundational notion, which of these columns are simply an attribute of the track? Not really, and the cheating way and the easy way in this particular one is like these numbers, all these numbers, like this number and these numbers, not that one. They just go along with track. And so we'll put that in. We got the track title, rating, length, and count, and we put that in. And then the question is, we've got the remaining things are, we've got the artist, we've got the album, and we've got the genre. And so we can say, okay, well, we've got some vertical duplication, so we're going to say, okay, this track probably belongs to an album. So let's pull out the album into its own table. Oops. Pull the album out into its own table. And so pull the album out into its own table. And so that pulls that out, and then you say, okay, what would be the next thing that we're going to pull out? So we pulled out the track, we've got this taken care of, this taken care of, that taken, now we've got the album. Well, albums belong to artists, so let's take out the artist. And then we'll pick where the genre belongs, and we'll just say that the genre belongs to the track. And so, because there might be albums with more than one different genre. So each album is not necessarily a rock album, it could have a rock track and a country track, etc., etc., etc. And so now what we've got is we've got 4 tables, right? We've got a track table, we've got an album table, an artist table, and a genre table. And if we sort of double check, all of the columns that had vertical duplication in them now have their own little table. So we can eliminate, the next thing we'll do is to show how we're going to eliminate this vertical data replication by showing how you represent these relationships that we just created inside of the database. Now we're going to represent these relationships in the database. And again, what we're trying to solve here is this notion of database normalization. Third normal form. There is so much theory, right? But in this lecture, I'm just going to condense this down to don't replicate string data and use what are called keys. Use integer keys to point at those things. And we're going to use these integers then to point. So we'll assign each row an integer, and then we're going to point from one row to another using those integers. And so we're going to add these special key columns to each of the tables, and help in the database will even give us help managing those. Now, and so we still need to keep track of, you know, who is the creator of the album, which album a track belongs to. We've got to create these relationships, and we have to come up with ways to store those relationships. And so the idea is we're going to have a column in a table, which is the key column, and we're going to call this the ID column. And so this is a row. It might have many bits of data here, but in this case it's just the name of an artist. So this album is going to belong to an artist. And we're going to assign a number inside the database, and so that Led Zeppelin is 1 and AC/DC is 2. And so we have this key, this is called a primary key, and then later when we want to say that the Who Made Who album really was done by AC/DC, we put the number 2 in. And so the difference here is, instead of saying AC/DC in this record, we just put the number 2 once we've established this number. So we assign keys, and then we have these pointers that point back, and so that's how we model a relationship with these small integer numbers. And so there are 3 basic kind of keys that we use. One is the primary key, and that is that little ID column that is just a number. But once we give Led Zeppelin the number 1, Led Zeppelin is the number, has got the key 1 for the rest of that database. The logical key is the text area that we use that you might look up. So the title of the band or the title of the album, that's the logical key. And then the foreign key is one of these keys that is really pointing to the primary key of another row. So that's called a foreign key. And you might think that you want to use something like an email address as the primary key for a user table or something like that. The logical key should always be separate, and there should always be a primary key, that integer number. Because things like logical keys do change. People do get new email addresses, and if you've got that email address as a foreign key pointing all over the place, it doesn't work out so well. And so that's why you use these small integer numbers that have no meaning outside. So sometimes if you're on a system and you see a URL and you see some number like 422,016, you're like, oh, that turns out to probably be my primary key in their database. So sometimes you can look in a URL and you can see these primary keys in the URL, but they don't mean anything outside of that particular system. So like I said, a foreign key is a key that is really pointing at a row in a different table. And so we have the album has a primary key for it, but the artist underscore ID points to a row in the artist table, as we will soon see. I have a naming convention, and in my naming convention on this lecture I use ID for the primary key, and then artist underscore ID I use uppercase for the table names, and then artist underscore ID says this is a key, this is just a key that points to the ID key of the artist table. And so that's what I do. So you'll see in all my stuff I'll use that. It's a convention. It's not something SQL forces you to do, but you will find when you go to organizations and work on their databases, these conventions are very important so I can do something and you can understand the rules in which I created it. Some of these, you'll find this used by some people, you'll find completely different conventions, and that'll be okay. Whatever convention your organization uses, learn that convention. So now we're going to talk about how we put these keys in and then how we actually make the connections from one row to another row. So now that we know what a primary key, logical key, and foreign key are, we're going to actually start putting these together and creating tables that have these kind of values in them. So when we were done, we drew this picture that was sort of a logical model of how our data would be spread across 4 tables and how those tables are connected. Now we have to take this and we have to map it in a way that leads to the columns and the needed columns in each of our database tables. And so here's what we do. We basically have to take, and for each of these, when we're going to build a track table, we add a primary key. So we just added an ID field to every one of these things, and that's so we have a place to store the sequence number of this particular row. We have logical keys, we've just marked those are strings, and then we have things like, rating, length, and count, they just kind of go in here. And now we have to model a relationship. So what we do is in the table that the relationship starts from, we put one more column in, and this is the one I will name album ID, and that just is an integer column that's going to record the album ID. So this might be 16, and then 16 goes in here. So there's one of these columns that's a foreign key that points to this, and that's why it's foreign. This is a key that's not in the track table. This is a key in the album table that we're pointing to, and so there's a foreign key. And that's what we have to do, and we just do that over and over and over again, and we quickly convert that picture that was a logical picture to having every table has a primary key, and every time we have a starting point we have a foreign key, and then foreign key. And then we mark these things as logical key, logical key, logical key, and we'll see how we do that. And so that's the picture. Now we have a picture of exactly how we're going to lay these tables out and the fields that we need in these tables. So we're going to do a create table statement,